future plans with this European super neutrino superbeam based on ESS. And we will start with a presentation by Markus Drakos, who is our coordinator of this EU-supported project, who will give an overview of the project to start with. Please, Markus, go ahead.
Okay, thank you, Tord. Good morning to everybody. Unfortunately, I couldn't come there to make this presentation in person. So I will speak to you about the ESS and USB design study, which is ongoing now, and what we will do, what we plan to do in the near future, because this project, the European project, will end end of March next year. So I remind you that we had already in the past cost action, which is networking on this more or less the same subject called the EuroNet. And now we had this, we prepare using this cost action, this H2020 design study from the beginning of 2018. And as I said before, we'll go up to March next year. Using these two applications, we have prepared two small videos that you can find here and here on YouTube about our project. The first one is for scientists in general, not only neutrino physicists, and the second one is for general public. So this is our design study. We have a duration 4 years. The total cost is 4.7 million euros. 3 million euros are provided by the European Union. And you see here the 5 work packages we have for this project. One on the LINAC modifications, the accumulator and the switch yard, the target station, the detectors near and far, and a physics work package. So we would like to add on the present neutron facility, ESS neutron facility, a neutrino facility without disturbing, of course, the neutron users. We would like to double the rate of the LINAC, going for 4% duty cycle to 8%, and they're also adding, instead of protons, H minus, because we have to compress the pulses using an accumulator. So we have to build also a target station at the exit of the accumulator, and on site we need also a near detector and a far detector about 500 kilometers on the north of Lund. So the mandate up to now, it is well accomplished, and we will produce a CDR at the end of this year. So we did many dissemination activities. I will not insist on that. Less now with the COVID. We have participated to this European particle physics strategy activities. As you see here in this schematic plot about all the activities considered, we have ESS and USB here. Pay attention that after ESS and USB there is comma, and after that the question marks. The question marks are not for the ESS and USB. And in the deliberation document of this European strategy group, they say that the design studies for next generation long baseline neutrino facilities should continue, and this is what we will try to do. So we had important progress now on the physics performance this last months, after getting new migration matrices for the far detector and also optimizing the target station. You see, we have started from the black lines here. We have the delta CP versus the significance. We have started here, and now we are at the level of the blue lines. You see that we made significant progress for the Garpenberg mine at 540 kilometers, and also for the Zingervan mine at 360 kilometers. Here you can see the results at the end of EuroNew in 2012. We can see here in the blue continuous line our results compared with the dashed line where we have the neutrino factory, which is considered as the Rolls Royce of neutrino facilities, the ultimate facility. You see that we have now comparable results with the neutrino factory, which was unimaginable before. And here also we have the coverage of delta CB for the 2 mines. We can see that we can cover more than 70% after 10 years. And again, here I compare with the neutrino factory, where we have more or less the same performance. Of course, the other parameter which is very important is the precision we can cover also on delta CP after the discovery. We see that here the Zinkgruvan is better than Garpenberg. We can go lower than 8 degrees for all the delta CP values. And here I compare it again with the neutrino factory. And again, we see that we have a comparable performance. So everything can be found in this archive paper we have published last month. So how to progress now further? Of course, what is natural to do after a CDR is to perform R&D. But with the present course, this is not so easy. We cannot apply for InfraDev 2, where we can do R&D, because there is a precondition that we have to be on the S3 list. We are not ready to apply to go on the S3 list. So we have to find something else. We can apply again for InfraDev 1 as the one we have now, as they did also for FCC, because for these large facilities it's not easy to do everything in 4 years. And we can also apply for an ERC synergy grant. So for this ERC synergy grants is quite a complex application, and the deadlines for the 2022 call are already during this year. You see that this is in November this year. I don't know why they call it a call of 2022. This is a call of 2021. Probably they will do the same for next year. So we don't have time to prepare an application. Now we're very busy with the CDR and what it remains to deliver for the present project. So we'll insist more on the InfraDev 1 for the next application, with a deadline of the 24th of March, which coincides with the end of our project. But we would like to have the CDR before, because we will use also the CDR during this application. So what to do under these conditions? We have to put something more than what we already did. For example, we can put everything concerning the civil engineering on site, and also at the level of the fire detector, detailed studies about safety, which is a very important item, and a few other things that I will show after. And we can add additional pillars for the ESN-USB extension to go towards the Hi-Fi project and the synergies without project. We can cut this in 2 phases, one before the approval of the construction of the ESN-USB, and what we will do during the construction of ESN-USB, again going towards the Hi-Fi. So there are advantages of the completion of the project in phases. Parts of the projects can start earlier before we have the whole facility ready. Take profit of synergies without projects. These projects also can push in the same direction than us. Financing also becomes more feasible, and we can increase also the attractivity, especially to young people. So this is what we propose to put in the new InfraDev application. We will have already the studies about the LINAC and the accumulator. For the accumulator, we can see how to add also a compressor, or use just the accumulator to compress further the bunches for the muon, especially for the muon applications. We, at the same point when we wanted to extract the beam to send it to the ESN-USB station we have here, we would like to add a small target station with only one target and only one horn to prepare for R&D after. We don't want to put it in this position there, because we will irradiate everything after. So we keep this area free for the final facility. And from here also, we can study everything concerning the muon extraction using a reduced beam, 1/4 of the beam. And why not also to add the racetrack ring of low energy new storm, hitting towards the near detector. The near detector will use also for the final ESS in USB. So we have to put everything together and try to write a text and a consistent project with all that to submit to EU. This is the possible work packages we can have. The main one is the civil engineering, the safety and the environment preservation. LINAC accumulator compressor and the low energy new storm racetrack in one work package. 1/4 of the target station, hadron muon production and muon extraction for the low energy new storm in another one. This is a very preliminary sharing of the activities. Detectors and physics performance will put everything together. We have seen during ESS and USB that very often these groups, they had meetings together. And partial design studies of initial steps towards a muon collider, the compression from 1.3 to 3 microseconds to 1 nanosecond. And again, everything to prepare the R&D phase. We cannot go yet to the R&D phase, but we need preparation for this R&D phase. We have always to keep in mind that by 2025, we will have a very powerful LINAC at ESS, and we cannot ignore this factor. Very quickly about this work packages, as I said just before. So we'll study all the civil engineering on the ESS side, the cavern construction at Garpenberg and or Zingrovan. At certain moment, you have to decide in which one to keep according to the physics results we have. Licensing, safety, and the environment protection. And just to remind that we have to follow with the LINAC all the new requirements we have with modifications of the LINAC, the accumulator and the compressor, and the racetrack ring of low energy new storm. For the targetry, as I said before, we'll have just one horn, one target, and there we can study everything about these targets. There are new ideas. Instead of using titanium spheres, to use carbon spheres. All this R&D we have to prepare it before the extraction of the muons at the level of the beam dump. This is the distribution of the pions and of the muons versus the decay tunnel, the length of the decay tunnel. So we have to choose the length of the decay tunnel and how to extract the muons from there. It will not be an easy task for that. And for this low energy new storm, we have to also see how can we do physics if we go to this direction of low energy new storm, especially for the sterile neutrinos. New storm can also be used for cross-section measurements, but for sterile neutrinos, we did some very, very preliminary studies about that. Especially we have to place the detector. This is the distance from the production of the neutrinos up to the detector. Our detector, now this near detector we have is about 0.5 kilometers, with somewhere here. So it is already quite good, this convenient, this distance we have already now. The detectors and the physics performance again, we have to see more about the near detector if there are modifications to do for this low energy new storm. And study also if there are any new developments about the far detector. News now for the future applications. I have shown you this just before. This would be for the muon cooling, neutrino factory, muon collider, and probably, why not, also muon polarization. This talk will present this with more details after. So towards now the ESS new USB construction. So we'll have these intermediate phases. This could also be part and receive funds from other HEP programs if could provide timely answers to key questions, as for example for the muon cooling. We have seen yesterday from Daniel Schultz that they have a schedule about all these activities, which more or less coincides with our schedule. And such an extension could be an important initial step. If realized, would be an important achievement towards the full ESS USB realization. So in conclusion, ESS will have the LINAC in operation with a multi-megawatt proton beams So probably they will not have everything ready before 2030, but our application, we need the full power around 2035 for our application. ESS and USB design study made a huge progress, mainly concerning the physics performance. We have seen that we are at the level of the new Technofactory. Towards R&D, further studies are of course necessary. Preparing the project in phases increase its feasibility. We have also to increase the synergies with our other projects and to have more financial contributors in this adventure. And at this moment, the only way we see it is to go towards an InfraDev 01 application. So please join these new applications. I'm finished.
Okay.
Third,
yeah.
on time.
Thank you. Yes. Can you hear me well?
Yes.
Marcus, because my mic doesn't work. Very good. Okay.
Yes.
So this talk is open for comments, questions in the hall, and also from the remote participants. Anyone? I cannot see. Yes, please. Right. Yeah. Yes. So why don't you?
Okay. No, Marcus, about the synergy. Okay, probably if I understand well, it's too early for the call of November. But do they know already whether it will be on a yearly basis as it was in the past, or because you remember sometimes they skip the call?
Yes, yes. This is my worry, but I hope that they will do like they are doing now for this year, to repeat for 2022 the same thing. But as you say, sometimes they separate. At this moment, we don't know yet.
Okay. So
in this synergy calls, there is a lot of money. I remind you that for 6 years project, we can have up to 10 million euros, and there we can do R&D.
Okay. Thank you very much, Marcus, for this overview. And we will now proceed to one of the topics that you have introduced, which is the civil engineering, safety and licensing at on-site ESS. And Boris Kildoff is going to present this subject to us. Are you there, Boris?
Yes, I am. I hope you can hear me.
We can.
Good morning. Good morning, everyone, and
morning.
Thank you very much for inviting me. So I will share my screen here. I hope you can see it now.
Yes, please go to display mode.
Yeah, just a second. Like so.
That's it. Go ahead.
So my name is Boris Kildoff. I'm an architect working with ESS. A few points about my personal background. I worked a number of years with the MaxLab synchrotron before joining ESS in 2008, and have since then worked with a number of different functions and civil projects within the ESS projects. The last couple of years, completing a number of civil structures and auxiliary buildings on site. So today I will speak a little bit about civil engineering and safety requirements for the super beam facility at the ESS site. I will try to cover a couple of points: the current status of ESS, the neutrino super beam proposed layout that Marcus already also showed, some points about civil engineering and constraints that we foresee, some points about safety considerations regarding licensing in the future, also the legal process in the future regarding licensing, and a conclusion and a couple of points on the way forward for the facility. So as you know, the ESS site looks like this this summer. Most of it is completed. You will note the large target building with its significant sombrero sun shading roof now being completed. We have the instrument hall for the extended instruments and some utility buildings scattered around the target area, and the accelerator. And to the south, we have the proposed neutrino superbeam site in this area roughly. So looking at this a little bit in a diagram, this is again the things that are completed at DSS today. And some obvious constraints we have for any other development are the proposed upgrade areas for future neutron scattering science. Also the switchyard area, which does not in a way belong to the ESS site, and the slightly unfortunate circumstance that we have a municipal tram depot to the south of the site. And you also have the constraints of the two district roads, the E22 and the Udderslövsvägen, on either side of the site. That, of course, restricts any future expansion. Also worth considering is that we have all of the main utilities supplying the ESS facility, not least the accelerator part. But all of this is almost all of this is placed on the north side of the site, allowing the south side of the accelerator to be used for the superbeam facility. So in conclusion, this is the area we have available for the superbeam proposed installations. And I think this is the same diagram that Marcus just showed, a little bit elaborated here with the transfer line, accumulatoring target buildings, some assumed support buildings topside, and of course all of the subterranean installations, including the near detector building, could look something like this once completed. So a constraint that I recently thought of was that when we originally planned ESS, the target station was placed more or less in the middle of the site to accommodate a requirement of having a 300-meter radius safety distance to the public, and if you would put the same requirement on the target for the neutrino, then of course we will overlap the site boundaries that I have tried to illustrate here with the red ring. And well, what does this mean? If you look at this image with this, which is the municipal planning status of the area where we are, you will see that we will considerably overlap the outside of ESS. Now this map is in Swedish, but very quickly to say that the pink areas here are basically areas where plans are already been made, and Lund is expanding in this region, and in the next 10 years you will see an expansion here of all kinds of settlements and projects, offices, housing, and so on. So this is of course a requirement to look into and be aware of when we plan the location of the superbeam facility. So another aspect is regarding geology, as we will be far into the ground here. In this overview, you can see that the site is intersected by a number of dikes with harder rock material, dolerite in this case. So if we look at a detailed general cross-section of the soil conditions here, you see that we have a top layer of softer materials, approximately 10 meters deep across the whole site with clay till moraine material, and then further down we have the bedrock clay shale, and this is interrupted by the dolerite dike harder rock materials that you can see in the illustration here in the middle. So if we look at a compiled section of where we will be depth-wise here, going from the ESS Clystone Gallery level to the slightly below the accelerator tunnel ESS with its shielding berm on top, we then go down to the level of the super beam accumulator, and then further down to the target. You will notice that we are well into the bedrock here, and we are well below groundwater level, which of course needs to be handled in the civil structure engineering and execution here when we build the target station. Also here in this 3D image, you can see here you have ESS from the other side. You will notice the target to the slight left of the middle of the image here. And the pink areas here are assumed extensions of the harder rock areas here. And as you can see, the proposed location here will cut through some of this, making some of the earthworks here a little bit more difficult. So again, looking generally at the geology, otherwise it is fairly uniform, which is very good from a civil point of view. Also, if we look at the types of soil, the site is very uniform, which is good from a construction perspective for us. Is a very stable geology and earth conditions here on the site, which of course also was a reason for building ESS here. And also the synchrotron, which is slightly next to ESS, as you know. If we look at the soil depth, the same thing goes here. We actually have a almost uniform type of soil cover here, actually slightly deeper even where we plan to build a neutrino facility, which will be good for us, minimizing the amount of excavations into the bedrock. And then finally, looking a little bit on general on the groundwater conditions, you will also see that this is fairly uniform. We are in an off-run area here from a ridge that goes fairly to the middle of the site along this older road here, which is the high point, and then you have a runoff of groundwater that goes down to this area that needs to be considered for the civil structures. So a couple of points to illustrate the stagings of the building project, some issues of safety, licensing, and legal processes. We need to start a legal process preparation and pre-studies to handle how the licensing will be maneuvered through the project. The scientific program and the basis for design for the technical installations will be needed by civil to start thinking about the building project. The rheological hazard analysis, of course, is of great interest and importance to the civil structures and conventional facilities projects for such an installation. The conceptual design of civil structures could begin in parallel with developing the machines and scientific installations. We need to consider location and some preliminary planning regarding exact location of the different parts of the facility, contracts for land, and how the relation to ESS will be handled within the site needs to be considered. We then fairly quickly will require a building program on a room level, basically a database with every room specified and some functional basic parameters to start a civil project. You will have to consider the possibility that the municipality will have a say on the architectural design here and maybe demand a competition or a parallel assignments for the design of the topside buildings, as this is a prioritized area of development for Lund, which of course then relates to the fact that we need a building permit from them to start any works here. After this, we can start a preliminary design going into construction that can start early, while also commencing a detailed and final design of everything. So from this list of bullet points, I would like to pull, yeah, we also have completion. Sorry, forgot that one. This is not sanctioned or discussed with you at all, but this is just maybe to start a discussion on a little bit on the time aspects of the civil project here. And I wanted to highlight here that the legal pre-study and application and permit process may be very long and extend well into the construction phase. Also to point to that the radiological hazard analysis and other aspects of safety and licensing will be very important to us to be able to start the design and civil structures construction on site. And from this, I wanted to pull a few slides here that I think are maybe important at this stage to consider. And Marcus already mentioned a couple of these. So I think it is very important to concretize the Superbeam overall technical design. Now, the conceptual technical design would be important for starting communication with authorities and starting the licensing process. I also think that it would be good to involve legal advice, as the licensing process is very complex. As Marcus also mentioned, the civil pre-study of geotechnical, hydrological, and environmental constraints maybe should be considered to start pretty immediately, and also to start some meetings with authorities to know a little bit how we will handle the permit process for the project. So the estimate we made here is that this is maybe a half to 1.5 year work that needs to be considered in the next couple of years. So another point to pull from this would be to say something about the Swedish Environmental Code. We will need to start a consultation process with all the external stakeholders in relation to how the environmental code works in Sweden. Then, of course, and this is the long process, is to set up the full application, including radiation and PSR documentation. And you then have a hand-in of the permit, including then public hearings, appeals, and the time that may be foreseen that this will take before you have a final file and license for the installations. And the purpose of this is, of course, to prepare for the final permit. And the time aspect here may be as long as 10 years, and as I said before, may extend into the construction phase of the project, and is likely to do so. So it would be urgent to start working on this. Then finally, regarding civil engineering pre-study, well, a desk study would be needed first to look at what documentation is already there. We then would go on site to do some drilling and radar investigations of the soil and bedrock to get also some deformation analysis and structural basis for design of the civil project. Now, some of these, of course, can be carried out in parallel and also during construction, but I think we need a basic geological study to know a little bit more about the ground here and how we can build the tunnels for the installations. So the estimated time aspect here is from 2 to 4 years, and again, this can be extended into the construction of the facility. So to conclude these points and hopefully point the way forward, I think the technical baseline design of the facility and civil structures is pressing. I think considering the legal process regarding permits and assigning some legal support here for the licensing part would be important to consider. We will commence a civil pre-study for optimizing the design of the facility. Of course, also the civil pre-study will enable us to make the facility more efficient and cost-effective. The study of radiological hazards to the third part outside perimeter would be necessary to look into. And also, of course, the issue regarding the groundwater and how this will be handled would be looked into in the near future. So that's basically it. And just to leave off with something a little bit more exciting than the legal aspects and safety requirements, the actual facility here in a 3D model that we have worked with to illustrate what it might look like. Thank you.
Thank you, Boris, for this very interesting overview of number of practical aspects that we now have to face when it comes to civil engineering and safety. So this talk is open for questions, comments in the room. Any? Yes? First. Yeah, sorry.
So question, can we buy the land across the street in which the radiation safety perimeter extends?
Yeah, that's a good question. I'm not gonna say we can. I think it's unlikely, but of course it could be considered. Maybe, as you noted, the map I showed was from last year. I don't know actually how far the municipal plans have proceeded in this area in the last year. But of course, and I think this was also raised in the last meeting, if we can, so to speak, extend the ESS site to the north and south, which would be interesting for this project, but also for other future science projects connected to the ESS site.
Okay, thank you.
Thanks, Stuart. So, Roman Zanov from Sofia. Your 3D model does not extend to the near detector position. Could you comment the geological conditions there, if you have some idea? I think you have, and keep in mind that from the target, we have 42 millirad inclination to the near detector, so it will be around 10 meters deeper.
Yeah, I'm aware of that. So I didn't even dare to illustrate this as it will be very deep. And actually, I don't have any geological data going that deep into the ground at the near detector site. So at this point, I would have to say we don't know exactly what's in the ground there, but that will have to be looked into, of course, and considered when planning the angles here, if you so will, to see how deep we can go. But basically, as far as we know, we don't have the hard dolerite section in anywhere near the detector site, which is a good thing. So we only have the softer bedrock material.
Any more? No? On off-site? Remote? Comment, question?
I think.
Yes, please, Colin.
Colin Carlisle. Thank you, Boris. That was an excellent talk. I really enjoyed it. I would just make a comment, and that is that the 600-meter exclusion zone that we placed around the ESS target was not demanded by authorities, but this was simply transferred from the experience at the ILL reactor in Grenoble, where the authorities had demanded a 600-meter diameter around the ILL reactor. And the other point I'd make was that there is room for expansion to the northeast, which is backwards from the iron source. That is just a field, and I'm sure arrangements could be made to expand there. It's not impossible to go to the northwest, which is more difficult because of the E22 motorway, but it's not impossible. And to the southeast, I think it's rather tricky because of the developments of Lunds Commune in that area, which is going ahead so fast. But thank you.
So let me just explain that Colin used to be Director General of ESS and therefore has this detailed knowledge about permission.
Yes, I completely agree that in this area here is likely to buy more land and expand, whereas to the south here it may be more difficult.
Okay, if there are no more questions, comments, then we thank Boris again, and I now call on David Sayang, who will talk on civil engineering and safety requirements for ESS and USB at the far detector side. David is a professor in geology, mining engineering at Swedish Luleå University in the north, and has joined our project, bringing his competence in that field. So, David, are you there?
Todd, I am here, but I need you to see me as well.
Yes.
Start video.
Here you are.
Okay, here I am. And now I need to upload my slide, I think.
You do. So go to display mode. That's it.
Okay.
Off you go.
Thank you, Todd. Todd has already introduced me, and my presentation is civil engineering and safety requirements for the ESS and USB at the far detector site. So our previous speaker has talked about the near detector site. So I will go straight to my presentation. We have basically identified two mine sites. They are located, as we have heard from Marcus, who was talking about this mine here, Singruvan, and also talked about this mine here, Cabenberry. These two mines, the distance that are located around the radius from ESS Lund, the distance to Singruvan mine is 360 kilometers, and to Cabenberry 540 kilometers. Mines have a well-developed infrastructure. That will also bring up another question, which my previous colleague speaker has talked about is licensing. The reason why this becomes important is because they have what they call a special mining lease. And that means whatever infrastructure they build in the mine has to be related to the mine. Our infrastructure has nothing to do with the mine. So that is an issue we have to look at, whether we are operating in a mining lease. So this is a legal issue that also needs to be looked at later on. What we have done so far in this far-field detector site is we have done some preliminary assessments. We have done field visits to both mine sites. We had meetings with mine managers, geologists, and engineers. And we have basically identified some locations of the mine site, around the mine site. It's important that one of the things to be careful about is that we have to also consider that will the mine expand in the future if they find new deposits, or they will potentially basically encroach into our area, and that is the risk. But for that reason, it's important that we talk with the mine manager and engineers to find out where we are able to our activities. We have also done some preliminary assessment using a computer simulation. So we have done three-dimensional numerical simulation and look at some of the risks. And we identified that further work needs to be done. So basically, this is one of the sites we looked at, Singurvan Mine, which is located 360 kilometers from Lund. And the location we have chosen for this area after discussion with the mine geologist is located on my left here, is located about 1,000 meters or 1 kilometer underground. And this is the location here that is of interest to us. So we have basically tried to see if we place two of the caverns in this area, how they would look like. And that would help us to do some computer simulations to see how our infrastructure will interact with the mine. That's very important because our activity would basically affect the mine, and probably the mine will not be happy about that. And that's very important that we know that our activities do not disturb the mine, and the mine's activity does not disturb ours. So, and that requires three-dimensional numerical simulation. There is another thing I want to highlight here is the infrastructure. The waste rock that we will take out, we will use, most of it will be using the mine's infrastructure. They have several shafts here. One of them is a ventilation shaft, and the other two shafts are the ones that we will use. But the most important thing is this is only to handle waste, and we have to know the capacity of the shaft so we can use those kind of infrastructure. But to take in the water, we cannot use the shaft. We have to use what we call the declines or the ramp. So if you follow my mouse here, you see this is a decline that is going, or ramp, that is going up to the surface. So we will have to use pumps and then move the water to our caverns, okay? And that requires also to communicate with the mine to see if we have the capacity to do so. Basically, what is important in regard to the safety is one of the most important things we want to look at is the geology. And is the site, the question is always, is the site safe enough to host our infrastructure? And that means looking at the geology. And what we know is that the mining companies usually try to map as much as they can around the area of interest. They are mostly interested in the ore body or the deposits they are mining. So anything outside of the deposit, they really do not focus too much about it. They do have some ideas about what the geology is around, but they do not have any detailed information. So basically, that's what you see here, is that we have some idea from the maps they have generated. So the area that we are interested in is located in a rock called marble. It's a limestone, but it has been metamorphosed to strong limestone. And then we have the quartzite there, which is also a metamorphic quartz. So these are quite high strength rock. So in terms of engineering, we can use what we call the rock mass classification, and we can plot it on a graph like this. And we can see here that the rock here is, it's fair to good. So it is basically a good material for the purpose of engineering construction. So, but this doesn't mean that we can go ahead and start constructing the caverns there. We need to do more investigation. Like I said, this is basically from the general information that we get from the mining companies. And this is the other side, which is further north from Singruvan. It's the Cabanberry mine. It's owned by Boliden. The Singruvan is owned by Lundin. This is the mine this is a new mine. The old mine is down here called Cabanberry South. The mine is located in this boundary, and this the boundary is here, the red line. We are mostly interested in this area outside of the mining boundary. And over here, you can see how it is, the map of the geology. So you see the mining is going on in this area that is labeled here 1 to 8 and 1 to 9. And you can see all this blue, that's the ore body. And we are outside this area. It's mostly in granite. And you can see here that this is just a granite and it's not fully detailed, so we don't know much about what is there. So anyhow, we need to do more work to find out what the granite is, so we can carry on further investigation. So again, the granite is shown here. It is a very good rock, fair to good rock for engineering purpose. There is another thing I want to talk about is the stress situation that we have in Scandinavia. That's mostly in Sweden, Norway, Denmark, and of course, if we include Finland, then it's called Fennoscandian. So the stresses in our region are quite high, very high, in fact, in the horizontal direction. And if you can see that we have almost 3 times in the horizontal direction. So that gives us a lot of problem to have a vertical excavation. So typically what we normally see is that we have mostly kind of a horizontal excavation because of we're trying to streamline the stresses. So this is one of the challenges we will face when we design the caverns. And here I also made a comment here. One of the additional problems we will have is the stress that is induced by the mine, because we are using the mines. So generally we use a rule of thumb, and the rule of thumb is that the disturbance or the stress that is induced by the mine should extend 2 to 3 times the width of the mine. So that means if you know the width of the mine, then you have some idea how far you should stand off in order to be safe. So we have built some numerical models. Our initial model, you can see, is 65 meters in diameter by 100 meters, but this has changed. These dimensions have changed. But I show you the result from our early analysis. Okay, and this is what I mean by the disturbance from the mine. So you can see we have this area which has been disturbed because of the mining activity. So we cannot stay inside this area. This area we will have trouble with our excavation. So we say standoff distance. So we try to put it outside here. So we estimate this distance to be about 200 meters. So we try to place the caverns outside of the mine area by 200 meters, 250 meters here in the model. So, and then we space the caverns by 150 meters. As I mentioned, the rule of thumb is the diameter of the excavation times 2. So I put 150 here to be a little bit off by 3. And then we can see here the interaction. So we can see that our caverns are interacting with the mine, but not so much. We looked at the stress, how much of the induced stress, the mining induced stress, can affect our caverns, because it affects the stability and thus the safety of the two caverns. So this is important. We need to know that. And then we look at what we call displacement, or how much does the ground deform if we are considering that the influence of the mine. And you can see that we are within the range where we will be affected. But this is to be further studied, so we can know that we can control this kind of deformation or this kind of stress by our reinforcement system that we use. Basically, this is what we see in generally in the Swedish environment. When we go deep, we see a lot of damage appearing on the walls. And this is also what we see evident in our computer simulation. So this will give us some idea on how to reinforce the caverns. And this just gives you a general idea of how the Swedish designs are generally because of the stress conditions. The way is that we try to align the excavation in horizontally so that we can streamline the stresses. But as you see that in our design for this ESS and USP, we would have a ratio that is a little bit more higher vertically. So conclusion from our initial study is that the caverns can be investigated further detail. And again, I come back to what Boris has said earlier, that we need to actually do a lot of exploration work for the site. So to assess the rock quality, we need to do assessment investigation of the engineering parameters of the rock. We need to also think about the groundwater, because the groundwater will affect our stresses. And also the mine will be worried that we might divert groundwater into the mine, and that's not a good situation for the mine. And we need to also investigate the stresses, because the mine that is actually going ahead has created new stress regimes. So we will have to do stress measurements to get the new stresses that will affect the stability of our construction. There is some risks here that you see, that we would have what we call mine-induced seismic tremors, basically small events, seismic events that we need to monitor. And then we will have major stress shift due to mining of the newer bodies and mine-induced in situ stress. So we, again, coming back to what we really need to do quite immediately, if we want to go ahead with this site design, analysis, and investigation, we need to basically do diamond drilling. That's important because diamond drilling will give us the detailed information about the rock itself. We can collect samples for testing in the laboratories. We can get an idea of the rock structures. And this is the kind of information we get. And with diamond drilling, one of the things that we do is that we orient the hole, and that is important. And you can see this is an example down here. This orientation of the drilling is important, and we can do that in order for us to measure the structures like this, and that's important for the stability of the caverns. And we can perform that even from the underground or from the surface. And we can utilize geophysical exploration whenever or where it is necessary. Okay, so now it's coming to mostly the final points of the safety requirements. So you see here that first of all is the quality of the rock mass. The question is the rock fit to host the infrastructure? And to do that, we need to understand the competence of the rock to act as an engineered infrastructure. So we need thorough investigation of the site geology and its engineering characteristics. Another parameter we need to investigate is in situ stress. It's important for the stability of the caverns. The in situ stresses in the Scandinavian silt are very high in the horizontal direction. And that is important, as I stated earlier, that we need to look at it because our caverns has a greater ratio, aspect ratio in the vertical direction. So groundwater, it will affect the stability of our caverns. That needs to be investigated. Seismicity. Seismic events will affect the stability of the caverns again. So there is not so much of earthquakes in Sweden, but it's worth looking at it. But the closest event we can look at is the mine-induced events. And that's because of the mining is going deep. And then the stress builds up, and then you have rock burst. And then we have earthquake events that we can register. So design construction. The shape of the caverns must conform to the ground stress conditions. That's important. And then we have the ground reinforcement, which is vital to the safety of the infrastructure, both dynamic and static support. What I mean by dynamic and static support is that if we have seismic events, then we need the dynamic support to help us overcome the seismic events. And then static support is when we get just static ground deformation. So the construction is to be highly procedure driven. This will allow us to reinforce the ground because it's very wide. It's not easy to reinforce it with a normal practice. So it will require a highly procedure driven procedure to do it. And interaction between the mine and the ESS and USP infrastructure. The activities of the mine will affect our NUSP infrastructure or vice versa. And this is important because neither the mine or our project would be happy if we affect each other's activities. Water management will be critical to the safety of both the mine and the ESS and USP. It will be particularly a very significant concern to the mine because, for example, if we lose 1 million cubic meter of water, we have basically killed the mine. And that's not what the mine would want to risk. So these are some of the considerations we need to think about. And then also I mentioned that we have to also think of other things like, if I go back to this slide, we have to also think that we are operating in a mining lease, special mining lease. So it's outside of a civil engineering lease to construct. So this is a legal thing, and I cannot comment on that. That we need to look at from a legal point of view. Are we able to construct on a special mining lease or a special mining license area? That is one question. So now I'm coming to the end. We don't have any such cavern of these dimensions that the ESS and USP demands, that is at 1,000 meter depth in Scandinavia. So if we build it, it will be the first of its kind and at a very difficult condition. And the Scandinavian rock stress will put excessive pressure on the infrastructure. The reinforcement of such an infrastructure at 1,000 meters will be impressive, meaning that it would be costly and it would be not the kind that you see used in tunneling and in mining. It would be a unique kind of reinforcement design. The construction of the infrastructure will be challenging and will require detailed engineering. And I would like to emphasize the same, come back to the same point that Boris, the previous speaker, has mentioned, that we would probably have to start early if we want licensing, because the experience tells us that in Scandinavia, To obtain a license to construct typically takes 3 to 10 years. So because mining companies, even well-known ones like LKB, can wait for 10 years before they get even a license in a mining property they already have. And this is always when it comes down to environmental issues. We are going to deal with waste rock. We are going to deal with water. According to the Swedish law, that's considered our byproducts or the waste. And according to the Swedish law, we have to prove how we could manage that. And that's the most difficult part that we need to look at. And to be able to move forward, I think we should start a little bit earlier on this. I think that's the end of my presentation.
Thank you very much, David, for this overview of all the multiple aspects of the mining project. Do we have questions, comments from the audience?
So David, in your slides, you put the cylinders of our detectors 65-meter wide and 100-meter tall. In our baseline, we have 78 meters wide and 78 meters tall detectors. This maximizes volume to surface ratio for the detectors. So if that cannot be achieved, you should speak now, and we should come to agreed dimensions with the detector, because we start kind of technical design, engineering design of that detectors.
Thank you. What you see here was a preliminary modeling from the initial work that we have, but now the design has changed. So this model is to be updated. The 1-to-1 ratio would basically, if you look at the results that I have shown in this, this is the Swedish kind of conditions that we see. I think the 1-to-1 ratio or even lower would probably help us in this case. And the most important thing is reinforcement. If we can come up with a reinforcement that can hold the caverns, I think it is possible to construct at depth with that ratio that you mentioned.
Let me make 2 comments. One is when David talks about reinforcement, this is there are 2 main technologies from that. One is to drill long holes, like 10-meter deep holes horizontally into the rock from the wall, and install a bolt, a 10-meter long steel bolt, to hold back the wall from cracking. And the second technology is called shotcrete. It's concrete that you pad onto the walls, maybe a meter thick, in order also to keep the wall, the cavern wall, from cracking, and that there will be debris falling down the wall. The other comment is that we hear here that there are to use an active mine has a number of complications with on the 2 sides that we have to solve and avoid, but it also has advantages, of course, like access shafts, ventilation, organization of the area, which is very valuable for us. So this is why we project to be in a mine and not start a green field, or whatever to call it, mine, where there is no such existing infrastructure already. So let's then, if there are no hands raised on the web.
Yeah, I have a quick question. Thank you very much, David. Very interesting talk. So my question is more of a general one, because of course, the rigidity and civil stability of the caverns is essential. But what about the requirements from the detectors? Is the detector in itself sensitive to the settlements and seismic events we can expect here, and the possible disturbances from the mine? Of course, I am exposing my on the knowledge about the detectors here.
I wouldn't say so, but
but it would be interesting to know how the requirement from the detectors relates to your talk.
So if there are disturbances from kind of stresses, those will be, I expect, short events, and we will just draw out the data taken during that time.
I see. Yes.
No major interference in that respect, I think. Okay, so
thank
you again. And we will now listen to Colin Carlisle. I already introduced. Colin is a visiting professor at my university, Uppsala University, former first Director General of ESS. So it's very valuable to have you, Colin, with us, with all your experience earlier of ESS, and in particular when it comes to starting up a major project of this kind. You were the person who did that 10 years ago, starting up ESS. So please, Colin will talk about the environmental conditions for our project in connection with society. Please, Colin, the floor is yours.
Thank you, Tord. Let me share my screen. I've shared it. I need to go to full screen, which I think is here. No, where do I get full screen? View. Right. So thank you for including me in this interesting morning. I wish you a good morning from Lund in southern Sweden, and hello to Cagliari. It's a good sign that there are open meetings beginning. So here we have a view of the ESS site from the country road. On the right, you see the ESS buildings appearing, rather majestic cloud scenes there. We're looking into here in this paper, the societal impact of ESS New SB. I'd first of all like to go to a person who influenced me a lot in my neutron days, Peter Egelstaff. He gave a seminar at Rutherford Lab many years ago now, in which he said that since the Second World War, the gestation period of large-scale facilities has increased by 1 year for every year that has elapsed. In other words, you start, if you have an idea today, it takes you N years. If the idea doesn't come till next year, it takes you N+1 years to achieve your dream. So we looked into this. That's Ken Anderson and I. Ken now is the director of the SNS at Oak Ridge. And we put neutron sources onto this. So on the y-axis, we have the year of the first idea, and on the y-axis, we have the number of years it has taken to achieve full specification since 1945. And you see it's more or less a straight line. Although ESS is supposedly today at full specification, so this line is curving upwards, in fact. But let us put ESS New SB on there. And then we find that ESS New SB from the first idea, which was just before 2010, would take about 43 years. So full specification by 2052, by which time I will be retired, but I think that Tord probably will not be.
Yes.
The slope of this is not 1 year per year, but it's 8 months per year. In other words, the longer you delay, the longer it takes you. So let's look to the future. The future, in terms of funding streams for these kind of developments, is Horizon Europe. We've heard from Marcus about this. And when we look at the 3 pillars, then we find that there are certain boxes that need to be ticked. Research infrastructures, of course, fits us. But then we have global challenges. And despite the fact that these pillars are supposedly separate, there is overflow. Health, culture, civil security, digital economy, bioeconomy, agriculture, environment. And then the third pillar is innovation. So we have somehow to tie together these three pillars as we go forward to Horizon Europe, as Marcus said, 24th of March deadline. And what we have to admit to ourselves, whether we like it or not, is that we are selling our science. No one owes us a living, and we have to accept that. And then we have to say, but to whom are we selling our science? Well, naturally, we put a lot of effort into selling our science to scientists, our colleagues, those who are pursuing other projects in neutrinos, and those who are pursuing other projects in totally different disciplines. All are competing. Then, of course, the funding agencies who don't like to commit themselves, and research ministries who even less don't like to commit themselves. Industry that comes in and can benefit enormously, as they are doing at the ESS now, and the taxpayer who has got to be able to see that what is happening in his or her environment is actually a benefit to them. And then not exactly identifiable as a person, but the environment. We have to be extremely sensitive to the environment. So if we put a traffic light system onto that, I would say that scientifically, it is recognized that this particular project is extremely powerful and would be a next generation facility. The funding agencies, we've been partly successful, but the other four, we have not. An effort has to be put into those four in order to go forward. So in order to work out the impact, we have to work out the full lifetime cost. These are my unofficial estimates. These are not from the costing group that is working hard. And I came up with capital costs of 1.2 billion euros over 10 years, operating costs 75 million per annum, and a 50-year period for operating, let's say. Then politicians and agencies, environmental agencies, demand decommissioning as well, back to a greenfield site, which roughly speaking, 1/4 of the capital cost. And the number of employees, whether they are employed directly, whether they are in kind, whether they are at home laboratories, but must be paid, is about 280 employees in my estimate. And that makes a full lifetime cost of over 5 billion euros, which is quite reasonable, I think, a duration period of 65 years. How many jobs would be created? This is an important thing for the economy, both locally and distributed. And we have to be very much aware that whilst this is on Swedish soil, benefits have got to flow over to the other partner countries. Taking the average salary in Sweden, adding all the costs, social costs on top, and adding 50% because of the highly technical staff, we come to 120,000 euros per year to employ one person. So the payroll costs would be 34 million euros, which is about 45% of the estimated annual running costs, which is about right. When I was in Grenoble, the Institut Langevin, their payroll costs were slightly under 50%, and the European synchrotron next door was slightly over. We have to identify where will these employments be. Of course, the majority will be in the host country, but they will be internationally recruited, or they will be seconded as an in-kind contribution, or they will remain in their home laboratory. For example, we might use the data management center in Copenhagen, which manages the data from the ESS. And those employments, extra employments, would be included. So what is the impact on jobs? Direct 280, but then there are the indirect jobs. They are the support activities that are needed to added often as part, as months per year, and that's roughly double the number of direct employees. 560. But then there is the larger figure, and the larger figure is those jobs that are created by a kind of gravitational attraction to high technology sites. And we see that in different places like CERN and ILL in Grenoble, ISIS in near Oxford, and on the west coast of the USA. This is the largest, but takes the longest. So indirect activities, they range from hairdressers, banking, cafes, transport, cultural activities, housing, everything you can think of, it requires for families and organizations to exist. Induced or gravitationally attracted activities, they range from the relocation of industry. We've got an example of that only last month here in Lund. Kockums Saab, the submarine manufacturers, windmill manufacturers are relocating just to the southwest of Max 4. We had the news last week that a European Space Agency incubation center will be located at Lund. And then we have regional investment around the ESS, and a key one there is the tram line, which is now fully operational. Whereas when we look to CERN or we look to the ILL, tram lines for bringing in people to the research centers has taken 10s, 20s, 30 years to achieve. So what's the impact on innovation of having such a huge capital investment? Well, it is enormous. And the question is, how do you manage it? And how can you, let me use dirty words, how can you monetize or politicize these innovations? And there are ways to do it, but it has to be organized and it has to be clearly accepted by governing bodies. But we see on the right examples of now household names of Swedish innovation. Sweden is rather a fertile place to nurture innovations. So how would we mitigate our costs with respect to innovations? Well, we would follow the example of the European Molecular Biology Lab, EMBL, and their enterprise management system, which they have put in place. EMBL is non-profit, but they have put together an enterprise management organization which earns roughly 5 million euros per year from the innovations that have taken place in EMBL labs. And we should be looking at how we can do that. The other way to mitigate costs is that we recycle our cooling water to Lund's district heating system. Another way is that we actually own the means of generation of electricity, and that locks down the cost of electricity and makes us immune from electrical cost variations. And then, as we heard from David, 3 million tons of granite, building material, excellent building material, and we have to deal with this so that we have a plan for that. And then a fifth thing that I have there is that it is essential that we enter into a partnership agreement with ESS and that we share resources, we share staff, and that will help to bring down costs on both facilities. So let's look at energy. What's the impact on energy use? Let me check the time. The accelerator power will increase from 5 to 10 megawatts. The electrical power increase supplied will go from 30 to 60 megawatts. 30 megawatts for ESS and USP. If we take 65 euros per megawatt hour, we end up with electrical supply costs of 12 million euros. Which adds to the payroll cost and gives us 61% of the annual costs. These two items are a significant demand on our annual budget. So do we accept the fluctuations in costs month by month? Do we accept to operate when electricity is cheapest, which certainly happened at ISIS, or is there an alternative? Now, when we look at the development of electricity prices, this is last week in Sweden. And it's much higher than the 65 euros, and it fluctuates enormously. So making contracts is not easy. It's far better to have your own means of generation. And we see an example, which is excellent. The Sesame synchrotron has a solar field that supplies all of the power that is needed during the year. And ESS came up with this idea 10 years ago. Partly it's been implemented, but it was rather a frightening concept 10 years ago. But today, the political and environmental opinions have changed enormously. I must say that this particular strategy that we had played a big part in winning the site decision for ESS in London. So I pulled out some slides of a talk I gave 10 years ago about the ESS. Carbon dioxide neutral over the lifetime of the facility, and we had our slogan, of course. Now, this is how you would usually do it. You need 30 megawatts of power, you put your plug into the mains, and you draw the power out. You have to heat, that's 15 minutes. You have to heat your buildings, etc. And of course, you draw that from the Lund district heating system. This is costly, and environmentally, you're helping to generate 165,000 tons of carbon dioxide every year. Now, 10 years ago, I said, this is how ESS will do it in 2020. Well, partly, but not quite. You own the means of production. And we had an agreement with the Nordic Investment Bank that they would finance this for us. And you would generate over a year the electricity that you needed to run the facility. And the hot water that you generate by cooling the accelerator would be fed into the Lund district heating system, and it would be sold to them. And that is happening. There is a link now from ESS to the district heating system. And so we quantified the energy flow in the different parts of the accelerator and the target station, calculated how much energy was needed, electrical in, and how much heat was recovered. And it's quite considerable. And we should be thinking about this for ESS and USB and encouraging the ESS as well to fully implement those plans. Conclusions. Electricity consumption is reduced, carbon dioxide savings are high, the operational costs for ESS are reduced. Our cooling water becomes someone else's heating water. Roughly 10,000 houses could be heated. And we would factor out the effect of electricity cost fluctuations. And this is really important. You're able to determine in advance what your annual costs would be in your budget. It's no longer such a fluctuating call on your annual budget. And believe me, when you go back to your governance bodies and say the cost of electricity has risen, they say, well, fine, you've got to find savings from within your own budget. So we have to bear this in mind. Then finally, in-kind contributions. They are, excuse me, they are very important, essential. Nowadays, large research infrastructures are only built using in-kind contributions. So we need an inventory of needs. We need a cost book where each item on the inventory is costed. We need a directory of suppliers, and then we need candidate organizations and countries who would fund those items on the inventory. And we must ensure a balance of benefits for all partner countries. We are well aware that this project would be in Sweden totally, and therefore it is essential that we do a lot of work to spread the benefits. So I thank you for listening. And the message really is that nowadays an awareness of societal and environmental impact really is essential for success. So thank you very much.
Thank you, Colin, for this valuable overview. And I couldn't agree more with your final statement here displayed now. We are not communicating only with the scientific community, but with the whole society on many essential lines, as has been illustrated. Do we have questions, comments from the audience in the hall?
Yeah, thanks. Albert Rook here. I agree with all you said. Maybe I should. I don't know if I'm in the camera. I should look there.
I can see you.
Oh, great. I had the following add-on to this, and this is if we should also be paying attention to the economic impact of what we are doing. And I give you one thing just as an experience I had myself about 5 years ago, that there is actually a professor in Italy, Fioro, from Milano. I don't know if people know him here, which I just picked up again. And he made an economic analysis of the LHC and also of a possible center for hadron therapy, and to see what the whole thing costs, and being very generously, but then also what the benefits are. Like with all the PhDs you get, all the products, say the World Wide Web, the Giant 4 and things like that that come out of it, which can be used, and calculate that also in. And I was actually surprised, being part of that analysis, that it came out on par, that maybe the LHC costs 10 billion, but it also produces 10 billion or even a little more on benefits, on economic impact for, like what you see, attracting industries close to it, the PhDs and everything like that. And for, of course, for the hadron therapy, it was even like 3 times or 4 times what you put in, what you get out again. And I wonder if that also are arguments one could play on to, you know, to make awareness to the public that we are not just burning money, but actually something comes out of it, even if they don't see it sort of like directly.
Yes, you're absolutely correct. What I would really like now at the moment here in Lund is that the Lund's Commune, the local politicians, should do a review of the benefits economically that have occurred because of ESS. They are enormous. We did a study, Copenhagen University did a study for us of the predicted benefits to GDP of building the ESS. This was before we got the site decision. They came up with a figure of 0.018% to the Swedish GDP, the whole Swedish GDP, per year, every year, added on, cumulative. It doesn't sound a lot, but when you actually do the calculations, it's enormous. And I think you're absolutely right. We really have to work those numbers out. So thanks for the comment.
Any more questions, comments in the hall? Any raised hands? I cannot see that, so let's thank Colin again.
Thank you.
And I now call on Janet Conrad from America. We'll be dialing in, who will be talking on the use of the neutrinos, diffuse neutrinos coming out from the ESS USB target. There are diffuse neutrinos coming from the ESS target, but they are impulses of 3 milliseconds, whereas those from the ESS new target is from 1.2 microseconds. So the background is suppressed by a factor of 1,000. And this is very useful for experiments like decay rest and coherent neutrino scattering, which Janet will talk to us about. Are you there, Janet? Yes, I see your slide.
Yes,
and what's the time in your place now?
It's a little bit after 4 a.m. But I'm very happy to be here and give this talk. Thank you very much.
Thank you so much, Janet, for this. Go ahead, please.
All right. So what I'm going to talk about is a complementary program to the ESS and USB program, one that's located on site at ESS. And it's one that is using the decay chains of mesons that are produced when protons hit a target, and these come to rest and decay at rest. So I'll be talking about prospects of decay at rest and coherent scattering at ESS. And so this is actually an area, decay at rest is an area that has where there's really rising interest. And I wanted to just start out by talking a little bit about why there is so much interest worldwide in this type of neutrino beam. And the first is precision. The decay at rest beams have energy distributions and flavor contents that are very well described. Nature describes it. And there are also 3 low energy cross sections that can be accessed using these beams that are very well known. So as we move into the precision era of neutrino physics, these are very valuable beams to have. They're also quick. Most experiments being proposed are actually relatively low cost. Many of these experiments are using relatively small detectors, and even new state-of-the-art technology is affordable given the size of the detectors involved. And also approaching physics, the neutrino physics questions in this way is not your same old approach. There's different questions of systematic uncertainties and so forth. And so it's really nice as a complementary approach to what we have been doing so far. There have been other decay at rest programs. In fact, there is one ongoing right now at JSNS squared, for example. But this would be an opportunity to have a very large facility doing decay at rest experiments. So the rest of my talk, I want to discuss briefly the fluxes, both at ESS and in comparison to others. I want to talk about the 3 classic interactions that are used for decay at rest experiments. In particular, one is the coherent neutrino interaction. And then I want to talk about more physics opportunities beyond this. So let me start out by talking about the fluxes. So most of the running and proposed experiments are making use of pion/muon decay at rest fluxes. So the pion decays, it produces actually a monoenergetic nu mu at about 29 MeV. Then the muon also decays, and this is decay at rest. So it's come to a stop. So that produces then a very well understood flux of electron neutrinos in anti-muon neutrinos. And in this decay chain, if you set up your target properly, most of the pi minus and the mu minus will be absorbed. So there's actually negligible new anti-electron neutrinos in this flux. So as I said, there are many experiments that are interested in this. And so this gives you a sense of what the pion-muon decay at rest landscape looks like. And this is a little bit different from the plot that I have shown in the past. This one was suggested to me by Juan Collar. And what's important about this plot is that I've replaced the simple power coming out with the neutrino flux. And that's what really matters in these experiments. So this shows signal to background along the y-axis, and it shows the neutrino flux along the x-axis. And you see that as you go up toward the upper right corner, that's better. And here you see ESS as it is, and then this is the short pulse upgrade for ESSSB. And you can see that it does improve by in order of magnitude these signals to backgrounds. I also want to point out to you that this is actually a study by Juan that is based on the neutrino flux that is coming from the ESS target, which is meant to produce neutrons. And if you were to build a specialized target for neutrinos, you can produce an even higher flux. One of the things that's unique about ESS is the energy of its beam, or relatively unique. Most of the experiments that I showed you on this previous page are using protons which are below a 1 GeV. Below 1 GeV, you can produce pions very well, but you can't produce kaons. And so one of the things that opens up if you go up in energy, you get to a kinetic energy of the beam of about 1.5 JeV, is that you start producing kaons, and you can make use of that also and have KDAR. So KDAR is actually the same chain as the PIDAR chain. You get a K plus that's decaying monoenergetically to a mu plus. That monoenergetic nu mu that comes out actually is about 236 MeV. And that's actually quite a nice energy for use, because you can do CCQE scattering and neutrino scattering with that. There are lots of accelerators in this world that produce kaons. You know, you can go to nearly any accelerator out there that we use for particle physics, and it's producing kaons. But what you're looking for is you're looking for a place that will produce kaons that come to a stop and decay at rest with minimal decay in flight, because your decay in flight backgrounds actually sit at higher energies, and that feeds down on top of your decay at rest signal. So while KDAR has been seen, for example, off of the NUMI line at Fermilab, where the NUMI beam dump has been used for the decay at rest signal, it has been greatly diluted by the decay in flight neutrinos that are coming that are at the same energy or higher. So it's really nice to have a place where you can actually produce the kaons and they come to a stop in decay and have a much higher rate than the decay at rest flux. The example that I'm giving you here is JPark. But ESS will be very competitive with JPark. JPark has 3 GeV protons at 1 megawatt, and ESS has 2.5 GeV protons, so lower energy, so you'll get less kaon production, but at 5 megawatts to make that up. Okay, so how am I going to use these fluxes? And I want to say I use the word beam, but actually these are isotropic fluxes. It's like a big neutrino bomb. And there are 3 classic interactions that you can use with this. One of them is called the Sevens interaction, or the coherent neutrino scattering interaction. And it has the highest cross-section of the 3 classic interactions that I want to talk about. All 3 of these have theoretical predictions that are good to a few % level, so that is why they are so nice for precision. But coherent neutrino scattering is the one that's gaining a great deal of interest at the moment. And that's because if you write down the coherent neutrino scattering cross-section, it turns out to be dependent upon very well predicted numbers. In particular, it depends on sine squared theta W. And also it has a form factor, but this form factor can be well calculated. So that's the beauty of this, is that this cross-section is very well predicted. Also, another beauty of it is that you can actually change that cross-section in a well-understood way by changing the neutron number of your target. The problem with this is that coherent neutrino scattering has a neutrino come in, a neutrino go out, and it has a recoil nucleon, and you must be able to see that recoil nucleon in order to be able to know that the interaction happened. And that is very difficult. This is quite low energy. And so that is why, even though the cross-section is so large, it has taken a very long time for us to even start seeing coherent neutrino scattering. But at this point, we have observed coherent neutrino nucleus scattering, and it is now at a place where we can really look at it as an opportunity to do beyond standard model searches. I could have picked out quite a lot of different kinds of beyond standard model physics to talk about. I'm going to talk about one particular example that is described in the paper that I show you here. And that's because this experiment is actually proposed as an expression of interest to run at ESS pretty much as soon as ESS turns on. This will run at the ESS target. And it's to look for neutral current vector NSIs. And so you're looking for these non-standard interactions in the exchange. And it turns out that this is, of course, related to the number of neutrons that you have, your sensitivity to this. And so as a result, if you run with different materials, you end up with different capability to extract these coupling constants that are associated with the non-standard interaction. So if you look at what you can do, you can look at all of these different types of materials for your detectors, and a wide range are being considered. The latest to appear actually is this argon and xenon combination that could be run there. And one would want a wide collection of these detectors, similar to what is going on at SNS right now. But you can see that this is what you can do at SNS today. And this is what you can do at ESS DAR in about 3 years of running. And if you do a comparison of the different types of a target, you can actually really narrow in on the regions that are allowed due to these NSIs. So here, for example, is the argon plus xenon allowed region. This is from a new kind of detector, which is called a high pressure gas detector. It's one that is being developed for neutrinoless double beta decay. It looks, the planned detector, which is called GANESS, is actually almost exactly the same as the next new detector that is being built right now. And so this demonstrates that this DAR program that we could get started is actually a great venue for detector development for other programs also, which I think is a very nice and interesting component of the program. So then if I skip down to the lowest of the cross sections that are opened up by decay at rest scattering, that's the electron-neutrino-electron scattering. And if you think about this, this is a lepton-lepton collider. It's a very nice type of interaction. It is one that would show up really beautifully in a high pressure gas detector, because when the neutrino hits the electron is very forward going. And so it will point directly back to the target. The physics that you get from this is similar and complementary to the kind of physics you can get at sevens. You can explore, for example, non-standard interactions, and it is with slightly different couplings than what you have for the case of sevens. So it's quite a nice program to go along with it. Then the last of the interactions that I wanted to talk about is this inverse beta decay interaction, which you see right here. And this is a very interesting interaction because not only is it a very well-known cross-section, but in this case, you can fully reconstruct the neutrino energy or the anti-neutrino energy. So inverse beta decay is anti-electron neutrinos interacting with free protons in a target and producing a positron followed by a neutron. So this kind of an interaction is what was used by the LS&D experiment and many sterile neutrino searches. And these sterile neutrino searches are all statistics limited. So I present to you here, for example, the JSNS2 planned upgrade. So this is 5 years of running a JSNS2, which was 3 JeV protons on target at 1 megawatt. And you can see that you know, at 3 sigma, it doesn't quite completely cover this allowed region. ESS can give an order of magnitude higher flux for the same size detector. And it's got almost the same signal to background rejection, even before you have the short pulse upgrade. So actually, you know, it's very promising as a place to actually run. You could have scenarios where you're actually competing with JSNS squared, because if ESS is starting, you know, in 2024, 2025, somewhere in there, you needed to actually get this one going and run it for 5 years to reach this point. And this is 5 megawatts compared to 1 megawatt. So the higher statistics will follow very quickly in the case of ESS. And also you could imagine, instead of using your power to just get things done faster and go to higher statistics that way, to simply make smaller detectors and map out the L. Okay, so these are the 3 classic interactions that everyone talks about with decay at rest experiments. I want to point out 3 more physics opportunities just to make it clear that the program is really very rich. So first of all, I want to point out that there are many other materials that are used for detectors, and most of those have cross sections that are poorly known, but they are exactly in the range when you do decay at rest studies of what you need for supernova studies. So there's big supernova programs being proposed all around the world, and these are some of the different types of detectors that are under consideration for this. And so studying and measuring these cross sections would be very, very valuable and nice first physics that could come out of a neutrino program at ESS. Also, I want to point out again that the KDAR Flux offers unique new programs. So an example for this is a program which is called K-Pipe, which is a search for muon neutrino disappearance. And what it is it's a very big pipe. It is 3 meters in diameter, so not so large across, but 120 meters long and filled with liquid scintillator and instrumented with silicon photomultipliers in hoops through the detector. And this allows you to get the nu mu coincident signal from nu mu CCQE scattering. So a nu mu comes in, the monoenergetic nu mu comes in, it interacts, it produces a muon, and that muon stops and decays in the liquid. And this allows you actually a very nice reach in nu mu disappearance, as you can see from the plot here, one that covers quite a bit of this range that has been tagged by IceCube as possibly interesting. Lastly, I want to point out that you don't have to be doing necessarily neutrino physics. You could be looking for neutral heavy leptons. You can be looking for dark photons. And again, understanding your source very, very well, like you can at a decay at rest source, is very, very valuable for that. So this brings me to the end of what I wanted to say. I think that this ESS DAR program offers some very nice features. First of all, it's interesting in timely physics. You can look for short baseline oscillations. You can study cross sections, measure dark photons. You can do BSM tests through sevens. In fact, that is almost certainly the first program that will be started within this ESS DAR program. You can make use of neutrino electron scattering and more. And ESS is a unique opportunity for those interested in decay at rest sources because it really wins on power, on energy, and on ability to also to optimize neutrino production. So if you think about what's going on at all of the other sites are coming along to spallation sources and saying, can we fit our detector in? And that actually has made it difficult to fit in detectors where people want to put them or of the size that they would like to have. But I think we could look to ESS to potentially have a neutrino campus, and that neutrino campus could have its own target, which is ready-made for decay at rest studies. And this decay at rest program is really a unique opportunity for ESS also because, as has been discussed, it will take a little while to start up ESS New SB, although we are all anxious to get it going quickly. And this is a way to start a neutrino program quickly and start gathering neutrino physicists at the site. So I see this as a real opportunity all around, and I thank you for listening to what I had to say.
Thank you very much, Janet. So this illustrates that even if while we're waiting maybe for the far detector to be finished, we can start doing physics already with the accumulator and the target station, where we will gain then a large factor in background suppression because of the short pulse that is given by the accumulator. Is this not working? Hello? Does this work? Yes. Mm-hmm. I don't know if this means that, well, in the audience you may have heard, I don't know on the web, but what I said can also is not that crucial. So I would like to open this for any questions or comments from the audience. And are there any raised hands? Okay, I don't see. So again, Janet, thank you very much for your very chatting talk.
Thank you.
So we will now proceed with our planning for other uses of the base infrastructure of ESS New SB for other projects. What Janet talks about was a first example, and we now will hear from Maja Olvegård, a colleague of mine at Uppsala University, about the low energy new storm that was already introduced by Marcus. Please, Maja, take the floor.
Can you hear me well?
Yes, we can.
Excellent.
And we see your slides.
So I will talk a little bit about the design of a low energy new storm racetrack ring. This is outside of my expertise. I actually declined to give this talk, but my no was rejected. You might imagine who has this persuasive power. But I have some help, some feedback from other people that I'm very grateful for. So this will be used, this will not give a design of a low energy new storm racetrack ring, rather some input to a future design of a low energy new storm racetrack ring. So this is a picture or a sketch of such a decay ring for a new storm facility. This particular picture was taken from the reference below for the
Something happened. Can you hear us, Maja?
Sorry?
Go on.
I do have a quite shaky internet connection for some reason. Did I fall away? Okay.
Right. Anyhow, let's just carry on.
Yes. So we have this injection section where pions are injected into this first straight section through, and it has an optical correction scheme, they call it, to inject pions stochastically, which means that you can inject while you still circulate these other muons in the ring. And of course, you then take away the pions that haven't decayed yet in the first straight section. And the injection straight section is also the production straight section. So that's the one you aim towards detector, near detector and far detector. So there are already two, well, plans or wishes to build such a new storm facility. One at Fermilab, you see here to the lower left corner, you see a little racetrack ring there. And also at CERN, I think then they take the beam from the SPS. No, wait, is it the SPS? Never mind, it's not important for us. We need low energy.
Yes, it's the SPS, yes.
Thank you. So important features, I already touched upon that. You need as short arcs as possible because you want to have long straight sections. So you get as many neutrinos as possible to your detector, of course. This means that you need strong magnets in the arcs and that you need a very compact arc lattice. As I mentioned, you can use stochastic injection, which means you need to have a dispersive section here where you can merge pions and muons of naturally different energy. Or you could, in principle, use a kicker to inject muons directly, but then you need to take care of, you need to look at the size of the ring with respect to the let's say pulse length of the muon pulse, so that you have time to rise your kicker fast enough. You need a large momentum acceptance. So you need large magnets basically, or you could use well, in principle, you need large magnets anyway. You could also use a special lattice like the fixed field alternating gradient, FFAG lattice. Then you have inherently a large momentum acceptance. You need a large emittance acceptance as well. And also there, fix that through large magnet bores. And because you have a large momentum acceptance, you need to correct chromaticity fairly well so that you don't have losses. So there are three suggestions for a lattice. One is a simple traditional photolattice, so focusing, defocusing structure. You could use then either a normal conducting or superconducting combined function magnets in the arcs. And why combined function? That means that you have a dipole and a quadrupole magnet all in one. So this is to make it compact. And why use a superconducting? Well, then you can have stronger field. But this, I'm told, this requires some R&D. There's hardly any superconducting combined function magnets out there. So this would require some R&D work. So this specific design, this photo design, has very large magnet bores. It's about 60 centimeter to be compared to LHC. I guess it's 10 centimeters. It's very large. With a photo, you can have dispersion-free straight sections, which is good. But you still, within the momentum acceptance, you get large losses at certain energies. And you also have these resonance crossings that you cannot avoid. So you have large losses also due to this. So a way to fix this is to go for the fixed field alternating gradient option. As I mentioned, then you have a large momentum acceptance automatically, you could say. But it's a complicated lattice. You also have these wriggles in the straight sections because of how it's designed. And this lowers the neutrino flux at the detector by up to 20%. Just a thought that maybe if you have a low energy muon beam, maybe this is actually less important because you anyway have a very divergent neutrino beam, you could say, from the muons. You have slightly lower losses than in the photo option, and you have a larger acceptance, but reduced pion capture efficiency due to the dispersion in the straight sections. So to combine these advantages and disadvantages, there is a hybrid lattice, which has FFAG arcs. So the special lattices and the arcs. So you get a large momentum and emittance acceptance. Then you would have photos in the straight section, so you would have no dispersion. So you would have a higher capture efficiency and a higher neutrino flux. You have slightly reduced total 60 acceptance compared to the full FFAG solution. But on the other hand, no big R&D work needed for these superconducting combined functions and magnets. Right, so where are we now? Okay, so now to the ESS-based news storm, or a low energy news storm. So what I'm thinking here is the first question to answer possibly is, would we take then pions from the special target and inject stochastically just as the other options, or could we take muons directly from the ESS NUSB targets? So this is the big study to see what would the flux be in the two cases. If we take muons directly, then we don't have to transport two species simultaneously. So maybe something that we could gain, some advantages to gain there. We will have low energy muons, that's sort of the point. So we can have, and probably should have, a smaller ring. So shorter arcs, we can have it even more compact. But we would also have a wider angle neutrino source, so we lose something there. If we have should we have fewer turns, or should we aim at similar amount of turns as the other designs? If we have less turns, we probably have less losses in total, but we probably also get lower flux control because we get mess in and we don't have so much time to control it, you could say. Just to compare the photo option with a certain FFAG option and then our ESS option. So the other two use 120 GeV protons, 100 GeV protons, whereas we would use 2.5 GeV protons. It's a very big difference. The pion energy that they target in the other designs is 5 GeV, which gives muon center momentum 3.8 GeV. We would have muons around 0.45 GeV, so that's almost a factor 10. Of course, we know nothing about our momentum and emittance acceptance, but it's quite large for the others, so it's good to aim for the same, of course, if we can. The existing designs are both around 500 meters long. We could think of something at least 60 meters, probably maximum 300 meters, which would give us 10 to 50 turns. That muons make 10 to 50 turns. But yeah, that's to be studied. Unfortunately, I have not been able to compare muon fluxes, and we of course know nothing about our muon fluxes. So let's see if yes, also I want to mention that I had some feedback from Jean-Baptiste Lagrange, who's in his thesis here below. He has actually studied a low energy news storm facility. So there's already some work done there, and I'm hoping that he can join us in our application to the EU. So thank you, that's all I have.
Thank you very much, Maya. So yeah. So these talks here at the end of the workshop are actually preparations for our future plan beyond the super beam, neutrino super beam. And so this is one of the studies that you would like to make during the next 4 years. And the talks given now are only given the starting point for these studies, of course, but you have already come some way, Maya, on this route. So thank you. Do we have any questions, comments to Maya in the hall? Or yes, we have Jean-Baptiste, please.
Yeah, thank you. Yeah, thank you, Maya, for the talk. Just one comment on for the FFA solution. The FFA solution, the arcs would be superconducting as well. So which means that R&D would be still necessary. FFAs are combined function magnets, so they would be need for R&D anyway.
Right. Yes, I forgot to stress that. Yeah. Yes, thank you.
Okay, yeah. So our study has already started even before we have obtained the funds from EU for it. And any other comment or question on the web? No? Okay, so let's thank Maya again. And we will now, I will give a presentation of another study that we would like to carry out during the next 4 years, and that we will then be requesting EU for support, design study support. And this is of upgrading the ESS USB such that we can have muon collider proton complex test facility. You have already been introduced to the ESS site and this layout, so I will proceed without further ado. So what is a muon collider proton complex? Well, this term is used in the jargon. CERN has launched, as you've heard, a muon collider design study since a year. In this, among these working groups, what is called the muon collider proton complex. Is this? This doesn't. Sorry. Is the LINAC, the accumulator, the buncher, and the combiner, and the target assembly for the muon collider, be it at 10 TeV or higher or lower energies. This section is fairly similar and independent on what energy you are finally going to collide the muons at. And the combination of very high power, 2 megawatt, to be delivered in 5 pulses per second, each pulse being about 2 nanoseconds long, and each containing of the order 510 to the 14 protons of 5 GeV. So this is the task of the muon proton complex. There are outstanding problems further down the line here that we heard from Daniel Schulte, in particular the cooling, acceleration, and the colliding of the muons, and also the detectors. All these sections are going to be studied in the muon collider study at CERN. And this is thus the first stage along this line here. Now, given that the ESS proton LINAC under construction, and that we have already made a detailed design study of this accumulator ring, by the way, under the guidance of the preceding speaker, Maya, who has led the work package in ESS USB for the design of the accumulator, which is now fairly final. And we also have been studying this LINAC, ESS LINAC upgrade to 10 megawatt, of which 5 megawatt will be H- beam, such that it can be injected in the accumulator and compressed down to 1.3 microsecond pulses. What is required is then to have another ring in which these 1.3 microsecond punches are compressed further or bunched, rotated in a phase space down to a few nanoseconds, which is required for the further cooling line here. So this has been studied before. Such a proton complex, first in the muon accelerator program, MAP program in the United States, and also at CERN, where one has made a study based on the super proton LINAC, which was a LINAC, proton LINAC, very similar to the ESS LINAC, proposed at CERN 15 years ago to be used in the LHC upgrade program, but it was then an alternative route for that was chosen. So this SPL study was stopped in 2015, but before that, there was the parameters of that design, SPL design, was used to evaluate a neutrino factory proton complex. What is required by the neutrino factory and by a muon collider is not exactly the same, but very similar. So there was a study made of the proton complex based on the SPL, which is then one of the starting points for a similar study we propose now based on the ESS LINAC, similar to the SPS. Here you see this is from a talk given by Carly, proton-driven driver considerations at Muon Collider preparatory meeting in 19, where he outlines the use of, so that you would have to have a different bunching scheme in the LINAC from what we have for the super beam. We would then inject these much shorter bunches in the ring, in the accumulator that we have. So we need to have a different scheme for chopping in the LINAC. We need to, and we're going to use different acceptance and timing for the accumulator. And then have a second ring where these bunches are phase rotated in a compressor or buncher ring called, with the end product of having 2 nanosecond bunches, each containing 10 to the order 10 to the 14, 10 to the 15 protons. So I just illustrate that this has already been studied before and thought of before. Now, when we come to the ESS LINAC, has the design parameters 2 GeV, ESS USB will upgrade it to 2.5 GeV, 5 megawatt, 14 hertz, and 10 to the 15 protons per pulse, 14 times a second. So these are parameters very similar to the SPL, which allows us to use the SPL study I mentioned as a starting point. You see here again the ESS site as it is now, with the LINAC, the target building, and the neutron detectors, and the area for ESS USB here. And you see here a recent picture of the ESS accelerator funnel as the accelerator is now being constructed. So we need to modify the pulse structure in the LINAC. We need to introduce new pulses between the proton pulses, which will be H- pulses. So the pulses in the baseline project is 3 milliseconds long, and then there's a gap of 70 milliseconds. 3 milliseconds long, 70 millisecond pulse, and we introduce then a H- pulse in the middle here, which in fact is composed of 4 sub-pulses, which will be injected in sequence to the accumulator ring and compressed to 1.3 microsecond each of them. So this design, as I said, is more or less, the conceptual design is more or less finished and will be published in our ESS USB conceptual design report by the end of the year. So this has already been covered, I think, by several speakers now. The baseline ESS and USB design study, which will be published at the end of the year. I just want to point out that the target that we are using is a titanium target. So granuli inside a tube, a canister here, and this is our focusing horn placed in this region. So titanium has a fairly low atomic number. And just might comment on the use of high and low atomic number targets, because there is the general idea that the yield of neutrinos is you only need to know the power of your accelerator. Microphone doesn't work. Thank you. Does this work? Yes. So that the yield, it does not depend on the energy of the proton beam. Primarily, it is just a function of the power of the beam. So independently of energy, you get the same yield here as function of pi momentum. But it's clear that if you have an 8 GeV beam, you need to have it twice as intensive as a 16 GeV beam. Then you will have the same power and you will have the same pion yield. So this invariance would be invalid also even up to much higher energies. But you see that the low energy of our project, 2 GeV, this invariance would not hold, would be loose. This is when you use a high A material, but we are using a low E material. The calculation here done by Paolo Sale is for carbot A13. And here you see that we do not have this invariance, and that in fact, you are gaining by going for the same power, operate at low energy to maximize the yield. So now we want then to make this complementary design study of the muon collider proton complex test facility that Marcus already discussed in the beginning here. So during this period, the 4 years to come, we would apply for resources to do a study in particular then of the what I have defined as the proton complex in order to achieve 2 nanosecond long bunches of 10 to the 15 protons using the ESS and USB accumulator already, then complemented with a buncher and a special separate target for reasons that Marcus mentioned here. This study of using the ESS has in fact already been also started, if you like, and reported by Carly in his talk here in 19, not by us, but in fact by Carlo Rubbia, who will follow my, give a presentation of my talk here. And you again see this same scheme. The number of short bunches in the accumulator may differ, but the basic scheme is the same. You need to add many names for this second ring, a buncher or rotator, because it rotates the long 1.3 microsecond long bunches in phase space such that they get shortened to 1.5 nanoseconds. So we want to make a proposal to EU for financing this study over the next 4 years to come. And Marcus already talked about this. So in particular, what kind of scheme we are going to apply for with the deadline March next year. So we need now to focus on the formulation of this program. And this workshop we have here today is to give input to this work to prepare the application. That it's important, of course, to have the support of ESS management for this. We have here a letter of support that we can then join to our application to EU from the Director General of ESS, Kevin Jones, where he writes that I was very pleased to hear of the progress that you have made in the ESS News Design Study, and I look forward to reading the conceptual design report. In due course, the second phase of your work, which we are talking about here today, is very innovative and deserves to be supported. It broadens considerably the scientific scope and impact of the proposed upgrade to the ESS linear accelerator. I encourage you to put considerable energies and expertise of your collaboration into this second phase. And on behalf of the ESS organization, I would like to reiterate our continued strong support, because we have already had very strong support for them for the ESS NUSB study. For the neutrino, and you see here, particularly, and I have underlined here, muon physics opportunities presented by the ESS NUSB initiative previously communicated to John Wormersley, the previous Director General. Kevin is acting Director General currently, and Helmut Schober will take the lead of the ESS from 1st November, and he has a copy of this letter, so it's already been discussed with him also. This is important, as Colin pointed out, we would eventually have to merge this into the ESS organization fully, not have two different projects. Neutrons and neutrinos would be one and the same with the same management. So my conclusions are that the proton complex is one of the critical parts of the muon collider project. That the study of a muon collider proton complex based on the use of the CERN 4 megawatt super proton LINAC was made in 2013 already. Important input to our study. The 5 megawatt ESS proton now under construction is similar in several respects to the SPL design that was made. And since 2018, it's carried out an EU-supported design study of a uniquely intense neutrino beam complex based on the ESS LINAC, which will result in January 22 in a conceptual design report. It's proposed to enlarge in the next 4 years the scope of the ESS NUSB design of the LINAC and the accumulator to make a design of a compressor bunch ring generating 2 nanosecond bunches or 10 to the 14, 15 protons, and of the target and focusing horn that can stand such bunches. I didn't talk much about the target, but I did mention that we not only that we can't use a mercury target, but it is also advantageous to use a low A target because it will maximize the yield of muons. Could serve as a basis for a discussion of the realization of an ESS-based muon collider proton complex test facility to be operated in the first half of the 2030s. This would be a test facility integrated then in the program of CERN for now studying a muon collider, and there will be many other test facilities for cooling, etc., acceleration. But then the proton complex test facility is uniquely suited for ESS because only at ESS in the world we will have the 5 megawatt or even just 2 megawatt that are required for these studies for CERN. The ESS proton complex could also possibly come to serve as a first stage of a facility to test muon cooling at full intensity until CERN has taken off the decision to build an SPL for a 310 or 14 TeV energy muon collider, allowing such tests to be made at CERN. Because only at ESS in the world we will have the 5 megawatt or even just 2 megawatt that are required for the okay, we've had that before. So let me explain again. So we would make a design study of this proton complex test facility during 22-25. We could then start building it 1930, around 2030, and then become a first stage test facility for the CERN program. And in and maybe even longer perspective, as the proton complex of a 125 GeV muon collider Higgs factory, a low energy muon collider at ESS that you will now hear about from Carlo Rubia in his talk following mine. So before we listen to Carlo, are there any questions to what I have been presenting in the room or on the web? Yeah.
Just a short comment. I have a fear. What you just presented is very interesting and appealing, but I have a fear that if that program for test beams and so on and so forth will be realized in some volume at ESS, so everybody will forget about the idea to send neutrinos to a mine far, far away and build their megaton water Cherenkov with detectors. So the ESS new SB will be killed by these projects. So this is my fear. I don't have answer to that.
Neither do I, but I don't share your fear maybe, but your concern in the sense that we have to calibrate this very carefully. It's clear that the ESS LINAC is world unique. It has many opportunities. We have heard before, Newstorm, KDAR, etc. And at some point, the whole thing could become so demanded by many people that it would be to the detriment of our baseline program. So we will have to calibrate this expansion very carefully. On the other hand, I think it is needed because the uniqueness of ESS LINAC in the world, it cannot be denied that it represents an enormous potential for basic fundamental high in the physics. But if we have to proceed in an orderly way, we should also admit that this is to some extent because of strategic reasons. We need to show to EU this potential, but this does not mean that we jump stages, as you point out. The first stage is the the neutrino superbeam. So thank you for this remark. Are there any other comments or questions to what I said? Otherwise, I would call on Carlo, who already has his name displayed. Can you say something, Carlo? Maybe we will see you then also.
Well, I think that you already covered most of what I think I'm supposed to say. So I don't need to repeat again what you said about the basic factors for a muon collider. So I will simply say that I agree with what you say, that this is certainly an important question which has to be followed by the system, and I will stop to that. And if somebody wants to go read the transparencies, can read the transparencies by his own pleasure to see the differences if there is any. But I don't see much of it. I thought I was supposed to talk about it, but no,
I'm only talking about the proton complex. I have not talked about the physics interest of low energy muon collider or Higgs factory. I'm not talked about the cooling required for it, the collider ring. So I think you should open your presentation and show the full spectrum of this, or the full potential of what I have only talked about the very first stage. I encourage you to do that, Carlo, to give your talk.
Well, I don't know. I can repeat what I said, but it's most of the thing is already you already covered.
I didn't say anything about the importance, the usefulness of a Higgs factory, a muon collider Higgs factory.
Yeah, well, 10 TV, you collider, you don't know what to do with it. I mean, never mind that. I mean, okay. So if you want, I can go through those transparencies, but I say, déjà vu.
I agree. I said I covered some of what you have, and you can skip that, but there is a lot more material in your slides than I covered. Please go ahead, Carlo.
So where is my presentation?
Okay.
You should
upload that. You can't do that. Wait, just a moment, Carlo. Yeah. So Carlo does not have control. No, I have control. Yes. Right. Yes. I have control of your slides. So, but you see them, don't you? You see your first slide now, Carlo.
Yes, but I'd like to follow them. I'd like to give a presentation.
Yeah. So you just say next slide, and I will switch. Okay. Say next slide, and I will switch it. Okay. Please go ahead.
Well, I don't know really how to do it. Actually, this is not a PowerPoint. I asked for a PowerPoint version. This is not a PowerPoint.
This is what was uploaded to us.
Well, I don't know. Well, anyway, I don't know what to say. Where are you going now?
So here, please start your talk here. The muon collider as an optimal alternative.
Yeah, this is what I'm saying. It's a I'm pointing it out that the muon practically is an important reasonable station of the ES accelerator program, as you already said. So we can go to the next picture then. Muon cooling, the question of muon cooling is described here. Here's the summary of the process on muon cooling. There are two possibilities to do that for protons and for mu plus mu minus pairs. And most of this thing has been done in the past history by the people working on the proton pairs. Next transparency, please. Comparing the mu plus mu minus H resonance, since the H0 resonance is a scalar particle, obviously the muon pair is winning over the electron pairs. You can see in the numbers, 71 picobarn mu plus mu minus cross sections, and the electron minus the cross sections are 0.15 femtobarn. So therefore, you can see from the situation that in fact the muons are the winner because the electron pairs are not allowed because of the wrong helicity of the two of the beam. Next transparency, please. Here is the picture which you already taken up and you already described, so I don't have to describe it again. The future muon mu plus mu alternatives, I say there are two possibilities of muon alternatives in my point of view. One on the H0 mass, and the second one at a higher collider energy, somewhere between 0.5 to 1 TeV, to study other X-related process in these particular cases. And I believe that this thing can be certainly successfully used by ESS. I suggest also the use of the ESS as discussed already by you. Next transparency. Here is a Techland's case in which you produce at the mass of 125.5 GeV the Higgs muon, the two channels indicated here, the W plus W minus star process and the BBBA process. You can see the cross section. You can see the signals are very nice and very clear. So there is a very good chance to do these measurements in both channels. The high energy situation is somewhat more complicated. It's shown here. There are various alternatives indicated in this picture, which also indicate that this is possible. Single Higgs production and multiple Higgs productions. Now, next, You're jumping fast. So the summary of the setup for DSS is already summarized here. As you said, high intensity H- source, a pi proton mu decay channels. I've chosen energy under 220 MeV/C, a robust mu plus radiation cooling system, and then you recirculate the LIDAC to be muons to the required energy where collision are taking place. And then you have a collider ring, which has two forms, one at the rings in mass, and the other one in the sub-TV range with the cross luminosity also indicated. Now, the required ES process intensity is directly related to a relatively short muon lifetime. Next picture, please. Okay, this is a copy of the picture you already shown. There's exactly the same picture. It was taken from Fala. This has also been already described by you, and it is completely identical to the one which I show here, so I don't have to repeat myself. Next picture. Here is the cooling process as it comes out together. You can see the two cooling processes have two aspects. One is the first linear transverse cooling, then there is a ring cooling, and then there is a possibility of parametric resonance cooling as a last case. You can see from this graph here that the difference is between the two possibilities. The resonance cooling, if possible, in which the elliptical motion is becoming hyperbolic, can be added another factor 10 to the reduction of the emittance and therefore increase the luminosity. Next picture. Okay, now this is a description of the parametric resonance, as I said, is performed in such a way that instead of operating in left, the ordinary oscillations, in right, hyperbolic motion induced by perturbation via the half-integral resonance or the Betterton frequency. The two choices are indicated here in detail. Next picture. Now, this shows the overall gain of introducing a peak. You can see from this curve down here, down below, that the peak introduces about a factor 10 more rate for a given condition, so experiment, so it increases the luminosity by factor 10. Next picture. And now, batch acceleration, it's also very obvious. It's already described by you. It's you inject the mu plus and mu minus into a ring in which you bidirectional structure of 200 meters, followed by Neufeld in 1913. And in this way, you collect the events into a final stage of 62 PGV, mu plus, mu minuses for the resonance analysis. Thank you. Next picture. Here is the picture of the storage ring, shows how the distribution is now the collision point with beta star equal to B plus B, X BY equal to 5 centimeters, which is a reasonable figure. Again, it is already published by Ackenbrand in 1999. Next. So conclusion, high luminosity ESS is indicated here, is the numbers are here. Summarized, indicated that the basic formula can be used in order to detect those events. And if the new novel parametric resonance cooling is successful, the cross-section is reduced by a factor of 10. And we collect, in this case, 1.2 10 to the 5 events per year per interaction point. Next picture. Okay, estimated performance is summarized about the peak cooling. You can see only the number down below here. The number X particle with peak is something like 10 to the 5, 1.2 10 to the 5 events per year. Next picture. Okay, this is a problem of the background-related questions. Using muons instead of electrons induces the fact that muons decay to electrons, and this produces a decay. So there is a background which can be produced. So you can see here the picture of the detector. You can see that the question is to eliminate the background coming from the that can be done as adding some shielding. It is, excuse me. This is an open problem which I think one has to consider more carefully. It's not obvious to me that you can in fact reduce the electron background to a value which is acceptable. It has to be dissolved. Some people have done some test calculations, some backgrounds. They seem to be willing to the predictions, but still has to be done. So it is a really clearly big open problem. Next picture, please. Okay, so this is a summary, and indicates here the possibility that before going ahead in making the ESS factory, it is worthwhile to introduce some kind of intermediate realization to the small ring between 20 and 40 meters circumference in order to achieve the theoretically expected longitudinal transverse emittance of asymptotically cooled muon. So I can see double two-step process. The first process is an initial cooling experiment, and the second process is the realization of the actual factory DSS. Next picture, please. Here is how the initial cooling is represented here. You can see the numbers. You see it's a small ring. You can see the parameters which are indicated in the table here. Next picture, please. Okay, so conclusion. The Higgs production colliders have a lot of advantages. Large cross sections, 41 picobar in external resonance and 0.2 picobar at the 500 GeV. Small size footprints, it may fit within existing ESS site. No synchrotron radiation and Bernstein problems. Precise measurement of the line shape and decay width. Exquisite measurement of the whole channels to test the standard model. The cost of the facility, and this is my own estimate, provided cooling can be successful, is less than 1/10 of the value of the LHC. Challenges are also very important. A low-cost demonstration of the muon cooling has to be done first, so we have to have a early cooling experiment before. Muon in 2D and 3D cooling needs to be fully demonstrated, and this is something, of course, is the purpose of the operation. 3.3 needs ultimately very small center of mass energy spread, 0.03%. And this is a which is required. Constant muon decay are important, which has to be understood. And the final significant R&D required towards end-to-end design. Thank you very much.
And thank you, Carlo, to illuminate our conference with this talk, this very far-reaching and interesting project. So do we have any comments or questions to Carlo in the audience or on the web? I see Marcos. Please, Marcos.
Yes, for this, for the ionization cooling ring, this small ring, is there any place in the world where we can test this technique?
What? I couldn't hear your word. Can you repeat them?
For the ionization cooling ring with the lithium absorbers, is there already any place in the world where we can test this, the feasibility of this technique?
No, yes, the whole thing has to be set up. In my view, while the ESS is the primary place for the final detector, the initial detector can be done in many places. It could be done at CERN, it could be done at Zurich, it could be done in England, it could be done in the United States, it can be anywhere, because this first initial cooling experiment is a tiny little rings of 20 meters circumference, which can be put together very easily. But this is necessary in order to understand more clearly, experimentally, the results of the cooling. Because much theoretical work was done in the past years, but very little experimental activities. So the experimental activities can start with a small ring to be done anywhere, very quickly somewhere. And then once this is proven, you have to proceed to the final system. DSS, in my view, is the only place where you can do it.
Yeah, so I think this program, which has started at CERN now, the science study of a high energy muon collider, will contain cooling experiments, and the cooling experiments are relevant for any energy collider in the end. So, and the CERN program invites also other European labs to join in, and is in fact focusing on the cooling problem rather than on the proton complex program that I was discussing in my talk. So in that sense, it's complementary. Although I must say that when it comes to the proton complex problem with the compressor ring, there has been, going through the literature, there is very little concrete designs of a compressor buncher ring. So that is a study which needs to be done, but it's clear that the cooling is the, so to say, the most ambitious research R&D program that has to be carried out, and that there is quite some momentum now generated by CERN to look into this, as we heard from Schulte yesterday evening.
There is another problem which is associated with the possibility to use the peak.
Yeah.
Whether we have to operate the ring in the standard mode or near resonance mode.
So within the CERN study, this peak is being mentioned as a very challenging, but very interesting possibility. So even that is being addressed within the CERN study. And we are part of the CERN study. I am in fact co-convener of the proton complex working group within the CERN Muon Collider design study. Any other comments or questions? If not, let's thank Carlo for joining us, and let's thank all speakers this morning. For me, this has been a enlightening exercise. We are now going to sit down and write up all this in a future project plan. So thank you also for your participation in this ISNU SB workshop, which I herewith close. Thank you.
And I would like also to especially thank Tord and Marcos for organizing this workshop inside the conference, because I think this was we are very proud of having hosted this.
Thank you very much.
Hello, can people online hear me?
Hello, yes, yeah, we can.
Hello, ciao, hi Davide. So I leave you the floor for convening the session. Please.
Okay, thank you. Thank you, Walter. So we start the session dedicated to detectors. That is actually the first plenary session at Nufact about this topic. So yeah, we will go through PMT developments, future near detectors, and also novel element detectors. So we start with Christoph Bronner. So can you please share your slides?
Yes. So can you hear me?
Yeah, very well.
Okay, so I should be sharing my screen now. Okay, can you see the slides?
Not yet.
Okay, so let me try again. Okay, is it better this time?
Yeah, perfect. Thank you.
Okay, so let me start. Then, yeah, first of all, thank you for the invitation and this occasion to present here the development of PMT for the Hypercamioconde experiment. This experiment was already introduced yesterday in a dedicated talk, and it will be the next generation water Cherenkov experiment in Japan that will continue the program carried on by the current Supercamioconde NT2K experiments, studying in particular neutrinos from different sources, both for the study of oscillations and astrophysics, as well as searches from new physics through things like proton decay and dark matter searches. And one of the key limitations of the current Supercamioconde NT2K experiments is the statistics that they have. So one of the key ideas for Hypercamioconde is to have a larger detector to have more physical mass and so increase the statistics like this, as well as for where it's possible, like for accelerator neutrinos, increase also the flux of incoming neutrinos. Oops, sorry. And so we will be building a detector, as you can see on this picture, that looks very much like the current Supercamioconde cylindrical water Cherenkov detector with a linear detector here equipped with photomultiplier tube, where the events will be reconstructed, and an outer detector to veto outside events. But of course, the main difference is it's much bigger than the current Supercamioconde with a fiducial mass that will be about 8.4 times the size of the current Supercamioconde. But also the Hypercamioconde project is not just about statistics. There are also a number of other improvements for precision. In particular, there will be for the control of systematics, there will be more important at higher statistics, an additional intermediate detector, and also improved photo sensor. That is what I'm going to focus on in this presentation. But to explain a bit the developments of the PMTs for Hypercamioconde, it's useful to say a few words about all events are reconstructing a water Cherenkov detector using PMTs. Essentially, such a detector will be able to see charged particles that have high enough momentum to emit Cherenkov light and photons. And that kind of particle will appear on the wall of the detector as a ring pattern, as you can see here, that is detected by the PMTs, and we extract information on the events from those patterns. In particular, we can do PID from the sharpness of the edges of the ring and separate between showing events, rings that you can see an example here with fuzzy edges that would be either electrons or photons, and more sharp ring that would be non-showing category and be muons or charged pions. We can also go back to the vertex position, so the position at which the particle was created, by trying to minimize the spread of the what we call the timing residuals that you can see here. That is essentially the difference between the time of arrival of a photon and the time of flight from a given position on the detector. So essentially, the true origin point of the particle is the position that's minimized the spread between the time it would take to go to this the PMT and the actual time at which the hit was recorded. The momentum of the particle would be essentially deduced from the charge that is deposited in a certain region of the detector, essentially a cone around the direction of the particle. And additionally, we also have this outer detector, this external cylinder that we use to veto possible entering background. And for events, we ask, as you can see here on the outer detector event display, that there's essentially no activity in the outer detector compatible with an entering particle. And in hyperchemical so there's this very large detector that we'll refer to as the FAR detector that has a PMT. But as I said, we also have a new intermediate detector called the intermediate water Cherenkov detector that will be presented in a dedicated talk later. But this is also a water Cherenkov detector, and so instrumented with PMTs. In this case, it's actually multi-PMTs. You can see an example here. That's actually several small 3 inches PMT in a pressure vessel, a bit similar to what can be seen in chemistry.net and IceCube experiments. And for the FAR detector, so it's separate between the inner and outer detector. The inner detector here, we're going to target high photo coverage, so 40% photo coverage, and half of it is provided by the Japanese group in the experiments in the form of 20 inches PMTs that you can see here. But this inner detector will also likely to be equipped with multi-PMTs, although with slightly different constraint than this intermediate detector. The outer detector use much smaller PMT, will be 3-inch PMTs, but with extra devices like wavelength checking plates and reflective material on the walls to be able to collect more light. So you can see for the FAR detector, the PMTs between inner and outer detector are very different. And this is essentially because what we're trying to do in both cases is very different. So what the important characteristics are quite different as well. For the inner detectors, we try to reconstruct the event as precisely as possible. So we're going interested in characteristic that allow to maximize what I was presenting a few slides ago. In particular, better timing resolution allows us to be able to reduce the spread of the timing distribution for vertex reconstruction. For charge resolution, we want to be able to estimate as precisely as possible the amount of light that arrives in the given region of the detector. The better the granularity, the more we'll be able to judge how sharp the edges are, and that will improve our PID. And we also have additional requirements for the low energy physics. Here, we want to be able to, of course, detect as much as the light as possible to be able to lower the threshold and also reconstruct low energy events that emit a relatively low number of photons. And we also want to be able to identify neutrons from their capture on hydrogen, and that requires a low dark rate. So all this reason actually optimize an efficient 20-inch PMTs complemented by some multi-PMTs is quite good. For the outer detector, it's completely different. We're not trying to reconstruct event, but just V2 events that could be entering particles from outside the detector. And this is based on identifying a cluster of PMT8s that could correspond to an entry point of an outside particles. And for this, it's actually interesting to maximize the number of PMTs to have as much units that can be above or below threshold and to identify such an entry point. We also want, of course, to collect as much light as possible to be able to not miss an entering particle or be going there. But because this time we're not interested in timing resolution so much, we can use extra devices for light collections that give more light at the cost of degrading the timing resolution, like wavelength shielding plants or reflective material on the walls that allows to detect the photon after a few reflections. And so for this, using smaller PMTs with those extra wavelength checking plates and reflective material is quite interesting and cost efficient. So starting with the 20-inch PMTs, I will go through the different elements for Hyper-K. So we had 3 candidate models that were considered for Hyper-K. All of them are so-called high quantum efficiency PMTs. That is to say that for the first part of the process where the photons has to get converted into an electron, they are more efficient than basically the PMT in superchemical. And where they really differ is in the second phase of the process where this electron gets amplified to produce a signal that can be detected for the electronics. The first model considered that looked quite interesting was the so-called hybrid PMT, where an avalanche diode is used for the amplification. And it looked very interesting at the beginning as it's quite simple as design. So there was some people that allow to reduce the cost. And also this system has a very good resolution, both for timing and charge. However, in practice, a number of problems appeared. In particular, it requires a preamplifier. That turned out to be quite difficult to design, and also it would be quite complicated to mass produce those hybrid PMTs. So, despite those attractive features, we abandoned those hybrid PMTs as an option for Hyper-K, and ended up for the 20-inch PMTs, considering mainly 2 models. First one I refer to as the box and 9 PMT is produced by Mamatsu, and it's actually an evolution of what is used in Super Kamiokande, while the other one that we referred to as MCP PMT used microchannel plate for amplification and is produced by a Chinese company called NNVT. First, the box and line PMT, I said it's essentially an evolution of what is used in Super Kamiokande. Outside of the higher quantum efficiency, it has a different shape for the diode. It will use a box and line diode here instead of Venetian blind diode as used in Super K. And that's actually a number of nice features. First, that this box is quite wide, so that it's very unlikely that the electrons would miss this first diode, as could happen with Venetian blind diode. And so the detection efficiency is increased. And at the same time, also with this line setup, the electrons have much more uniform drift path, and that gives better timing and charge resolution than what was seen in Super Kamiokande. And we've actually confirmed those improvements in performance in tests in the lab when combining the improved quantum efficiency and detection and collection efficiency. We found for the box and line PMT in blue here about twice the detection efficiency of the Super Kamiokande PMT in black. We've also seen twice as good charge resolution and more than twice as good timing resolution, as can be seen. And those were tests done in the lab, but we've also done tests inside a real detector, as there was an opportunity with the refurbishment of the Super Kamiokande detector in the summer of 2018. And at this occasion, in an agreement between the two collaboration, box and line PMTs were used to replace the PMTs that are stopped functioning properly in Super Kamiokande. And we purchased 140 box and line PMTs for this purpose and tested all of them prior to installation with the setup that is seen here to confirm that they satisfied all the criteria to be installed in the detector, and they all passed the test. And that also gave us a first view of the consistency of production quality in a larger production. As you can see here, for timing resolution and charge resolution, the production was quite consistent. And in the end, 136 box and line PMT was installed in Super Kamiokande, which give us information on the performance in the real detector and also over time stability data. And in terms of what was seen in the detector, so that's the result of the calibration campaign in Super K in 2019, where you see in red for the box and line PMT and in blue for the normal Super Kamiokande PMT, what was measured in terms of detection efficiency, charge resolution, and timing resolution. And here again, we see the same kind of improvement that was seen outside of the lab. The only difference is that the timing resolution is only twice as good as normal Super K PMT, which is already quite nice, but we're seeing something better outside of the detector. And at this point, we're not totally sure where this is coming from, but we believe it's more due to something either from the way the measurement is done or the environment in Super K, rather than really the performance of the PMT degrading. And another things that we tested on this first large batch of PMTs we purchased was how the performance of the PMT varied as a function of the position at which a photon hit on the surface. That could matter for the reconstruction, and also as a function of the remaining magnetic field, as we cannot never really cancel just magnetic field in the detector as beta as hyper K, and that affects the performance of the photon multiplier. So in terms of performance as a function of the position on the surface of the PMT, we found that they were quite uniform, except when you get on the very edges of the PMT where you see some degradation, and also around this region that corresponds to the box diode, the performance are a bit worse here, but overall still acceptable. In terms of magnetic field, the effect of a remaining magnetic field actually turned out to depend strongly on the position at which photon hits on the surface. There's almost no effect at the center, and starts to have bigger effect essentially when you're away from the center in a direction perpendicular to the magnetic field. And again, we see the biggest drop in performance or variation in performance around this box region. That's the example shown in red here. That's a very localized region, and everywhere else, the effect is rather small and well within what we require for hyper K. So here again, those box and line PMT satisfy the requirement. Now, the second candidate we looked at for the 20-inch PMT in hyper K was what I call the MCP PMT developed by NVT. They were originally developed for the Juno experiment and have a number of nice features. In particular, they also have quite good detection efficiency, but they also have low after pulse compared to the box and line PMT. They are quite strong and can, and in terms of pressure tolerance, which is important for an experiment as deep as Hyper-K, and also quite clean glass with low, in particular, radioisotope contamination. However, what matters for Juno was a bit different than what matters for Hyper-K. In particular, the timing resolution and dark rate is not so important for Juno, whereas it's very important for us. And so the model developed for Juno couldn't be used as is for Hyper-Kamiokande, but NNVT has found some way to improve this by adding some focusing electrodes. You can see here, they managed to improve quite significantly the timing resolution and to make it better than what is in the Super Kamiokande PMT, although not as good as the box 9 PMT, but still acceptable for water Chenkov experiments. And yeah, this improvement was quite successful, and actually those improved PMT are used in the cosmic ray experiment in China called LASSO, which ordered more than 2,000 of those. And so we tested quite extensively this improved PMT for Hyper-K. Don't have time to go in detail, but we tested the performance also for a large number of them, both pressure tolerance, long-term stability, and also practical things like how much the material of the PMT could degrade the transparency of the water. And we iterate many times with NNVT along the process. And in the end, found that those were quite good PMT, and they satisfied most of the Hyper-K requirements, but there were still some points we're a bit worried about. In particular, although the dark rate could be reduced considerably, it was still above our target of 4 kilohertz. And it was not totally sure whether those PMT would be able to handle the very high rate that we expect in case of a nearby supernova explosion. So as a result, for the Japanese contribution, we decided to use the box 9 PMT by Hamamatsu, although this MCP PMT option is still available for additional PMTs by other groups outside of Japan. And since the PMT were installed in Super Kamiokande in 2018, there's actually been still additional developments on those box 9 PMT. In particular, there were a number of improvements for the purity of the glass that allows to reduce the impurities in terms of radioisotope that are background for the energy physics. You can see here the comparison between the Super K PMT, the initial box 9 PMT that was installed in Super K, and where we are now with a significant reduction. And what is also interesting is it improved the transparency, and we can know for the current box 9 PMT we're receiving in red, be able to detect light on a broader range of wavelengths than where with the PMTs in blue that were installed in Super K. There were additional background reduction with also reducing the radon content in the cables. That is another background for low energy physics. And finally, Hamamatsu continued working on reducing the dark rate to achieve our 4 kilohertz target. And so in the end, those PMT nodes satisfy all our requirements. And as I said, we decided to go for this option for the Japanese contribution, and the mass production of 20,000 of such PMTs are started. And actually, we already received the first of them at the end of last year. And at the current point, we already have received more than 1,500 of them. For the first initial PMT, we went into an extensive program of quality checking and checked about 800 of them, both visually, as you can see here, inspecting the glass and waterproofing as well, any possible defect inside, testing the signal and others. And we didn't find any major problems there, but sent feedback on a number of items to Hamamatsu, which led to a number of modification and improvements in the production. And we're now preparing for setup. You can see here, we have like dark room with temperature control that will allow us to test more in details the performance of a fraction of the PMTs. We expect to be able to test 16 PMTs at a time there in those dark rooms. And the last item for the 20-inch PMT is the anti-implosion covers. As Hyper-Kamiokande is quite deep, the pressure is very strong. And one risk in those conditions is if one of the PMT was to break, the pressure wave that would be created could trigger a chain implosion and would lose all the PMT underwater. And to mitigate this, as in Super Kamiokande, we are using protective covers, and we've been designing new models compared to Super K, both because they need to resist to stronger pressure, but also to try to have a bit less background, produce a bit less background than the Super Kamiokande covers. And we have 3 such designs that you can see here, and that we actually validate through implosion test underwater. You have the schematics here. Basically, the cover tested is put in the center with the PMT inside, and we have 4 non-protected PMTs around. We trigger the implosion of the PMT inside and see whether, thanks to the cover, the other 4 PMTs are destroyed or not, and the cover passes, the PMTs are not destroyed, of course. And for cover design to be validated, we require it to pass the test successfully 3 times under 80-meter depth. And we're planning the next iteration of those tests at the end of this year, and we'll come to a decision about the cover for hyperchiasis based on the results. So after the 20-inch PMTs, moving back to the multi-PMT, as a sorry, reminder, this is where we used 19 small syringe PMTs in a pressure vessel, and that will be used for the intermediate water chunk of detector, as well as in the far detector in complement of 20-inch PMTs. The main interest of those multi-PMTs is they provide high granularity. You can see an example here of expected event display for the intermediate water chunk of detector. You see the different spots corresponding to the different syringe PMTs, whereas with 20-inch PMT, we just have 1 spot for each of those big rings. And so we hope that it will help improve reconstruction, particularly near the walls. But another interesting feature is the syringe PMTs being smaller. They have also a better timing resolution than 20-inch PMTs, which helps improve the vertex resolution. You have an example here in terms of vertex resolution. So comparing first what happens with 20% coverage from 50-inch PMTs, 20-inch PMTs. If you double the number of 20-inch PMTs, you improve the vertex resolution. But what is interesting is if instead of doubling the number of 20-inch PMT, you put multi-PMTs and still only 20% photo coverage with the 20-inch PMTs, you still get better vertex resolution that keeps increasing with the number of multi-PMT used. And finally, those multi-PMT will also be useful for calibration. In terms of design, so it's 19 syringe PMT inside the pressure vessel, and that makes an all-inclusive modules that have both the PMTs, but also the high voltage power supply and the electronics. The current design is shown here. Used for the transparent parts, an acrylic with the PMT couples to it using optical gel. And we are now considering assembly methods with 2 alternatives being considered that differ essentially on whether the gel is coupled to the PMT before assembly or after they've been put in the vessel. And there's also a number of ongoing tests for the candidate syringe PMTs there. Now going back to the auto detector, so as a quick reminder here, the auto detector main goal is to reject background that would be from entering particles from outside the detector would go into the inner detector. And it does so by using 10,000 syringe PMTs that are looking outward, and also with the help of wavelength shifting plates and reflective materials on the walls to increase the light collection. And so tests are ongoing for the different elements here, both the PMTs, wavelength shifting plates, and reflective material. For the syringe PMTs compared to a 20-inch PMT in interest, there's a much bigger market, so much larger number of model available, and we've been testing a number of them. And in particular, the 4 that are shown on this slide here were found to satisfy requirements, both in terms of gain as function of high voltage, resolution for timing and charge, and low enough dark rate. So all of them could be used for the final detector. We also been testing the different elements for the increased light collection. So first, the wavelength shifting plates where different model were testing using that kind of setup, where you measure as a function of the position at which the light is injected in the wavelength shifting plates the efficiency to detect the photon using this setup. We've also been looking at different reflective material that are Tyvek actually, and we found that of course the reflectivity would change from one type of Tyvek to another one, but also interestingly that it would increase with the number of layers of Tyvek used and vary as a function of all the different layers would be attached together. It's of course more expensive to use more layer of Tyvek. That could still be interesting as an optimization study has shown. So here to try to optimize the light collection efficiency of the auto detector, simulation were run assuming different size for the wavelength shifting plates and different reflectivity for the reflective Tyvek that would be put on the wall. And in terms of photon detected, as expected, the bigger the wavelength shifting plates and the higher the Tyvek reflectivity, the more photons are detected. But what gets really interesting is when you look in terms of value per money, it's actually seems always interesting to try to increase the Tyvek reflectivity. But for the size of the wavelength shifting plates, there's seems to be an optimal around 30 centimeters. And so the baseline design for the other detector is to be in this optimal area that maximizes the amount of photon detected per dollar, essentially, which means using 30 centimeter plates with high reflectivity Tyvek, more than 90% reflectivity. And the last line is just my summary. So the Hypercamera Conde will be equipped with a new improved photo sensor. For the Japanese contribution for the inner detector, which be 20% photo coverage, we have selected the Hamamatsu R12860, also called Boxer 9 PMT, which has very good performance with double the collection efficiency, twice as good charge resolution, and more than twice as good timing resolution than the PMT that currently equips Hypercamera Conde. The mass production of those new PMT has started, and we started getting them delivered, and it will continue until 2026. And in addition to those 20-inch PMT, we'll be using multi-PMTs for higher granularity and directional information in the inner detector, whereas the outer detector that is used to veto entering background uses smaller 3-inch PMT with additional wavelength shifting plate and reflective material on the wall to increase the light collection in a cost-efficient way. So, yeah, thank you for your attention.
Thank you, Christoph. Perfect timing. Is there any question? I don't see raised hands. So just a quick question about the outer detector. So you have a wavelength shifter and the Tyvek. So I imagine that reduces the, let's say, the spatial resolution, the reconstruction resolution, right? But that's not what you need for the outer detector, right? You just need to see a lot of light.
Yeah, exactly. So usually you want to, what you really want to say is whether there's a cluster of it around where the particle could have entered. So following the trajectory of a particle reconstructed in the inner detector. So yeah, as you don't really try to reconstruct, what is really important is whether the particle passed here and there. If you get, a few dozen nanosecond later events, that's still fine.
Okay. Any other question?
Yes.
So you have been talking about Venetian blind tubes, box dino tubes, and microchannel plates tubes, and
yes,
Hyper-K has chosen box dino. Could you say something about the relative pricing of these three types in mass production?
I'm afraid not. So yeah, so I don't actually know whether the Venetian blind that is the one that was used in SuperK. I don't know if it's actually still produced or not. No, this one is the one we went for production, but actually data of the contracts are confidential, so I cannot really say much more there.
You don't know which is the cheapest one, so or most expensive one?
My impression was that prices were not that different, but a lot of things can change in. I mean, between the options we consider, that are
okay. So they are similar, you say, and I
mean, like when you order a lot and there's negotiation and so on, so the price you actually get might turn out to be different.
It's a difficult question. I agree. It depends on many parameters. But can you also just say why would you use multi-PM tubes in the outer detector? You don't need granularity there.
Oh, sorry, we don't use them in the outer detector. So I don't know if you can see it there, but it's not exactly the same. So KM3net
at the end of your talk, you were talking about multi-PM tubes in the outer detector. No?
No, we don't have it in the auto detector. So basically it's like this.
You showed the last few slides, and this is early in your talk. The end.
So yeah, so this is the intermediate water shrink of the detector.
No, further down, towards the end of your talk. Yeah, no, that's too far. Yeah, go up 3 slides.
Here, I only have 2 slides on multi-PMT, actually, only those 2 slides. This doesn't have any.
Here, 8-inch outer detector from. Sorry, no, I misunderstood apparently. Sorry, thank you.
Okay.
In the room. No, okay, please go ahead.
Yeah, thank you. So I think we spent the time for questions. Thank you, Christoph. We can go to the next talk. He will is reporting about future near detectors.
Hi, good morning. Yeah, just give me one moment. Sorry, I will
no problem.
share my screen here. And here we are. Okay, can everyone see that? And can everyone hear me?
Yeah, perfect. Thank you.
Okay, well, I'd like to thank the organizers for this opportunity to talk about near detectors. I would say it's bright and early in San Francisco, but in fact, it is still dark, and it just reminds me that I would much have liked to have joined everyone in Cagliari, and I'm sorry that I cannot. So I'd just like to start with a bit of an overview. I will focus on conventional accelerator long baseline experiments, which I think is okay for this physics. I think for this conference. Similar cost considerations apply to other neutrino oscillation experiments, but obviously, depending on experiment energy ranges and signatures differ significantly. So a lot of the practical details will differ. And it's just a reminder that near detectors by construction have to be considered in the context of the overall experiment that it is serving. Another point is that we are sort of, depending on how you count, I would say in the third generation of such long baseline experiments, starting from experiments like KDK and MINOS and moving on to TDK and NOVA that are the current generation. And obviously in each generation, the goals have become more ambitious. And so moving from a discovery phase of various channels of oscillation, we've gone through several phases of precision measurement. And then I say several phases because as long as I've been in this career, in this field, we always say that we're in the precision era, but we move to more and more precision. But in the next generation, or even currently, we're looking to see new effects in oscillations that we haven't seen before, namely things like CP symmetry violation and the impact of the mass ordering on the matter effects. And that requires control over all oscillation parameters. So not surprisingly, control over systematic uncertainties become increasingly more demanding. It's always a crucial part of the experiment, but in every step, we have to do better than the previous generation. And so that means we have to learn as much as possible from the previous experience and confront new issues arising from our more increasingly ambitious goals. So just as a background, so what is a long baseline oscillation experiment with a conventional beam? We produce an order GeV, sign-selected muon neutrino or muon antineutrino beam via pion decay. So these are typically intercepted by a near detector at order a kilometer from the target before oscillation effects take place. And these are the detectors we'll be focusing on. And so it's conveniently labeled, generically labeled particle detector in this diagram. And then, some hundreds or thousands of kilometers away, we observe the same neutrinos again, same flux of neutrinos again at the far detector where enough time has elapsed for oscillations. So what does it take to be competitive in this game? Current and future oscillation experiments require something like a megawatt of proton beam, requires something like 10 to 100 kilotons of far detectable target mass, and something like 10 years of operation. And so in addition to just getting the statistics to do this physics, it requires systematic control at the percent level. And that's where the near detector comes in. And I'll say more about that in the coming slides. So in terms of what we observe in the near detector, we can just sort of follow the physics of what happens. This quantity N beta of E reconstructed. So that's what that's supposed to represent is a number of a particular neutrino flavor we observe through charge current interactions at the far detector as a function of some observable, let's say, the reconstructed energy. And if we follow what the physics does, we produce a flux of neutrinos in a given initial flavor. The oscillation physics takes place and therefore provides a flavor change that depends on the neutrino energy, the oscillation parameters, and typically a fixed baseline over which the neutrinos propagate. There's a cross section for the neutrinos to interact in that new flavor through various channels, as that depends on the neutrino energy, and a detector response that also depends on the channel and the neutrino energy. And then all these things are then integrated over the neutrino flux to give us what we observe at the FAR detector. And so then comparing these two predictions, the prediction as a function of oscillation parameters to the observed observation as the FAR detector, that gives us, that allows us to extract the oscillation probability and therefore the oscillation parameters. So one thing I'd like to mention here is that in this, what I would call a measurement era, predicting and modeling the signal is just as important as predicting the background. And so getting the signal modeling right is what allows us fundamentally to also get the oscillation probability and therefore to observe the new effects that we want to do, whether it's a CP violation or precision measurement of a certain parameter. So in terms of what kind of uncertainties that we are trying to achieve, I think anyone who's in this business knows that the systematic uncertainties are very complicated, but nonetheless, I think it's sort of an interesting exercise to get a very rough sense of what's needed. And so if we consider sort of the case of observing CP violation, at the first oscillation maximum, the swing in oscillation probability from nu mu to nu e is at most 30%. And due to the spectrum and backgrounds and other things, the observed nu mu to nu e rate varies by at most something like 20% in our experiments. And so that means for a definitive observation of 5 sigma, let's say, of maximal CP violation, we would need to have total uncertainties, that's statistical and systematic, to be something like less than 4%. And that implies that the systematic uncertainty should be hopefully smaller than that. And one should know that is sort of what I would call the first, it's beyond sort of the current capabilities of the current experiments, but would sort of define maybe one of the initial goals of the next generation of experiments. And so further goals where we try to have sensitivity to CP violation over a larger range of delta CP parameters and non-maximal CP violation or precision measurements in delta CP would actually require even better systematics. And so that pushes us down into the few percent level. Now, obviously, the numbers, I put some numbers up here, and maybe I'm a bit daring in doing so. These numbers depend on the underlying parameter values. You have spectrum information that can be extracted. It's not just a counting experiment. There are potential cancellations that occur when you consider asymmetries between neutrino versus anti-neutrino oscillations and so on and so forth. Obviously, it's complicated, but nonetheless, I think just to get a visceral sense of what kind of uncertainties we're targeting, this is a useful thing to keep in mind. So one of the obvious point is that in this discussion about what we're trying to observe, we are talking about what we're observing in the FAR detector. And so I think it's useful to remind ourselves that the NIR detector exists in an ecosystem where it's addressing systematic uncertainties in the FAR detector. And so what's happening at the FAR detector is designed, how we make measurements is a crucial aspect of how we design the NIR detector. And so if we try to address these uncertainties, well, it's interesting that they have kind of different things, right? That the flux of neutrinos, for example, is largely independent of the FAR detector. It's produced by a neutrino beam, and whatever detector you choose to put at the far end, the neutrino flux is the same. Some of these depend on the basic features of the FAR detector. And so, for example, the cross-section, if you were to measure in a NIR detector, you would want to match the same target nuclei so that you observe the same nuclear effects. And then some of these things very much depend on the details of the FAR detector, like the response that we have with the FAR detector to these interactions. One further note is that the neutrino energy plays a special role, since it is, once you fix a baseline, what is driving neutrino oscillations, and it is basically the argument of that probability. And so, yeah, the observable versus true neutrino spectrum must be accurately understood in order to predict the signal correctly. So that gives rise to some conflicting considerations. So if we want to somehow address the systematics associated with the response of the FAR detector, it requires that the NIR detector should be similar, at least similar, and in fact, as similar as possible to the FAR detector. And that allows us to provide opportunities for cancellation and systematic uncertainties, where we can assume things like efficiencies and background rates could be similar between the NIR and FAR detector, and systematics there could cancel. But just practical considerations mean that the NIR detector and the FAR detector can't actually be identical. For example, the NIR detector must be much smaller in size than the FAR detector, typically because of hall size constraints. And that size itself impacts the performance of the detector and its response. Furthermore, the NIR detector operating very close to the neutrino source, and now very intense neutrino sources, have to operate in a very high rate environment in a way that the FAR detector, at least in the context of a long baseline experiment, does not have to do. Finally, in terms of detector optimization, FAR detectors have some compromises made in in order to allow them to scale to kiloton scale detectors. And so, for example, we have so far given up on the opportunity, for example, to magnetize a far detector. But then for a near detector, where we're talking about much smaller detector systems, it's not clear whether you should accept those compromises are necessary. And if you can produce a detector that can tell you more, then why wouldn't you do that? And so there's sort of these two conflicting things that I'll try to address. And you can sort of see the different strategies here. In the case of the NOVA experiment, you see these quote unquote functionally identical detectors that are at the near and the far site. In the case of the TDK experiment, you see a near detector that is very different from the far detector. And in some sense, they are capturing these different elements of what we're trying to achieve in the near detector. So if we try to address each of the elements that are involved in the prediction that we're trying to make, so I'd like to talk first about the neutrino flux. And so what I call the ab initio prediction of the neutrino flux, that is basically sort of a Monte Carlo simulation that allows us to predict what the neutrino flux is with various external inputs, has really improved tremendously since the beginning of the long baseline era. And I remember, maybe even a decade ago or so, some people considered this to be actually an intractable problem. And now we've gotten to a point where something like 10% or even better uncertainty can be achieved by this method. And that's thanks to hadron production experiments like NA61 SHINE, as well as improved simulation frameworks and analysis techniques enabled to some extent by more computing power that's available to us. And likewise, because we have this fundamental understanding of the beam, the relationship between the flux in the near detector and the far detector is nominally also better understood than sort of the absolute flux at either detector. However, the uncertainties are still larger than desired, and obviously in a neutrino beam, there will be differences between what we're simulating and then the neutrino beam that we actually build, particularly once we consider operations. And so the ability to actually directly measure the near fluxes in the near detector is very much a desirable property. And in fact, it was a kind of a new element that we're trying to introduce in next generation experiments. And that implies using channels or event signatures where the cross sections are very well understood. These could be leptonic interactions or purely leptonic interactions like the elastic scattering or the low nu method. We further also have to understand the flavor content in the beam. And each of these things, basically there is an opportunity for a detector that may be different from the far detector. And in some sense, obviously, identifying these very rare leptonic channels requires an extremely capable detector. And so this is one of those cases where optimizations or capabilities beyond what you have in the far detector can be important or in fact necessary to do this at all. A related question to the neutrino flux is the beam monitoring. I think we all know that megawatt neutrino beams that we're operating now and in the future are extremely volatile environments, and we can have variations that take the form of a slow, sort of tolerable creep to just outright failure of the beam. And so both from the purposes of efficient operation and also systematics, it is really important that we be able to detect in short order, like I would say on the order of a day, potential variations at the percent level. And that means that we need to have a near detector system with a large target mass to quickly assess the rates and profiles and spectrum of the neutrinos that we're observing. And also, I'll come back to why I say this, an on-axis deployment, which optimizes the rate and spectral sensitivity. And then separately, the detector has to be stable over a very long period so that we can sort of see that in some sense a standard candle that can be monitored over the lifetime of the experiment. Just as a comment, we also have auxiliary beam monitors like muon monitors behind this hadron absorber. These are also very important, but I do not think that they can replace direct monitoring of the beam through neutrinos as has been done in the current generations of experiments, and I think we can look forward to that in the future as well. So in terms of the cross sections, the modeling of neutrino nucleus interactions is potentially, I think, the most challenging aspect right now for the long baseline program. It's not necessarily the largest nominal uncertainty, but I think the physics here is very difficult. And over the past decade, we made significant progress in understanding the situation, and so for example, these modeling of pionless charge current final states, we made a big advance in. But then, when we look at sort of take our models and apply them to similar processes like electron scattering, we still see quite significant discrepancies. And at least personally, I'm still worried whether we are converging on the right physics within our generators. And so for me, this is a particularly precarious situation for future measurements, whether from the current experiments or future experiments, and where there is these large uncertainties which are not particularly well defined. And I think that's always a situation that makes us worry when it comes to systematic uncertainties. So in terms of the detector response, I think one of the challenges compared to, let's say, our colleagues in the collider fields is that the neutrino and nucleus interactions really offer very few well-defined calibration or control samples. And so, people working in colliders, we have BABA scattering, we have mu pair production, J size, K shorts, Z's, and whatnot, where in some sense we a priori know what the answer should be, and we can use things like tag and probe techniques, calibrate on mass peaks and things like that. And there are very few of those things that neutrino interactions provide us. We can have pi0 decays, we have MIPS, we have the Michel endpoint spectrum. And furthermore, in the FAR detector, this is compounded by the relatively low statistics that we will have just by the virtue of the experiment being at a long baseline. And so we do have quite a heavy reliance on getting the detector simulation correct and then have with limited cross-check. And furthermore, because of the requirements of target mass, whether we use water or carbon or liquid argon, the dense medium of the FAR detector means that we have significant secondary interaction effects, particularly hadronic interactions, where we always have challenges in modeling such things. And so furthermore, there is also this coupling between the underlying neutrino interaction and its response. And so there's a bit of a chicken and egg problem here, where things like the efficiencies and the resolutions for a given observable, let's say the reconstructed neutrino energy, both depend on the underlying reaction mechanism, where, for example, the relationship between the incoming neutrino energy and the outgoing kinematics of the particles, but also the kinematic distribution of the outgoing particles, where the detectors will have various detection and identification thresholds, different resolutions, potential for re-interactions, and all these things affect the response of the detector. And so in some sense, we have to deal with both of these issues, the modeling of the neutrino interaction itself and the response to the detector simultaneously. And that in itself is a challenge. And in my view, it is essential that we study these things in a near detector in a way that can be robustly translated to the FAR detector. And so unlike the flux situation, this suggests that the near detector should be functionally similar or identical to the FAR detector so that you can observe the same issues and address them in a near detector with high statistics. So just as a case study, I think everyone's quite familiar with this. A decade or so ago, we had this puzzle of a mini boon of this new charge current pionless states, which was well explained by a change in the form factor by the dipole parameterization. And so the underlying physics of that, the implications of that is that we have a large increase in the quasi-elastic cross-section and the hardening of the interactions. But then I think immediately people were not quite satisfied with that explanation. And people like Marco Martini and others pointed to overlooked multi-nucleon effects, which introduce a topologically new, similar process with inherently different kinematics, where the neutrino interaction implications for the neutrino energy reconstruction is actually different. And so the interpretation, the original interpretation and this new interpretation gives us very different results, which would actually be quite disastrous for the physics goals that we have now if we were to overlook this issue. So the lessons are that we always have surprises, that even rather basic nuclear physics and other issues can be overlooked. It's not sufficient just to achieve agreement in your detector observables. There can be degeneracies which impact your predicted FAR detector distributions and therefore would bias your oscillation parameter measurements. And not only that means that the near detectors must have a sufficient capability to resolve these degeneracies that may arise. And then that once again suggests that the near detector should be capable as possible, whatever you have for the FAR detector. So just coming back, so once again, I sort of highlighted these conflicting requirements. On the one hand, we want to have something that's very similar to the FAR detector, so we can study things like the response with high statistic neutrino interactions. And so that's driving us to a near detector that is similar as possible to the FAR detector. But then there are things like very specialized measurements like leptonic channels, where we're trying to measure neutrino flux, details of neutrino interaction modeling that we're trying to study in a near detector. And that's pointing us to try to have as much capability as possible in a near detector as possible. And so the obvious solution is not to try to do all this with one detector, but that we can have some subsystem specialization that take one or more of these tasks as part of an overall strategy. So one further thing I wanted to mention, a new tool that we have is what we call PRISM. And this is just based on the fact that the neutrino beam spectra changes as one moves off axis from the beam center. And so you can sort of see this both in the case of the TDK neutrino beam line, the spectrum here, that the bottom is what you observe on axis. And as you go to 1, 2, 3, and 4 degree off axis, the spectrum becomes narrower and lower in energy. And that's the same situation as we have here at Dune. And so there's the opportunity to basically have a detector which actually can sample these different spectra and have an independent handle on the neutrino energy spectrum that allows us to, on the one hand, resolve degeneracies and more elaborate applications of this technique, actually try to directly predict the FAR detector observables as a function of the oscillation parameters, thanks to the additional handle on the neutrino energy. So here are some of the developing concepts in terms of TDK and Hyper-K. We have an on-axis beam monitor in the form of Ingrid, which you see here, and which is served very well through TDK and ensuring the beam stability. Furthermore, we have the ND280 off-axis spectrometer, which is operating with a 0.2 Tesla field and has a simulated tracker, a time projection chamber, an ecal, and nuance system to study neutrino interactions. And so once again, you can see the contrast of the capabilities there in relation to the water Cherenkov detector that's used as the FAR detector. And in addition, there are additional upgrades, a new 3D simulated tracking system with these wide-angle TPCs, which improve the overall acceptance of the measurements. And then finally, coming back to the functionally identical part, as Christoph just mentioned, we have a water Cherenkov detector, which in fact would also be able to execute this prism movement over around 50 meters. Moving on to Dune, we have once again a subset of detectors which is functionally similar to the FAR detector, liquid argon TPCs, what we call ND-LAR. And these have a design that's optimized for the high rate, in particular modular design, along with a pixel readout that allows us 3D charge response, which we think is important for the high pileup that we expect at this detector. And then we also have a gaseous argon TPC where we have much lower thresholds relative to the liquid argon, as well as a magnetized reconstruction that gives us capabilities beyond what we see from the liquid argon detector. Now, these two detector systems can now move up to 30 meters off axis to exploit this prism technique. And given that, we also have a detector which is a dedicated on-axis beam spectrum monitor here called SAND, based on the Chloe Manning plus ecal, which also has an inner tracking system, including liquid argon target. I'm going to skip this slide. So I just wanted to start closing up here since I'm running out of time. So once again, the primary purpose of the near detector is to reduce systematics in a long baseline experiment. And the near detector is not the only way to do this. And so we shouldn't lose sight of some of the other things which occur, like the hadron production and scattering experiments, which will allow us to continue to improve our understanding of the neutrino beam. There's a test beams at things like the certain neutrino platform, which allow us to improve our understanding of the detector response. And then the theory itself of neutrino nucleus interactions. And just keeping in mind that billions of whatever currency you like are at stake over for this program, I think an investment here is very wise and will give us more robust results in a richer science program. I also like to encourage people to continue to think about the future, whether it's a second oscillation maximum, new forms of neutrino beams, and from there, we will have to start thinking about near detectors again. And so let me come to the conclusion. As long as I've been in this field has been in the golden age, and I think that continues to be true. And I think experimentally, we're in a very exciting place where relatively mature experiments, TDK and NOVA, are moving towards their ultimate goals, even as we roll out a new generation of experiments. And obviously, we have a very difficult situation in terms of the systematics, but nonetheless, one that I think is a challenge that we should gladly accept. And that being said, I think with the future relatively clear, we should continue to think about how this experimental program continues and optimize it for future discovery. So so thank you very much again to the organizers, and particularly given the difficult organizational state we still remain in given the COVID pandemic. So I'll stop there.
Thank you, Iro. Very nice talk. I see raised hand, so by Emilio. Yeah.
Okay. This could be a very naive question. I apologize in advance, but you say that the near detector should be functionally very similar to the far detector. However, I could think to a difference that usually the near detector is much smaller. So is like the scalability could be a problem in the systematic error, in the response, etc. Could this be a problem? How big?
Right. So if I understand correctly, in some sense, yes, there is a. If we look at the FAR detectors, typically the reconstruction of a neutrino interaction in the FAR detector, whether it's super K, hyper K, or NOVA or DUNE, that does rely on the containment of the interaction, right? And so you want to see all the bits of the neutrino alkaline particles within the detector, and if you have a muon or something which punches through out the detector, that results in an incomplete reconstruction. And so that actually does imply what I would say a sort of a minimum size to the near detector for its functionally identical component, where you want to at least contain the hadronic system in such a way that you can observe it in the same way as you would do in the FAR detector. And so, yes, I think there is an issue there. Practically, there is a limit on how small you can make the near detector. And in the end, I think that size is not set by the statistics given by given the very intense neutrino beams we have, but rather this containment issue. Now, separately, the muon is something that's actually very difficult to contain in the typical scales that we are considering in a near detector hall. And so we have to find a way to, we often have to find a separate way to reconstruct those muons, usually through magnetic spectrometry rather than ranging them out as we would typically do in the FAR detector. And so that's sort of a bit of an exception to that situation.
Okay, thanks. Just to clarify, I was thinking more like, for example, as far as I know, liquid scintillator, you could have an issue of, a reduction of the light while the photons are traveling through and so these could be very different if you have a Juno detector or a smaller detector. So I was thinking also to something like this, but as far as I understand, there is no such a problem in this kind of near detector, right?
Oh no, I didn't say there was no such problem. Yes, they're all, every kind of detector has a scaling issue. Light attenuation in fiber is one thing. Propagation of Cherenkov light in water is also another. The drifting of electrons in liquid argon, over 1 meter or 2 meters or however many meters are things which will make the near detector and the far detector different. And so to me, this sort of returns to the point where, these things have to be fundamentally very well understood and modeled correctly. And so, I would not say that that's not an issue, but one where I think we do have methods and handles, but we will have to work very hard to make sure those systematics are under control.
Okay, thanks.
Actually, I do have a question. So you mentioned the flux measurement, and which is something that future experiments are focusing quite a lot, actually. Do you see them a way to further reduce this overall systematic uncertainty, which is not easy because it's already quite low, or a way to validate the modeling and make sure that there are no mistakes?
Yeah, I would say it's a little bit of both, right? Davide, as you know, in TDK, we do start with the neutrino flux model, and in some sense, on a high level, we verify it, but then we put it into a fit, and then basically we improve the same model. I tend to, maybe just out of force of habit, think of it in the same way. On the one hand, with high enough, let's say, lepton scattering, we can control the overall normalization to, I don't know, a few percent, which I think is considerably better than you can do with existing ab initio constraints. But at the same time, you are relying on all the near far constraints that are coming out of the model, and so this measurement by itself is not sufficient for the experiment, right? You are still relying on the modeling of the beam. You need to verify it through the measurement, but then having verified it, you are still relying on the covariances between the near and the far detector in order to bring the systematics to a level where you can achieve the goals of the next generation of experiments. That's my view.
Yeah, I agree. Yeah, I think I think we went through all the time. Thanks, Iro, for the nice work.
Thank you for having me.
And thank you. Thanks a lot. So we go to the last talk of this session by Filippo about noble element detectors.
Hello, can you hear me?
Yeah, hello, Filippo.
Hi. Do you see my screen?
Yeah, I can see. Yeah, perfect.
So let me start thanking the organizers for the invitation. The title that was given to me is spreads quite large topics. So a disclaimer first. This overview may not be complete because of lack of time and because of lack of knowledge, and I apologize if things should be presented or not. Please let me know. And then I'm biased on the topic, and I try to be unbiased with this presentation. So it is divided into two sections, this presentation. The first one is the characterization of the noble elements as detecting media, and the second one is an overview of detectors using this kind of liquids or gases. So noble elements, they're also called rare gases. They are nonetheless relatively abundant. Argon, for instance, is the third most abundant gas in the atmosphere. They are gas at room temperature and liquid at cryogenic temperatures. You see them here, except the last one, which is synthetic, and the second last one, radon, which has no stable isotopes. The other ones are stable. Well, there are isotopes which are stables. They are chemically inert. They are typically simple to treat and clean. They are all bright scintillators. They are not conductive material with high dielectric strength, and ionized gases or liquids can allow electrons to drift. So here's some properties. From the left to right, it's the lighter to the heavier. Not much to add here, except that the liquid, so the cryogenic temperature at which they become a liquid and solid, it is increasing as a function of the atomic mass. So how the energy is transferred to these gases or liquids? Well, through ionization and excitation. And ionization means creating electrons and ion pairs. If nothing happens through recombination, we will have atoms which are excited, and excitation gives rise to scintillation, light, and heat. While ionization, if we are able to separate electrons from ions, we have quasi-free charges, quasi-free in liquid, free charges in the gas. Excitation can quite rarely give rise to free charges, though there are pending mixtures where the excitation of the main gas, for instance, argon, has a higher ionization energy, excitation energy than the ionization energy of the less abundant gas. So ionization is also possible exciting argon or xenon. So once the if the ionization, how to avoid ionization to recombine completely? Well, in the presence of an electric field, a fraction of the generated initially electrons and ion pairs do not recombine, but they can drift apart. Charge recombination is of two kinds. It's a geminal recombination when the electrons recombine with the parent ion, and it is typically very fast, depends on the electric field. And then there is the volumetric recombination when the electrons do not recombine with the parent ion. It is typically slower, and it depends on the electric field, but it also depends on the ionization density. So per energy released, the charge collected applying an electric field depends both on the electric field and the linear energy transfer that showed in this plot, being R, the recombination factor. And you see that as a function of the electric field, the charge starts from 0 and then it goes saturating. Electrons drift into liquids and in gases with velocities which depends, of course, on the electric field. And in liquids are typically slower than 5 millimeters per microsecond. A typical electric field used in TPCs. And in gases, instead, they can be significantly faster, though in general, noble gases, they are not known to be gases that allow drift very fast. Typically, to allow drift faster, some complex molecule like CO2 or CF4 are doped in small quantities. For what concerns ions, depending on the state, gas or liquids or solid, and the pressure, they are typically slower from a factor of 10 to the 3 to a factor of 10 to the 5 with respect to the electrons. This is typically not of a concern except if there is a large rate of primary ionization charge, and if the drift length is very big. If this happens, ion space charge can actually induce distortion of the electric fields, as we will see later. What happens when electrons reaches liquid to vapor interface, for instance, in liquid detectors? This is valid for sure in liquid argon and in liquid xenon. Well, they can be extracted but under the influence of a strong enough electric field. There are typically two components. One is extracted fairly fast, and one which takes some microseconds, and the time at which it is extracted depends on the electric field. The point is that 100% of the charge, electron charge drifting, can be extracted. And this is a fundamental feature for all the dual phase detector types, typically using argon and xenon, and used for extensively in direct matter search experiments. If the charge is not separated from the ion with the electric field, then it recombines and gives rise to scintillation. Scintillation is also produced by excited atoms. So the process is schematically shown in fairly simplified way with this cartoon. charged particle interacts with the noble element, and it can either ionize it or excite it. The ionized or excited state will interact with a neutral atom, forming a dimer, either an excited or ionized dimer. The ionized dimer can then recombine with an electron and then fall into a state of excited dimer that can be on a singlet state and a triplet state, and this relax to the ground state, emitting a UV photon. The slow component is the triplet state, and here I mention the lifetimes for the triplet components for liquid nitrogen, liquid argon, liquid xenon. The decay times in gases are slower. For instance, in argon vapor, it exceeds 3.5 microseconds. Now, there is an interesting features which is true in particular for liquid argon. Singlet and triplet states are populated in different ways. So the population depends, if you want, on the linear energy transfer, so to some extent to the dx. Okay, so this is a way to identify particles. The spectra, they are all in the VUV. The hardest one is helium, obviously, and then towards the visible, not extremely UV is the xenon. In this plot, neon was not plotted, but it's roughly in the same position as the helium scintillation. And another nice feature is that since the model, simplified model that I described before, is valid both for argon and liquid, and actually also solid, the spectrum, emission spectrum, is very similar for all the three states, as shown for argon as an example in the picture here on the right. Are there additional mechanisms to create scintillations in the gases? There is the primary scintillation, which is what I just described, and there is electroluminescence, which is when free electrons drift in gas, and this is valid only in gas. And they gain energy from the electric field enough to ionize neutral atoms, but not enough to ionize them. So the light production increases linearly with the electric field and with the electron path, and it is inversely proportional to the gas density, number density. And it is very simple to achieve in pure noble gases. This is fundamental for all the, it's a feature which is fundamental for all the dual phase detectors which use S2 signals. In the gas, avalanches can also be generated, so charge can be actually amplified into dedicated structure by means of controlled electric field, and in this case, simply the energy gained by the electron is sufficiently to ionize atoms when the electron interacts with the neutral atoms around. So as a light and charge, since the model I described briefly before are they must be anticorrelated, right? If I create an electron, if I separate an electron from an ion, I will not have a photon. And this is actually true. You can see from this plot that the function of the electric field, the charge increases while the scintillation light decreases. And this is true on an event-by-event basis as well. And this feature is used to increase the energy resolution of liquid xenon TPCs in particular of this kind. I will skip this slide, but if you're interested, we can come back later. So the contaminations affecting the light, there are different ways to quench the light. One is, for instance, adding nitrogen on or CF4. The medium can become no longer transparent, as shown in this slide. So 10 ppm of gas of nitrogen in liquid argon reduce the absorption length of scintillation photons to 6 meters. This is another way to quench the scintillation. It is during the production. Molecules like water, methane, oxygen, nitrogen, and so on, they can actually interact with the dimer before they excite, emitting the photon, and the excitation follows a non-radiative path. As an effect, the photon is lost. The effect depends clearly on the concentration of the dopants, and it is more probable for the long-lived dimers, the ones which they excite after a long time, as seen in this picture. So effectively, the scintillation light of the liquid argon in this case goes from 1.6 microsecond slow component here, adding 10 ppm of xenon, it is effectively reduced. Another form of quenching the scintillation light of argon, for instance, but it's actually an efficient wavelength shifter. It's adding, instead of nitrogen, xenon, because the addition of xenon enables the following processes. So argon dimer colliding with the xenon forms an argon xenon dimer, and then again to form a xenon dimer, which then de-excite on the wavelength of the xenon, which is 175, 178 nanometer. And here you can see actually how the scintillation spectrum changes the more xenon is added. Of course, the fast component of the liquid argon scintillator is not really affected, because the singlet de-excites fast enough so that the dimmer cannot interact with the xenon atom before being de-excited. And there are contaminants which actually affects the drift as well. It is a minor concern for gas detectors, a big concern for the liquids. The electronegative impurities, they actually trap electrons, forming negative ions, which drift significantly slower, from 1000 to 10 to the 5 times slower. And as a result, the signal is lost because the current is too small to be read out. So in large TPCs, liquid argon or liquid xenon TPCs, one needs to have a sub-ppb level oxygen equivalent impurities. And here you can see that an impurity of nitrogen for what concerns the drifting electrons is definitely less problematic than an impurity of oxygen, which is less problematic than impurities of SF6, which is the most electronegative molecule in this plot. For helium and neon, this is less of a problem, because the impurities, since they are helium and neon are colder, they tend to freeze out on the walls of the detector. And in the case of the neon, anyway, they can be filtered with the cryotraps. One feature of xenon is that water has high solubility in liquid xenon. So if most likely the issue on liquid xenon detectors, if there are issues of purity, is water. So this brings me to the overview of the detectors. I tried to find detectors for each element. I found one beautiful helium-based detector, which is the only one that actually exploits heat. There are bubble chambers, xenon and argon-based bubble chambers, mostly used for direct matter search experiments. But there is a presentation this afternoon about the argon bubble chamber. So Heron is a proposed experiments to maybe outdated, to use superfluid helium at 20 to 30 millikelvin. And the idea is that protons, which are the low energy elementary excitation of superfluid helium, like phonons, will actually travel through the liquid helium to the liquid argon, to the liquid helium surface, and they will evaporate a liquid helium atom, which then can be detected by a silicon wafer, which is a few millimeters installed above the liquid helium surface. And here you see actually the detector, a prototype working. And since liquid helium scintillates as well, the same detector can measure the scintillation light, which is gives the T0, and then the roton signal arrives several hundreds of microseconds afterwards. Here you see the spectrum from a source, and here you see the temperature measured on the wafer. Beautiful. About neon, well, neon-based is CLEAN, which is a proposed neutrino, electron and neutrino nucleus scattering detector. Back in 2005, the medium liquid neon as a scintillator, only the scintillator. Neon, why neon? Because it has no long-lived isotopes and no internal background. It can be cleaned very effectively using cryogenic traps, since almost anything will be frozen on those cryogenic traps, but not liquid helium and liquid neon. So the detector consists of, it's 10 meters in diameter. It has a primary shielding of water, which can possibly be active, and then a not-instrumental layer of liquid neon, and the active volume is seen by 2,000 photomultipliers looking at the helium, liquid neon, and with the scintillation light being wavelength shifted with a solid wavelength shifter on windows in front of the PMTs. And then the diffusionization is done from the spatial distribution of the detected light. There are prototypes, microclean, which operated in liquid argon and liquid neon. And then mini clean, which is compatible with the liquid neon, liquid argon. It is actually a direct matter search experiment, but for the moment operated only with the liquid argon, and it is installed at Snow Lab. So xenon-based detectors, they are used for neutrinoless double beta decay, and both high-pressure gas TPCs and liquid xenon TPCs are used for this scope. Xenon is known and scalable technology. It allows particle identification with charge-to-light ratio. It's very good self-shielding for at least middle to low energy photons, gammas. It has a decent energy resolution. It is simple to enrich, in the sense that in the world it exists more than 1 ton of enriched xenon. And then there is the possibility of tagging the daughter of barium. So low background and superparticle identification capabilities are and extreme energy resolution are key characteristics of this kind of detectors, because they must detect a full energy peak at the end of the neutrino less double beta decay spectrum, as shown here. So next is next program is developing a technology of high pressure xenon gas temperature reduction chamber with luminescent amplification. The goal is to build a detector which is 100 kilograms enriched xenon installed in Canfranc underground laboratory. And it's a staged development. Next, there are ongoing R&D started from next DBDMB, and then now in operation there is next white, which is 10 kilograms operated at Laboratorio Subterraneo de Canfranc. And here you see the demonstration of extremely good energy resolution of this detector. This detector is TPC, which works in this way. The scintillation light, prompt scintillation light is measured for T0. The secondary scintillation light, after the electrons are drifted into this area of high electric field, generate the electroluminescence, which is read out from silicon PM plane for the event topology, and from the photomultiplier tube for the measurement of the energy. The topology of double beta decay is a track with the two buds at the end, the two Bragg peaks where the electron stops. And the actual 100 kilograms next TPC is something which looks like this. It's 1.3 times 1 meter in diameter, 1.3 meters in length. EXO is the other detector using xenon, but it uses xenon in liquid form. It is installed underground in the waste isolation pilot plant in New Mexico. It runs since 2011. It had 2 physics runs. The TPC is, as shown in this picture, is 30 centimeter long and about 30 centimeter in diameter. There's a transparent mesh which is a cathode in the middle, and 2 sets of strips, wires read out for so the scintillation light is read out by large area avalanche photodiode installed behind the wire planes. Here you see beautiful pictures of the assembly of the TPC, and actually the fact that the anti-correlation of scintillation and ionization charge is used to improve the energy calibration. So argon-based detectors, they are very well represented in this workshop. So gas-based detectors are suitable as near detectors, near detector for T2K upgrade, and the dune near detector, which is magnetized and movable, as we just heard. And there will be other 2 presentations. Liquid-based TPCs comes in 2 fashions: single phase and dual phase. Single phase, we have Icarus, Microboon, SPND, the dune near detector, dune vertical drift single phase, dune horizontal drift single phase, and the prototypes, which are proto-dune single phase at CERN. And for what concerns dual phase, we have the charge. The dual phase version can be read out the charge, where charge is actually amplified. and the detector is the Dune vertical drift dual phase. And the prototype here at CERN, the proto-Dune dual phase. And if the light is read out, there is Ariadne, and then a number of direct dark matter search experiments, which can also be used to detect neutrinos, and there will be actually a talk this afternoon. So I will not review all of these, but for a recent nice review, I suggest this link. So Icarus was the technique of the liquid argon series was proposed in 1977 by Professor Carlo Rubbia, and a long-running R&D framework culminated with the production and operation of the Icarus T600, which was operated in Pavia in 2001, and then it was brought at the Laboratorio Nazionale Gran Sasso in 2004, where it was exposed to the CNGS neutrino beam. Then it was refurbished in 2016 and 17 at CERN, and presently is used as a FAR detector for the short baseline neutrino program at Fermilab. Here you see the Icarus being refurbished. It is 2 independent modules. Each module has 2 TPCs because the cathode is in the middle. Here you see the photomultipliers tube behind the wire planes, which are 3 wire planes at 0 and ±6 degrees. And then here you see the cathode. This strip length is 1.5 meter. The nominal voltage is 75 kilovolt. And here you see recent event display recorded at the NUMI and the BNB neutrino beams. These are neutrino, muon neutrino candidates, and they were shown yesterday by and the talk of Bonesino.
Sorry, I don't think we have much time left.
I'm finishing.
Yeah, thank you.
So there are 3 for what concerns Dune. We have three kind of detector types are envisaged. So the baseline technology for the Dune fire detector module 1 is a single phase horizontal drift, which is in each module there are 4 TPCs and 3.6 meter of drift, 180 kilovolt of applied voltage, and the anode planes are actually called APAs, which are modular devices, 2.3 meter wide and 6 meter tall, one installed on top of the other, and there are 75 doublets of APA. The electronics is installed on the APA, so it's not accessible. Then there is the vertical drift dual phase, which was developed to reduce the channel count and allow longer drift. The drift is vertical, 12 meters of drift. Electrons are extracted from the liquid to the vapor phase, undergo multiplication into the large electron multiplier, and it is read out by anode. And this great large electron multiplier anode is called CRP. Here it was tested in full scale at proto-Dune dual phase. And then the offspring of the of these 2 previously technologies is the so-called vertical drift single phase, which the CRPs are installed on top and on the bottom. They are all immersed in the liquid argon. The cathode is in the middle. So 6.5 meter of drift and a nominal voltage of 300 kilovolt. So all this is prototyped at CERN at the neutrino platform, where there are 2 liquid argon temperature exchange chambers, each one of 750 ton, which are the largest liquid argon temperature exchange chambers ever operated. And phase 1 was completed last year. when protoneum single phase and dual phase were tested for the first time. Phase 2 begins next year, where protoneum single phase and dual phase will be operated again. And here, just some results from protoneum single phase 1, which was exposed to a charged particle beam, and the developments for the vertical drift single phase. This, I will skip the summary. I'm ready for questions.
Thank you, Filippo. And yeah, we have time just for one quick question. Yeah, yes, I see Adi. Yeah.
Yes, thank you very much for this beautiful overview and very informative. I was wondering about the ratio between the two dimers and the prompt and delayed light. We're used to seeing that as a way to distinguish between particles. I was wondering if it was already investigated in different electric field and for different energies of the incoming particle that is causing this entire process.
Yes, to some extent. Yes, to some extent. Well, always order of few MeVs, below few MeVs. There is, it works fairly well with the liquid argon. It's much more complicated with the liquid xenon because, at least because the two components, the decay time of the two components is very similar. While for the liquid argon is 6 nanoseconds and 1.6 microseconds. And yes, it happens that highly ionizing particles like alpha particles or nuclear recoils, they tend to populate more the singlet state. They are faster.
And so was it investigated for different energies of those particles? Like alpha?
Yeah, typically energies of alphas to some hundreds of keV, not above.
Okay, thank you.
Okay, thank you, Filippo. I think we need to close now the session. Thanks a lot for the nice talk. And I think we close the session now, and now there is the break. And I think, please organizer, correct me if I'm wrong, we will reconvene in about 10 minutes, maybe.
Thank you, Davide. I think we can give some little more break. So let's reconvene at 2:40. So in 15 minutes. Okay. We need the time to grab a coffee. So 15 minutes is minimum. So 2:40 p.m. We reconvene.
Okay. Thanks to the speaker.
Adi, are you online?
Yes.
So at 2:40, you start, regardless of what happens here.
Perfect.
Okay.
And then when should we end? Like an hour and a half afterwards?
Well, the time that is needed. I mean, I wouldn't be okay. So, but okay. At 2:40, you start. Otherwise, we get too late.
Okay, no problem.
Okay. Okay. Thank you.
He proposed this technique of, at the same time, he was proposing the people to put out no price. 45 years after, the same detector is still being actively used in quantum physics, and is the basis for this man, however possible, is a deep. It's outstanding, and I remember this. I think we should not count against what I say. Yeah, I think you are, because I think we lack respect. He is kind of a dragon. He is uncontrolled. But you know that, and at 87 years of age, still being able, to propose. And I remember talking about carbon epsilon and the P-Barty collider in that at that time, 1977. He was driving these to long term.
But the story is not finished. Today, in the local newspaper, there was an article about the conference, and the title said, "Physical neutrino, not regional."
Yeah.
Yeah. Because it is known because we founded the CRS4, which is a research center owned by the about informatics, software simulation, and that was maybe 30 years ago. Then, okay, but it was the founder. So again,
extremely fertile. Extremely fertile. I mean, I think he's really the greatest physicist of our time. And I would, however disturbing he may be, and mistakes he did with the discovery, etc. Okay. Yeah. Well, he was self-directed. He started LHC development. Oh, it's I think people are in general skeptical to him. Okay, because he is really difficult to deal with, but you cannot deny his outstanding science in our field.
In realtà alla società devo chiamare però quel giorno c'era spesso adesso non si montare queste cose e loro avrebbero dovuto vedere Sì, anche perché appunto il discorso è che dobbiamo che apportazione, quindi devo mandare che non legge. Sì, c'è la macchina per le dove ci metti? Ancora un po'. Lo spazio più o meno può essere. Altrimenti quando girano vicino così doppio attacco meglio così comunque dai aspetta trovo che è un'altra cosa quello di costo ho segnato qui primo ACD che è SS4 24 che l'audio più webcam che è l'idea no? E quindi qui sono sì, no, se mi ci sta comunicando. Vedete, c'è da chiedere di altro. Sai che ci sta comunicando ancora con questo senti. No, poi diciamo che è relativamente tranquillo. Qui tutto a posto? Questo, sì. Sempre così a intuizione. Bisogna andare a cercare se ci sono relazioni. Sì, ma anche perché non è che avete tanta lista di ospiti. Altro che tu devi parlare in inglese. Quello degli altri figli. No, vabbè, non credo che non rispondono tutti e due. Certo, io però non ho vediamo. Adesso mi fermo.
Hello, everyone. I see that the room is pretty empty. We'll give them half a minute. Maybe we'll just start.
Do you know if we're running on time or are we a little bit late?
Yeah, I'll be sure to stop the talks. Okay, but I think we're going to start because we're running a bit late. So welcome to the second plenary session dealing with neutrino interactions. I'm very pleased in order to present Jorge Morfin to talk about shallow and deep inelastic scattering. Jorge, are you with us?
Yes, I'm with you. Let me just share my screen.
Okay, so I'll give you 5 minutes before you can know.
All right, 1 second, please. Let me try and get this into my full screen. It's not disappearing.
I think it's fine. We can see it properly.
No, that's all right. It's just waiting for the. There we go. All right. So, hello, everyone. I'm pleased to be able to present some of our knowledge of shallow and deep inelastic scattering with neutrinos. It is a very big topic. So I refer you for details to the review that Sajjad Attar and I published recently on the SIS and DIS channels. And also to
George, sorry to interrupt you, but can you show your face if possible?
Yeah, 1 second. I'll have to go back and start the video.
Oh, thanks a lot.
Very good. Yeah, thank you for reminding me. So I remind you that there are 2 very good workshops covering this topic. The NewStack workshop on SIS and DIS and the NewStack workshop on buy-in production. So let's just jump into it. There we go. Let me get this out of the way. Very good. So the overall SIS and DIS landscape versus the effective mass of the hadronic system has been presented by Christoph Bronner several times. The last time was in 2018. And it shows you here what the 3 major generators predict for the event distribution. And we should also recall that the Gibu generator, it's not really a generator, but the Gibu calculation should also be included when comparing this. But as you can see, there is a considerable amount of disagreement on what's happening in this area here. Let's go directly to define, get that there. Okay, we'll use that. What we define as the DIS, there's the community definition of W greater than 2 and Q squared greater than 1 GeV squared. Note that even in the DIS, according to the landscapes that you're seeing here, there's considerable disagreement between the generators. But I hasten to point out that true DIS also has a Q squared greater than 1 GeV squared restriction, and that's not in the landscape that we're looking at. And that Q squared less than 1 GeV squared with W greater than 2 is soft DIS, and that has not been touched, either experimentally nor in principle theoretically. Now we go to the definition of SIS. Now, shallow or elastic scattering was conceived as the non-resonant meson production with W greater than the pion threshold. We cannot experimentally separate non-resonant from resonant meson production, so we practically define SIS as inclusive meson production with W less than 2 GeV. Now, as you can see from the landscapes, the majority of the contemporary studies, at least as pion production is concerned, have been for 1 pi, mainly delta production. So that's where we know things fairly well. So for this overview, we'll define SIS as meson, mainly pion production in the unexplored kinematic region from 1.5 to 2 GeV in W. Now, I hasten to point out that this is really significant for Dune because 45% of the charged current events from Dune will have W greater than 1.5 GeV, a non-trivial amount. To start the overview, let's just briefly look at the theoretical picture for the SIS-DIS region. And this is mainly from Sajjad Attar who was my co-author on the SIS-DIS review. And I point out that Huma Haider will be giving more details on this theory in a Thursday Working Group 2 parallel. What Sajjad did was very concisely and very evenly present neutrino nucleon scattering, first in the shallow and elastic scattering region for resonant, non-resonant, and interference contributions, then deep and elastic scattering, where he introduced the structure functions and parton distribution functions. He then went through the various QCD corrections and then brought the whole thing into the nucleus using the Alligar-Valencia formulation. I don't have time to do much more than show you one figure, but it shows you a figure of what the Alligar-Valencia formulation predicts for a neutrino energy of 65 GeV on iron, and it's compared to the experimental results of Nudev in black points there and CDHSW in red. And it is actually not bad. There's some problems here at low X and low Y, but that obviously translates to low Q squared. And we know that low Q squared has always been a problem. There's also some disagreements at the higher X, but nothing that stands out. Please wait for Huma Haider's presentation for more details. So let me go directly to the experimental and phenomenological overview and remind you, when we start with deep and elastic scattering, that neutrinos have been using DIS to study the structure of the nucleon for 50 years, over 15 major experiments. We started out with the Gargamel heavy freon experiment back in the early 70s, where we were actually trying to verify scaling, which had been recently discovered at SLAC, and we were talking about hundreds of events. That exploded over the next 30 years to the measurements like the NUTEV measurement on iron, the CCFR measurement on iron, CDHSW on iron, which were millions of events. And then in addition, we had CHORUS on lead, also millions of events. So quite a big explosion in the 30 years. Let me point out the most recent neutrino DIS measurement is coming from the Minerva low energy beam, where we measured the DIS neutrino nuclear ratios. These were the ratios of carbon, iron, and lead to scintillator. The red shaded histogram in these distributions is the Gini prediction using charged lepton measurements of nuclear effects. 1 second, please. All right, so these Minerva low energy measurements of the DIS cross-section ratios will be very useful for improved understanding of the low Q squared and low W nu A DIS interactions. The results from the Minerva higher energy DIS nuclear target analysis using the higher energy, medium energy beam are soon to be released. You should hear more from Minerva in the next talk from Michael Kordowski. Now, what are these charged lepton measurements of nuclear effects? And why did Minerva measure ratios? Well, that's this next slide, which says along the way, in 1983, as a matter of fact, the European muon collaboration measured the ratio of cross sections per nucleon of iron to deuterium. That's this right here. And what they found, instead of this ratio being 1 across X, they found that there was a definite shape. And this definite shape has since been categorized as the shadowing region, the anti-shadowing region, the EMC, and then the Fermi motion region. These are called nuclear correction factors that were used to combine neutrino nuclear results with nucleon results in trying to get global fits to the nucleon PDFs. The ratio shows that for at least charged lepton nuclear interactions, the structure of the nucleon in the nuclear environment is not the same as that of the free nucleon. And that implies that the PDFs of nucleons in the nuclear environment, which we call nuclear PDFs, are not equal to the free nucleon PDFs. Question we want to ask then, of course, is do neutrino interactions with nuclei show the same effect? there were early hints of a difference between neutrinos and charged leptons when, as a matter of fact, 1993, we, in the CTEC collaboration, in our global nucleon PDF fits, tried to combine neutrino nucleus interactions with the charged lepton nuclear correction factors. Excuse me. I'm going to address this question with the nuclear CTEC studies, but there's also other groups like the Florian group, the Bakunin group, and I noticed that Kumano is now on board, and he has done a lot of work on this in Japan. So let me just give you a quick one-slide summary of what we found for the nuclear PDFs from NCTEC. We did our first test of this in 2010. And what we found using NuTeV and core steeply elastic scattering and NuTeV dimuon sigma cross-section for the strange C is shown here on the right. This is for 5 GeV squared and 20 GeV squared. What we found is the red line with the errors in yellow. And what it shows is that there is a clear difference between what we find for the neutrino nuclear correction factor compared to what was found for charged leptons. We tried many ways and we could find no compromise fit for both neutrino dominated by NuTeV and the EMU results, the electroproduction results. Update, we found this to be a very striking result. So we wanted to check it again. So we have an ongoing 2021 analysis of NCTEC looking at the ratio of cross sections. And we expanded the data sets to include the dimuons of CCFR and NuTeV, as well as the deep elastic scattering results of CCFR, NuTeV, CDHSW, and Chorus. We put this kind of Q and W cut on this, which meant that the Minerva data does not yet make this cut. We improved the treatment of the cross-experiment normalizations, and we looked at the R denominator in more detail. And what we find, and this is still preliminary, but soon to be released, what we find is that the tension still exists, particularly at x less than 0.1 in the shadowing region, and to a lesser extent at higher x. So we have confirmed what we found in 2010 for low x. We have softened at higher x. Now, I do want to point out that there is a new fit from nuclear CTEC collaboration that goes down into the SIS transition region. It's called NCTEC 15 high X. You can find the nuclear part-time distribution functions at this address. And it's for charged lepton PDFs with now W greater than 1.7 GeV in the transition region and Q greater than 1.3 GeV squared. What we did is we took the higher X, lower Q Jefferson Lab data, new data, and we folded in target mass corrections, which are subleading M squared over Q squared corrections to the leading twist. And they're accounted for with the help of the Nachman variable C. Then we also included higher twist effects. Now, the non-perturbative multi-quark interactions, these are theoretically not well understood, but we parameterize them experimentally by looking at the F2 goes to F2 leading twist plus a factor that now includes a 1 over Q squared effect with a CHT numerator. Speaking of higher twist, there is two major results that show us what higher twist looks like for neutrinos. And again, I remind you that from perturbative QCD with Q squared evolution proportional to 1 over log Q squared over lambda squared, we extend into the non-perturbative QCD regime that's going down in Q squared, down in W, and consider 1 over Q squared effects. There is the target mass and the higher twist that I mentioned before. And what we found from two early experiments, these are both bubble chamber experiments, Gargamel heavy liquid and BEPS neon hydrogen in the SPS beam, using leading order QCD and with target mass corrections already applied. What we find is that the higher twist in neutrino scattering is smaller and negative compared to what they found with charged leptons, which was increasing in size as far as X increased. So both experiments find this difference in higher twist for neutrinos. And I point out there have been several theoretical studies that say that one can expect a difference in higher twist between neutrino and charged lepton scattering. So let me continue into this DIS to SIS transition by bringing up quark-hadron duality. Now, quark-hadron duality is a general feature of the strongly interacting landscape, and it just tells us how to connect the physics of quark gluons from DIS with the physics of nucleons, mesons of SIS. This is quark-hadron duality. Most of the theoretical work has been around Bloom and Gilman's definition of duality by studying structure functions from nucleon scattering, and noting that the leading QCD formulation of DIS is like the average over the resonance regions. So what does it look like? This beautiful figure here on the bottom right is an example of quark-hadron duality. It is from F2 proton, and it's electron-proton studies at Jefferson Lab. And it shows you the various resonances that are in red at the different Q-squareds marked on the right. And then through that, over the same distance in C. Now, this is the Nachman variable, not X, but C, to indicate that target mass corrections have been included. This NMC value at 10 GeV squared from DIS, this over the same C region is the curve. And as you can see, it looks very good. This is an example of global duality. But this means it just looks good. How about a quantitative test of duality? The quantitative test of duality is a ratio of the strengths of the SIS to DIS region, where ideal duality would be I = 1. And it's the ratio of the structure functions in the resonance region compared to the structure functions in the DIS. Again, I remind you what C is, the Nachman variable. If we use the Giesen fit to electron nucleon scattering, we find that if you take this ratio, the resonance contribution is on the order of 85, 90%, something like that. But then when you actually add in the non-resonant production, it goes up quite close to 1, 0.95. And so this is a pretty good indication that at least for E-nucleon scattering, duality holds. Now, what about neutrinos? Let me emphasize again and again that there are no high statistics nucleon data to make comparisons for neutrino-nucleon interactions. So you must rely on models for neutrino-neutron, neutrino-proton, and neutrino isoscalar scattering. At the top, I have the resonance estimates of Lala-Kulich, Melnick, and Paskos for new neutrino-neutron and neutrino-proton scattering. And what you look at here is neutrino-proton, that the integral is much greater than 1, whereas if we go to neutrino-neutron, the integral is much less than 1. So you say, wonderful. 1's greater than 1, 1's less than 1. Let's combine them, divide by 2 for the isoscalar nucleon, and that should be better. And indeed, it is better. This is the resonance estimates from the Gibu model for neutrino isoscalar nucleon, and it's compared to DIS at 10 GeV squared. And what we find is that the integral comes out to be about 0.7. Now, no non-isoscalar pion results have been included, so maybe it goes up to 0.75 or 0.8, but it's still at least 20% away from ideal duality. Now, even worse is when we start talking about nuclei. With nuclei, there is, of course, an excess of neutrons in iron, for example, not a huge excess, but an excess. And problems could come from models for final state interactions. So what we have here is the Ghent and Giesen models for neutrino iron, F2, And then this is the ratios down here. And the ratios, as you can see, it's these lines here and here. They're more on the order of 0.5. So it seems to be missing ideal duality by about 50%. So in general, for neutrinos, the resonance structure functions for proton are much larger than for neutrons. And in the case of DIS structure functions, the situation is opposite. Now, how duality should be applied with neutrinos is still an open question. There's interesting ideas on two-phase duality, where one is for XF3 and the other is for F2, but I don't have time to go into that now. Now, has the duality concept led to predicting SIS behavior from the DIS measurements? And the answer is here. There is the Bolek-Yang model. Again, I don't have time to go into the details, but it's a clever model that takes the GRV lowest order PDFs that are good for W greater than 2 GeV and Q squared greater than 0.8 GeV squared, and extends it down in Q squared and W into the SIS region. They include target mass corrections and higher twist effects by a modified Nachman variable, if you wish. Then they introduce quark flavor dependent K factors to extend the values of the individual PDFs down from Q squared equals 0.8 to down to lower Q squared. All initial development and checks of the Bolek-Yang model were done in electron, neutron and electron proton. So the V contribution to neutrino nucleon scattering, pardon me, as well modeled, and Bolek-Yang then added the A contributions. They introduced nuclear effects as measured in electroproduction. And we just saw that there are differences between the nuclear effects of electroproduction and neutrinos. The updated Bolek-Yang model now lets us, they say, gives us both neutrino and antineutrino nucleon cross sections with W greater than 1.8 GeV. So immediately one thinks, how about comparing Bolek-Yang and the NC-Tech 15 high X nuclear parton distribution functions for W greater than 1.7 GeV. Another important SIS-DIS concept is hadronization. And what we find here is that it is important because it gives multiplicities and kinematics of the hadrons before final state interactions and impacts the estimation of backgrounds and calorimetric energy of reconstruction. Mike Kordowski also mentions why this is important in his talk coming up. The empirical observation of the average charge multiplicities is n charged as a function of log W squared. And we, in Gini, they use the AGKY model based on KNO's model at low W and Pythia at high W, because you need to understand what is the dispersion around this average to be able to predict or to generate events with particular multiplicities. Down here, we have a figure prepared by Kostas Andropoulos, and it shows as E nu increases, the fraction events that are resonance, KNO, and Pythia. That's all I have time to talk about now. But now we've been talking about inclusive. What about—
5 more minutes, sorry.
Pardon me?
You've got 5 more minutes.
Oh, okay, thank you. What this shows here is getting away from inclusive and going more to exclusive predictions for SIS phenomena. First, I have the new MK model from Inu. It's a single pi model. And what she has done recently is she has very much extended the W and Q squared range of the model. There are several of us who've been pushing to come on. We have to go all the way up to 2 GeV to actually understand what's happening in the SIS region. And her latest update extends this model to high W and higher Q squared. And I want you to note here at the top, this row is for low W, essentially 1.2 to 1.4 GeV. And it shows that her predictions match the data really quite well. Now, even at high W, going from 1.6 to 2 GeV, her model matches the data that's available. For EP plus goes to EN plus pi plus, it matches it quite well. And she also shows us exactly what the various contributions are. This is the resonance contribution. This is the non-resonant pion contribution. And this is the important interference between non-resonant and resonant. So you see, it's a complicated process, and you really have to understand all three contributions to be able to come to something that could match the data. This has all been for nucleon. However, she has neutrino-nucleon interactions coming soon. Now, how about multi-pion production? Multi-pion production is really important. What it shows is that when you go above the delta, the 2-pi decay states are between 25 to 55, even 90% of the resonances above the delta have 2-pi or greater contributions. Now, Nakamura, Kamano, and Sato have taken on the challenge of predicting multi-pion productions in this high W region. They start with a dynamical coupled channel model that they developed for pi n and gamma n interactions. They extend the modeling to the vector current to model electron nucleon and compare with data. Then they use PCAC to include the axial vector current and develop this dynamical coupled channel for neutrino nucleon resonances. They also include the interference between resonant and non-resonant amplitudes. And the result for single pion agrees quite well with data. And they have the first dynamical coupled channel model to give double pion production, resonant, non-resonant, and interference. I show down here just an example from their paper. And this is the pi plus, pi naught, pi plus, pi plus, and pi plus, pi minus states. And this is their model prediction compared to the data. And let me emphasize again that the data is old bubble chamber data from the 70s and the 80s. And that is a hindrance for people who are trying to make models to predict what we expect to see and have only old bubble chamber, low statistics data to normalize their events, their predictions, excuse me. So, yes, we are getting increasingly sophisticated models covering the SIS and DIS region. However, there is minimal high statistics neutrino nucleon and even neutrino nucleus data covering the kinematical range of interest, and for neutrino nucleus over a wide A range. What experimental data can we expect in the near future? Well, Minerva will finish the study of 1.5 to 2 GeV of neutrino, anti-neutrino on scintillator. We will measure the total and differential inclusive cross sections with respect to Q squared, C, and W in the SIS region. And we will measure multiplicities of charged hadrons in increasing W bins from the SIS to and in the DIS region. That will be the contribution from Minerva. And then we expect from Dune should have millions of events in this unexplored SIS region, as well as a huge DIS sample for detailed hadronization and nuclear parton distribution function studies. This is the distribution predicted for Dune. There is also a new player in the game. Let me point out there's the CERN Forward Physics Facility, which will have neutrino beams from the LHC to expand the study W and Q squared regions. This is for like a 10-ton liquid argon detector in the LHC, I guess it's HD LHC, I believe, starts in 2027. And this, if you can look at the scale, this right here is 1,000 GeV squared in this line right here. So these are all above 1,000 GeV squared, where this is all above 1,000 GeV in W. So there's huge samples in a very expanded W and Q squared region. So now, instead of actually conclusion, because I don't think there is a conclusion right now, the conclusion is we've got a lot to learn and we've got a lot to study. There are open questions for the theorists and open questions for the experimentalists. I have summarized here just a few points. The theory of DIS needs a study of the non-perturbative QCD regions for neutrino, high X, low Q. We need a better understanding of X greater than 1 region for nuclear targets. This is important for us in the nuclear parton distribution function global fitting game, because our global fits stop X equals 1 with where we expect 0 events, but that is not true for nuclear targets. We have to have a better understanding of partonic nuclear effects with neutrinos. Experimentally, we definitely need a large hydrogen and deuterium experiment. We need neutrino-neutron to normalize 1 pi and 2 pi models to understand hadronization of neutron. So we then need, this would give us the high statistics, double differential cross sections of single and multi-pi production of neutrons and protons, improve tuning for hadronization, provide experimental checks, a whole series of things from hydrogen and deuterium experiment. We also need large statistics measurement over a wide range of low to high A, particularly lighter targets. We essentially are stuck with iron and lead, which are very interesting experiments, but there's a lot of lighter nuclei that need data. As far as SIS, we have to have a better understanding of how duality works with neutrinos, continued development of resonant, non-resonant single and multi-pi models on nucleons. We have to bring these models into the nuclear environment. So we have to have increased investigations of final state interactions. Experimentally, we need measurements of single and multi-pi production on nucleons. This again says we need a hydrogen and deuterium targets for neutrino-neutron in this case. We have to have measure SIS inclusive and exclusive cross sections as a function of WC for duality studies. And we need high statistics, double differential cross sections off a wide range of low to high A. So that's just a couple for both the DIS and SIS region. I invite you to contribute more, to keep thinking about this, because these are 2 kinematic regions that really need help both theoretically and experimentally. And I would invite you to continue with this study. So let me stop there and open up for questions.
Thank you very much for this important talk. Yes, I see we have a first question from Ori. Go ahead.
Do you think the safety issues regarding a hydrogen target that Minerva faced can be overcome?
This is obviously an important question. When we tried to do a hydrogen target for Minerva, and actually just started looking at the possibilities of a hydrogen bubble chamber to put in the NUMI beam. The most critical part was the safety considerations, and I think that these can be overcome. There are studies underway of how to do it, but I don't have any more details at this point. It is a challenging problem, Laurie. There's no doubt about it.
Okay, and the second question by Shanzu.
Yeah, in page 13, you show the higher twist effect, and especially the difference between the charged lepton and neutrino. I'm just wondering what will be the physics mechanism. Is it the nuclear effect or effect within the nucleon?
This is a question that hasn't been answered, because we don't have enough data on neutrino nucleon to look for higher twist from the nucleon.
Yeah.
All I can point out is that this question of nuclear higher twist in nuclei is very important. There are many people who think that the higher twist in nuclei is even stronger than the higher twist in nucleons. And we don't really yet understand what the A dependence of higher twist effects is.
Is it something related to the Fermi motion?
It's possible in the nuclear, but we've seen higher twist effects in the nucleon for electron production. And of course, that's not Fermi motion.
Yeah, that's right.
So yeah, lots of open questions, but thank you for emphasizing.
Yes, thank you.
There is
Are
a
there
question from the audience here.
Please go ahead.
Yes, I saw from your slides that you consider essential an experiment with deuterium or with hydrogen. And also Maury was raising some concern about the safety. But my point is, I've seen in literatures that there are several papers that claim that it is possible to use an hydrogenated target and then subtract the contribution from the carbon in such a way to pin down the cross-section for hydrogen. What do you think about this? Do you think that the claims and the systematic budget that they claim is realistic, or that anyway we need this hydrogen and deuterium experiment?
Yeah, that's an important point. Thank you for bringing that up. I think, as a matter of fact, Roberto Petti from South Carolina has done a very nice job of making a proposal on how this can be done, not only with the subtraction, but in using the kinematical balance of a neutrino-hydrogen interaction compared to a neutrino-carbon interaction, for example. I think there is approaching the possibility of making this real. I have not been completely convinced yet, but Roberto has been doing a good job of trying to convince me. Now, the need for deuterium is obvious if we want neutrino-neutron interactions, and they are extremely important in themselves. If we are going to be able to look at the models for single pi and double pi production, they are crucial to look at neutrino-neutron given the single pi and double pi. It's also important for hadronization studies, which are crucial for all of the important reasons that I listed. There are neutrino-neutron constants as well as neutrino-proton constants, even in the average multiplicity arguments. So I think to disregard neutrino-neutron as an important emphasis is a mistake. One needs to consider neutrino-neutron as well as neutrino-proton.
Okay, thank you very much. If you have any more questions, I urge you to write them in Slack, and we'll make sure that Jorge will get them, and we'll have to move to the next talk.
Okay, also please don't worry about emailing me with questions. I'll be glad to get into a discussion about the topics. Thank you, everyone.
Thank you very much, Jorge. Okay, so we'll move on to talk about results from Minerva. Michael Bordowski, please take it away.
Hi. So hopefully everybody can hear me okay. Thank you for inviting me to give this talk. I really wish I could have come in person. It looks lovely there. And hopefully during better times, we can see each other again. I'd like to start with a little bit of an apology to Jorge, because I decided to take my talk in a little bit of a different direction than he was probably expecting. There are a lot of results from Minerva, but it turns out kind of the very newest things are our measurements to constrain the neutrino flux. And I thought, given that this is Nufact and it's really focused on beams and so on, that this might be a good topic. It's also sort of an end of the road topic for Minerva. We've pretty much done just about everything we can. So there's Minerva. It was upstream of the MINOS near detector, which it used as a muon spectrometer. Of course, this is at Fermilab in the NUMI beam. Its big sort of things are it had a fully active scintillator tracker with these triangular bars to allow nice fine grained tracking, and then it also had embedded nuclear targets that enable a program of comparing the same interactions in the same beam on different targets. So NUMI ran for quite a long time, or Minerva ran for quite a long time. NUMI is still running. So it took data in two configurations. One was the low energy configuration, and the second one was the medium energy. It turns out the data set is humongous, particularly in the medium energy configuration. So I'm going to focus mostly on that. That's where a lot of the power of Minerva comes from. So what's the motivation for doing this work? Well, you know, different people have different motivations. For me, it goes to oscillation experiments. And So if you look at the rate at a near detector, it's really an integral where there's a convolution of three terms. The first is the neutrino flux. And so we predict that a priori with a beam simulation. So G4 NUMI is what it's called for NUMI. G4 LBNE is sort of its successor for the, or G4 LBNF is maybe what we're calling it, for the LBNF beam. And then what you do is you try to take hadron production data that you use to improve the simulation. There are different ways of doing it, but the way we do it is event by event reweighting after the fact. And then you also try to incorporate the uncertainties. And so we do that via a multi-sim or many universes approach. That's sort of a jargon that we use, but basically the underlying data, hadron production data, and other model parameters are varied with their joint covariance matrix, and you get a new simulation, and you do have many of those. And then there's some systematic control that you can have by changing horn currents, target position, off-axis position, and so on. So the next part is a cross-section. And so this is nucleus and hence detector dependent. And normally or often the far detector and the near detector have the same nuclei, or maybe the near detector has some variety. And of course, there are various final states. There's not just one cross-section. Some are easier to measure than others. And then the final thing is the detector response, and that encodes the relationship between the true and the reconstructed energy. And that includes the kinematic acceptance of the experiment, smearing. It's predicted by a Monte Carlo simulation, so an event generator plus something like JANT. People often run test beams and so on to improve that simulation, but it really critically depends on the scattering channel in the final state. So there's a coupling between sigma and R here that is non-trivial and that one has to deal with. So just a couple examples of what happens if you get sigma times R wrong. These are both from the Dune near detector CDR, which I've spent some time working on. So here's a study where there's missing energy due to neutrons that's not in the model, that's not in your model. And you do a model tuning, but you don't realize that that's the problem. So you tune something else or some other things. And you don't realize that you've got missing energy due to neutrons. And you then look at what happens to an oscillation measurement. This is a disappearance measurement. And you can see that there's a large bias that's larger than the size of the current uncertainty on delta M squared. So this is an example of getting that wrong. Let's see. Here's another example. This is a case where it looks at the delta CP bias for a case where you've got a mock data model that's Neuro and your Monte Carlo is Gini. And there are various things that are different, but one of them is the pion production model. And so you have to correct R for pion masses in order to get E-RICO correct and unbiased. And so what this shows is that if you do nothing, you get black, which are large biases. And then as you do sort of more detailed correction, you can remove some of the biases. It's not perfect because there's other differences between the two, but it's suggestive of what one needs to do with a near detector. And there are other things that Dune in particular is thinking of doing. For example, moving the near detector off axis allows you to vary the flux in a controlled way, which is another way of trying to understand what you're doing. So if we go to the far detector, well, there's an additional term, of course, which is the oscillation probability. And so the goal, of course, is to extract the oscillation parameters and basically understand this integral. The beam simulation generally predicts the sort of the flux ratio between the two detectors fairly well, sort of percent level uncertainties, at least without oscillations. Of course, if there are oscillations, then they're causing a flux difference. And then you constructing the two detectors out of the same nuclei gives the same cross section at the two detectors. And then oftentimes you want a functionally similar near and far detector that can reduce the difference in R between the two detectors. But even doing all of that, you still have somewhat of a problem because that integral and the unknown oscillation probability just spoils a direct cancellation. And so oscillation analyses end up being model dependent at some level. And so there's a need to understand the models and or reduce or remove dependency. And so that's sort of the motivation for Minerva. and some of what I'm going to talk about today. So Minerva, in a way, you can think of it as a pretty capable near detector that just doesn't have a far detector. And so the real goal is to try to tease apart that integral there. And I'm going to spend a good time today talking about the flux. It's kind of the first thing you'd like to get right. The things we've done to try to constrain the flux has some unique elements enabled by the data set and the detector. And some of that, the lessons and techniques can apply directly onto future experiments like Dune. So I'll skip over the NUMI beam part of this. I think everyone's relatively familiar. So how do we get to a precise flux? Well, we start with the beam simulation. And so it's a combination of things like, getting the geometry right, doing careful sort of detailed surveying, materials assay, all of that. Then the physics part of it, the hadron interactions and correcting those interactions. And then finally, what I'm going to say more about today is in situ measurements that one can make to try to further correct the simulation or improve knowledge of the flux. So there are significant focusing uncertainties in these beams, and little details matter. So things like millimeter level offsets and percent level changes in things like currents actually have a significant effect on the flux. They all tend to happen. This is for the medium energy beam configuration in a particular region, which is sort of the edge, the higher energy edge of the focusing peak, which is a common area where it's easy to mismodel this area of the spectrum. And then so the hadron interactions are really quite a mess, and many neutrinos have multiple interactions in their ancestry. It's about 1.3 for the NUMI beam. These are strong interactions in hadronization at low Q squared in nuclei. And so there's really no reason to expect the Monte Carlo to get this all correct. So, you're expecting to need to do some corrections with data. There we go. So how do we constrain the simulation? So the first part is to carefully tabulate interactions in material in each of the neutrinos' ancestries. And then you get some relevant hadron production data. So an invariant cross-section for like pion production. And then you weight the interactions and you assign and propagate uncertainties. So the most important data set used for our a priori flux prediction is pion production data from NA49. It's a nice data set. It really covers the kinematic range that we're the most interested in the NUMI beam, and it's pretty high precision as well. So this is excellent data. There's data now coming out of NA61, which is sort of the successor to NA49, that is also going to be quite useful. It hasn't been incorporated quite yet into the NUMI or the LBNF simulations, but it is something for the future. So, we do all of this work and we come up with this a priori flux prediction and a correction to the raw Monte Carlo. So this ratio shows the size of the correction. It's not huge, but it's not small. It's sort of like 10% to 20% level corrections. And then once you've done all of this work, you can get down to an uncertainty that's in, less than 10%, but not quite to 5%. And so that's what you're dealing with a sort of a priori flux simulation once corrected. Okay, so now I'm going to start talking about it in some of the in situ data. And in fact, the first thing I'm going to talk about is something called the low nu technique that's been used for a while. It turns out that we put out a paper 1 week ago on this. So this is very kind of hot off the press stuff. But as you may know, the cross section as a function of energy transfer has this form where the A, B's, and C's are basically integrals over structure functions, and you get this polynomial in nu over E nu. And so what one can see is if we can keep nu over E nu small, then this goes to a constant. And so what you're measuring is the shape of the flux. The cross section is just constant as a function of energy. And to the extent that it's not, then you have a model like the model in Gini that predicts the non-constant nature of that, and you need to correct for it. So what one also can then do is take this and normalize to the well-measured high-energy neutrino charge current cross-section. How high you go is sort of depends on your experiment. When Minos did this, I think we normalized up at 50 GeV, but Minerva normalizes somewhat lower than that. Anyway, the long and short that comes out of this is something that we've sort of realized is an issue, which is that there's a warping of the flux shape around the focusing peak. And the best hypothesis is a shift in the muon energy scale of about 1.8 sigma. And so that's essentially the energy scale of muons measured by Minos. They're not exactly the same muons as the muons that Minos measures for its oscillation analysis, because those begin with interactions in the middle of Minos, the sweet spot of Minos. These are muons that are entering Minos from the front, where the field is less well known and more non-uniform and so on and so forth. So this is not maybe an entire surprise. The 1.8 sigma was for the actual Minos experiment. So anyway, this shows the ratio, and you can actually, there's this wiggle that can be made better by that shift. The weakness of this whole method is that there's a potential circularity with cross-section measurements, and there's some model dependence. And so when you're doing this, you try your best to account for model dependence. Minerva is studying interactions on different nuclei and has a corrected version of Gini that we use and so on. But still, as ever, the problem is the nucleus. And so the question is, what to do about that. And one thing you can do, and we have done, is just get rid of the nucleus. So we're going to consider some data that doesn't have any hadrons in it. So there are a couple of channels. The first one, and perhaps the most important one, is neutrino electron scattering. So there are some diagrams for neutrino electron scattering. The cross-section is extremely well predicted by the standard model. It's tiny, even for neutrino cross-section, 4,000 times smaller than the inclusive CC cross-section. Radiative corrections are important at the few percent level, and we're trying to do things at the few percent level here. So one has to account for radiative corrections. And I list some references there that are both experimental and theoretical papers, as well as a nice so-called wine and cheese seminar that was given just before the pandemic at Fermilab that goes into this with quite a bit of detail. So these events are dead ringers in the detector. The kinematics requires that the energy of the electron times the angle, or the angle squared, is small, less than 2m, twice the mass of the electron. And so what you see is just this very forward electron with no hadronic recoil. So this is a nice example of one of these starting in the Minerva tracker and going into the eCal. The electron can radiate real photons. Obviously, as it showers, it does, but in the fundamental interaction, the electron can radiate real photons. And so that's important to include them in the cross-section. And in fact, the cross-section that I've shown here, that's what this gamma indicates, that it also includes gamma production. And generally speaking, those photons are collinear with the electrons. So it's really hard for you to separate them out and say not measure their energy or whatnot. Okay, so this is some data from the medium energy anti-neutrino beam. So one of the two configurations of the medium energy beam. These are the two important variables for the analysis. The first is that E theta squared, which needs to be true, or which needs to be small. And the second is the DEDX of the shower right at the beginning of the shower, where it's still kind of track-like. So the idea here is, of course, that that if you have a photon-induced shower that's a background, then as that photon converts, it converts into an electron and a positron, and so you get a DEDX that's twice as much as you would get from a single electron. And that's what's shown in this distribution. And so there's a cut that's placed here and there to select a signal region. You can see it gets rid of quite a few background events. This blue is nu mu coherent pi zero production. So you'd expect that's a potential background. DDX gets rid of that. The other background is that's pretty significant is electron neutrino quasi-elastic scattering, where you've got an electron in the final state. And here you've also got a neutron in the final state. So this background is a little more serious in the anti-neutrino beam. So then what's done is we define some sideband regions. I don't want to talk too much about this, but basically in the E theta squared space, there are natural sidebands. One of them is effectively here. You can see that above the location of the cut. It's just background dominated, and below that, at least according to the model, there's not a whole lot of shape. So we try to go off and constrain the different backgrounds using sidebands and splitting the sample up into quarters. This is what the sidebands look like. You can see that different ones are dominated by different backgrounds. We fit in a variable called the shower end transverse position. You could fit in other things too. This seems like it's relatively well modeled, and so that's why it was picked. And then the results of the fit just gives scale factors. So the thing that the fit really wants to do is it wants to turn up the coherent pion production in bins of energy. So these are all different bins of energy that are basically informed by this particular histogram, this sideband in neutrino energy. So that's interesting. This is just a corner of the phase space, so it's not a statement that the coherent cross section is off by a factor of 2 in the Monte Carlo. It's a corner of the phase space. So this is what the distributions look like after the sideband fit and the signal selections. You can see that they're pretty well dominated by signal, except in that lowest bin. And the modeling looks pretty good. This is for example, the angle of the shower. And then this is going to be the thing that we're going to use eventually to constrain the flux. Okay, so then after background subtraction and efficiency correction, you get out an electron energy spectrum. And so we've got some integrated number of events. We know the cross section, and that can be used to effectively unfold the flux. So that's the whole idea here. This is statistically dominated measurement, and the systematics are actually quite good, particularly at low electron energy, where most of the events are. So this is a promising technique for the future, somewhere like Dune, which will have more events. So how does one then constrain the flux? Well, I told you earlier on that the way we propagate uncertainties is we have a so-called many universes technique or multi-sim technique, where we have a bunch of different models. So that's M here. And what we want to do is we want to compute the probability of a particular model agreeing with our data, the number of events that we've measured. And you can do that via Bayes' theorem. So this is hard to predict or to compute. This is easy, the probability of getting some number of events given the model. That just comes right out of the beam simulation. So, and then the a priori model of the flux, those are distributed in a way that I'll show you. So anyway, you have to compute the likelihood of the data. We do that in bins of electron energy, and this is essentially a sort of chi-square looking likelihood. So this is calculated for each universe of the flux error band, and then some of the universes are weighted down because they don't agree with the data, and some are weighted up because they do. Okay, so this is what comes out. This is again just from the medium energy anti-neutrino beam. So we have a number of neutrino electron scattering events. The black histogram is before the constraint. So this is what was predicted by the corrected beam Monte Carlo, and it's sort of a Gaussian shape, and this Gaussian shape tells you the probability essentially of the a priori probability of getting some number of events. And then after applying the constraint and weighting certain of the universes up and certain of them down, you get this red histogram. And so there's I think a 3% reduction in the flux here. There's also a noticeable reduction in the RMS over the mean, and that tells you that we're making the uncertainty smaller. So that's nice. So that's just number of events. You can then, once you've done that, you can go ask the model, okay, I want you to tell me what the flux of, say, antineutrinos is. And so this is actually the flux, the integrated flux of antineutrinos that comes out of the unconstrained and constrained models. So these plots have a single constraint from neutrino electron scattering in the antineutrino beam configuration. We have a similar measurement in the in the neutrino beam configuration as well that I'm not showing here, but it looks quite similar. And the technique is the same. And there's one more thing too, which is something that is relatively new, and that's inverse muon decay. So this is a similar elastic scattering type of, well, not totally elastic, but a similar scattering process to neutrino electron elastic scattering, but instead there's a muon in the final state. And so this is interesting. It also has a small cross section, and it has a threshold that's relatively high, 11 GeV. So this process constrains the high energy component of the flux, and it's only sensitive to muon neutrinos effectively. So this gives you an idea of what the flux in the of muon neutrinos in the two beam tunes is. The FHC beam is the neutrino beam tune. So obviously you've got a lot of muon neutrinos there. And then this is the spectrum of IMD events, and you can see where the threshold is. So we're going to try to use these events to improve our knowledge of the flux.
You got 4 minutes.
Yes, okay. I'm at 20 minutes right now, but anyway, okay. So these events are fairly easy to select as well. It's just a muon appearing in the detector with no recoil. And so there's a similar sort of variable to E theta squared. It's sort of a scaled version of it that's used in the selection. And you can see that events are, there's a peak of events piling up down at low values of this variable F, which is effectively E theta squared. So there are not a ton of events, but they're not such a small number. 127 in the neutrino tune and 56 in the antineutrino tune. So we're going to go ahead and try to use those to form a joint constraint. And so what one does is just take the bend. So these are the electron energy bins that I showed you earlier. These are the same for the neutrino tuned beam. And then these are the IMD events. And so you have this, larger histogram that we do the very same computing of probability and a weight for each of the individual universes. I'll skip over the covariance matrix. It's mostly diagonal. This gives you an idea of what the different constraints are. So this is number of neutrino electron scattering events in the two beam configurations, unconstrained. And then when you start adding constraints, I've indicated what the measured number of events are. You start to disfavor some of these universes. So each one of the dots is a universe. And so this is with one constraint, this is with the other. This is with the combined neutrino electron scattering in the two beams. And then this is what happens when you add inverse muon decay. And you can see it actually wants to turn the flux down just a little bit. So that's an example and a sort of a picture of how this works. And then this is the combined result. So this is new mu flux in the neutrino tune beam and anti-nu mu flux in the antineutrino tune beam. So these are sort of the dominant modes. And you can see probably the most important thing to look at is the RMS over the mean is 3.3%. So this is indicative of what the uncertainty on the flux is. We've gotten down to the 3% level. It's not quite as good in the RHC beam. And then this is what the actual fluxes look like. We just generally want to tune the flux down by about 10%, a little bit more in the neutrino beam. Okay, and so these are then uncertainties, starting with the a priori uncertainty and then drilling down to get to the final uncertainty when we've applied everything. And so it's achievable to get down to lower than 5%, and we're statistics limited on these in situ channels. Okay, so this will take me to the end of my talk. So Minerva's flux constraint uniquely combines a sophisticated and a pretty well-tuned beam Monte Carlo with in situ data. And this is the first ever joint constraint of a neutrino and antineutrino beam using this neutrino electron elastic scattering and inverse muon decay. And so we've been able to beat these uncertainties down pretty far, further than I think anyone would have guessed, when the experiment started. There's not very much shape information, unfortunately. A detector with very good angle and energy resolution for at least for the electron channel will be able to do even better by constraining the shape of the flux. It's elastic scattering, and what you're scattering off of, and it's at rest. So with two variables, the angle and the energy, you in principle can reconstruct the neutrino energy. So this is something for Dune to try to do. There's a nice paper on it that was written last year. There'll be a huge sample in Dune, much larger than in Minerva. And this is effectively the end of Minerva's long flux campaign. The plan is to release results for NUMI on-axis, which is what I've shown today, as well as some of the off-axis locations, and couple this with another bit of what Minerva is doing, which is a data preservation work to make sure the data can be used down the road. And in principle, these results could even be rephrased to constrain the flux for LBNF and Dune. That might be something we will try. It's just sort of a novelty, because once LBNF and Dune are running, they'll do this on their own. But in the interim, we could probably try that. So I will go ahead and stop there and take questions.
Thank you very much for this exciting talk. It's great to see the progress. Are there any questions in the room?
Yes.
Go ahead.
Yes, thanks for the very interesting talk. About inverse muon decay, just small comment. There is another process there that contribute in the electron anti-neutrino beam. This is the S-channel Z0 production. I hope you have included that in your analysis.
Yeah, you may have noticed I said it's basically only sensitive to the muon neutrino flux. In fact, I'll be honest with you, the analysis actually treats those events as a background, but they're very, very small. It's sort of a 1% type of effect. And so they don't matter, but if you had an electron anti-neutrino beam or just a lot more data, then yeah, you would have to account for those.
There is another question. So very nice results. Since you showed them separately, I wanted to ask if you could confirm that the two channels actually push the a priori knowledge of the flux in the same direction.
Yeah, I think maybe you're asking here, which is they both want to turn the flux down. That's so the common thing. Yeah.
You get a consistent.
Yeah.
Even though the inverse muon decay is like constraining the high energy tail, is it correct?
That's correct. Yep. But it also wants to push the flux down. That's essentially been the story of Minerva, that when we started doing corrections to the Monte Carlo, the Hadron production corrections pushed things down, and then the elastic scattering in situ constraints also wanted to push it down even a little bit more.
Okay, thanks.
Yeah.
Okay, I see there are no questions in Zoom because we're running out of time. Well, thank you again.
Okay, thank you.
Move on to the next talk. So our next talk will be about the status of VSS neutrino superbeam and summary of this morning's workshop by Vladimir Klichek.
Can I get the microphone?
So hello, can you hear me? No.
Yes, we can hear you perfectly.
Okay, so I'm quite happy to be on site, so please have some patience while we figure things out here.
Put the microphone here.
Like this?
No.
Why?
Because you don't hear it.
Where do you want me to put it? Here. So is it better now? Yeah.
I'll share your screen if it's okay, and then or if you can share your screen.
Yeah, I think that now everybody should see my screen. So, welcome to the talk on the status of the ESS NUSB and summary of this morning's workshop. My name is Budimir Kliček and I work in the Ruđer Bošković Institute in Zagreb. So time is tight, so let's begin with...
Budimir, sorry. Ah, great.
Yeah.
Now we can see it perfectly. Go on.
Sorry?
Yeah, please go on.
Okay. Okay, so what is ESS NUSB all about? We are a design study for an experiment to measure CP violation at the second oscillation maximum. As you know, CP violation neutrino oscillations is manifested by the fact that neutrinos and antineutrinos oscillate differently in vacuum, so the probability is different. In ESS NUSB in particular, we want to see whether the probability of oscillation of muon neutrinos to electron neutrinos is different than the probability of oscillation of muon antineutrinos to electron antineutrinos. So our plan in its core, it's quite simple. First, we will run with muon neutrinos and look at the electron neutrino appearance. And then we will run with muon antineutrinos and look at electron antineutrino appearance. So why do we want to go to the second maximum? So unfortunately, online people can't see my pointer, but kind of try to imagine. So on this plot, I'm showing the probability of oscillations of muon neutrinos to electron neutrinos at one of our baselines, 540 kilometers, as a function of energy. So the full lines are vacuum oscillation, dashed lines are matter oscillations, and different colors correspond to 3 extreme values of delta CP. So the first maximum is here, and the second maximum is here. So as you can see, the first maximum is kind of messy. And the difference in probability for different delta CPs is smaller than in the second maximum. And also in the first maximum, if you don't have matter effects under control, they can mimic CP violation. So you can measure, dashed line and think that you are measuring a full line. While at the second maximum, everything is quite cleaner. The sensitivity is larger and matter effects don't matter. But there are much less neutrino interactions in the second maximum. So the question is whether we can afford it. So to recap, the CP violation signal at the second maximum is about 3 times larger than in the first maximum. But the bad thing is that you get less neutrino interactions. So you can go either 3 times away and further away and you get 9 times smaller flux, or you can reduce the energy 3 times, but then you get cross section, which is at least 3 times smaller, or you can even go below the charge lepton production threshold and then you have no events. So the optimal thing here actually depends on the systematic error and beam intensity. So the point is this. The largest signal at the second maximum is somebody speaking somewhere in Zoom. Hello? So this does not count towards my time. Okay, so as I was saying, at the second oscillation maximum, we have larger signal, and then it's less obscured by systematics, but you still need to have enough neutrino interactions to see something. So if you still do have enough neutrino interactions to see something, then the second maximum is better. Of course, for this, you need to have like an intense beam, and you need to have large enough θ13 because this is what's driving the appearance channel muon to electron neutrino. It should be noted that if you have no systematic error, which it's not possible, first maximum is always better. So can we afford the second maximum? So as it happens, a very intense proton LINAC is currently under construction, and we know for like 10 years now that theta 1.3 is large enough. So the ESS proton LINAC, ESS means European Spallation Source, is will be the world's most powerful LINAC, which is currently under construction near Lund, Sweden. It is designed to produce neutrons, so not neutrinos, and we want to upgrade it to be able also to produce a high-intensity neutrino beam. The average power of this LINAC will be 5 megawatt, which is quite impressive, and it will actually accelerate 450 milligrams of protons to almost the speed of light per year. So it's kind of, you know, we are accelerating macroscopic amount of quantity almost to the speed of light. Its repetition rate will be 14 hertz, so we will have pulses 14 times per second. And this coupled with about 3 millisecond pulse duration, we get a duty cycle of 4%. So the LINAC will actually accelerate protons only 4% of the time. So there is a lot of room to add cycles. The current energy is 2 GeV kinetic, but can be upgraded to 3.5 GeV. And the first operation actually is expected to start in 2 years. So it's quite soon. So the upgrades that we want to do to ESS to make the neutrino beam possible are the following. What you are looking at is a ground plan of ESS site. And the black lines are what's actually being built. And the colored things, most of them are what we want to build. So first, we need to upgrade the accelerator itself. We want to increase the frequencies from 14 hertz to 28 hertz, meaning we want to add another 14 cycles per second that we will use for neutrino production, not to mess with the neutron program. And we want to use H- ions instead of protons. I will come to this shortly. And increase the energy to 2.5 GeV kinetic, which will actually improve our CP sensitivity. Then we need to build an accumulator ring. The point with the accumulator ring is that it needs to shorten the relatively long ESS pulse from 3 milliseconds to about 1 microsecond. And the main reason that we need to do this is because otherwise at the far detector we would be swamped by the background from atmospheric neutrinos. So if we have a very short cycle, very short neutrino beam pulse, there is a very low probability that we will get neutrino interactions from atmospheric neutrinos. And this is actually where the H- comes into play. Now this thing works in a way that you slowly fill the ring with a long pulse over many cycles, and then you suddenly discharge it. So the duration of the short pulse will actually be the time for 1 revolution in the ring. Now, if you want to put protons inside, you will have protons and you keep adding more protons, and then you will get a phase space pressure, and at some point it will break. So to trick this, we actually want to use H- to accelerate and bring to the accumulator ring, and then at the very last moment, strip the extra 2 electrons and put the proton inside the ring. Okay, then we need a neutrino target station in which we will have 4 identical targets and horns. We need 4 because of the intensity of the proton beam. It's very difficult to have 1. And because we have 4 targets and horns, we need a switch yard, meaning which is this purple line, which will, shoot the protons to each horn at the same time. And last but not least, we need to build a near detector site where we will have water Cherenkov detector, fine-grained scintillator, and emulsion detector. So there will be a dedicated talks in work group 3 about all of this, which should start soon because we are late. So Ben will talk about the LINAC upgrade. Maya will talk about the accumulator ring, and Lukasz will talk about the status of the ESS USB target station. And I will say something about the NIR detector. So combining all of this, we get following neutrino fluxes. So our peak energy is around 300 MeV, and our beam is quite pure. We have some small contamination of prompt electroneutrinos, which is good for CP violation, but not so good for calibration of the detector, because we need to use this small contamination to measure the electron-neutrino cross-section using the NIR detector. The good thing in all of this is that actually most of these electroneutrinos come from muon decays, because our proton energies are quite low, so we don't get much kaons. So you can actually predict the amount of these electrons much more precisely just by using Monte Carlo. Right, so concerning the NIR detectors, so this is a part of the technical drawing that we already have. So the beam is coming from this side, and most upstream we have a NIR water Cherenkov detector, which is half kiloton. Upstream of that, we will have super FGD-like scintillator detector, so the collection of small scintillator cubes, which can be read out semi-independently. And upstream of that, we are planning to have a Ninja-like water emulsion detector of 1 ton fiducial volume, which will allow us to very precisely measure the topology of our neutrino events, you know, the angles of muons, electrons, and so on and so forth. Concerning the far detector, currently we are still choosing the optimal position. So we have two options. We have Garpenberg mine, which is 540 kilometers from the neutrino source, and it sits exactly at second oscillation maximum concerning with respect to our beam energies. And the other one is the Zingruven mine, which is 340 kilometers from the source, and it partly covers first and the second oscillation maximum. Concerning the far detectors, we are aiming to have a 0.5 megaton total fiducial mass detector. So we are planning to dig 2 large caverns, and each one would host a 270 kiloton fiducial mass detector. We are planning to have 20-inch PMTs for the readout, and our baseline is 30% optical coverage, but currently we are using 40% for the analysis, and I'm kind of rooting to have 40% in the end. Having these large detectors, you can do a lot of other stuff like proton decay and all sorts of astroparticle business. We have already started preliminary technical geological studies of the mines, and for example, here you can see the possible positions of our far detectors in the Zingruven mine. I would invite you to see the poster by Olga Zornpa, which is tomorrow, I guess, about the ESS USB detector performance, where you will get much more details on migration matrices, efficiencies, and so on. Unfortunately, I don't have time to go into this in this talk. Okay, so from the beginning of the project, we have had quite a lot improvements on the sensitivity of the entire thing. So recently we produced the new migration matrices for the far detectors, which are optimized for the ESS USB beam. And we managed to go from 50% efficiency to almost more than 90% efficiency. So this thing actually includes the fiducial volume cut, so it's larger. And the reason that we could have gone to such high efficiency actually is the low energy of our neutrino beam. So we don't have to worry much about backgrounds coming from deep inelastic neutral current events and resonances and everything that is happening over here, because our beam is more or less only here. The other thing that was done is the horn optimization. So the horn was optimized using genetic algorithm to produce a more intense neutrino beam using a current proton beam. And this actually also led to the increase of the total flux. So the flux as shown before is actually after optimization. And with all of this, we have the updated physics performance of the ESS USB. I want to be clear about the assumptions that we made in our archive publication. So we still look at both distances. Our experiment runtime is 10 years, so 5 years neutrino, 5 years N10 neutrino. And we assume a systematic error of 5% on signal normalization and 10% of background normalization. And there will be a dedicated talk the day after tomorrow by Salva, in which he will show all of this in more detail and also show the preliminary results when we use shape uncertainties and include atmospheric neutrinos in the analysis and more. Okay, so the sensitivity that we are expecting to have now is shown here. So the expected sensitivity for plus minus by half is 11 sigma at the longer baseline and 13 sigma at the shorter baseline. So this is more than enough sigmas that you will ever need. And we will have like 75% CP coverage at 5 sigma in 10 years at the further side and 6 years in the closer side. But what I think our project actually really shines in is the resolution. So with the current assumptions, we actually expect to have less than 8 degrees delta CP resolution over the entire delta CP range. And as an added bonus, we can determine the neutrino mass hierarchy. Okay, so since we are planning to do all of these expensive upgrades to the ESS LINAC, we are already looking at synergies and things that can also be done using short pulses and our neutrino beam. So the first thing about the short pulses is that it allows you to do decay at rest experiments and coherent scattering experiments, which are quite popular now. And also we could think to do a new storm like a muon decay ring. So we could just take the pions from the decay tunnel, feed them in the ring, and then have a new storm. More enthusiastic approach would be to have a neutrino factory. So we could try to extract the muons, cool them, accelerate, and put them in a racetrack like muon storage ring. And then we would get neutrinos from muon decays. And the most difficult thing, but the best thing in the end, we could think to make a muon collider, because we will have a lot of muons, and then you can separate positive and negative ones separately, and then collide them, and you would have a very compact Higgs factory. And you will have enough statistics to know everything that you ever wanted to know about the Higgs particle. Okay, so ESS USB is a European experiment. We are funded by H2020 Design Study. Currently, there are 15 participating institutes from 11 European countries, and the institutes include CERN and ESS. ESS actually currently supports our ideas. We have 6 working packages. So work package 1 is the management, the most important one, of course. Then there is work package 2 is the LINAC upgrade. Work package 3 is a accumulator ring. Work package 4 is the target station. Work package 5 is the detector design. This is where I work. And work package 6 takes the input of all the other work packages and calculates the physics reach. So the possible ESS new USB schedule. We want to be a second generation neutrino beam, which could start data taking about at 2035, after the other ones will probably be built by then. Everything started actually in 2008 with the EuroNew project, and then about 2012 there was a measurement of theta 13, which shown that this is possible. Then we had the cost action, during which we wrote an application for the H2020 project. So here we are now. We are finishing our conceptual design report. Then we need to go towards the technical design report. Then we need to find money. And then we need to construct the thing and start taking data. So now I have to make a summary of the ESS USB workshop, which ended like 3 hours ago, so bear with me. So this is a timetable of the workshop. So first we had a talk by Marcos, our big boss, about the ESS USB and Hi-Fi study program. So Hi-Fi is a high-intensity frontier initiative, which will be like a continuation of ESS USB. And the talk was concentrating on the further projects and funding that we can apply for. Then we had a talk from Boris Kiltoft about the civil engineering at the ESS site. So Boris is an architect, and he had quite a lot of progress on where we can put our stuff. So this is again a map of the ESS site, and the blue parts are where we are would be allowed eventually to put our machines. Then there was civil engineering and safety at the fire detector sites done by David Sayang, who is a professor of geology. So he started doing the computer simulations of the mines and everything, and all of this is actually quite complex and not easy to do, and I don't understand half of it. But so here is like a study of it's an example study of the Garpenberg mine, so the one which is further away. Then there was a nice talk from Colin Carlisle on environment preservation and social commitment of our proposed experiment. So here, for example, he's shown us how ESS itself managed to reduce its carbon footprint, which is quite popular today. Actually, it was quite interesting for me to know that the cooling water for the ESS will be used to heat Lund, and also they will have their own power generation. Then there was talk by Janet Conrad about prospect of decay at rest and coherent scattering at the ESS, and I think that the talk was quite positive. And then there was a talk by Maya about the design of the Newstorm racetrack ring. And then there was a talk by Tord on the muon collider proton complex and the ways that we can start testing the technology to actually produce a muon collider. And last but not least, there was a talk from Professor Carlo Rubia about the physics reach such muon collider could have. Okay, so to conclude, ESS USB wants to measure the CP violation at the second oscillation maximum. Our recent optimizations allow us to reach over 5 sigma at 75% of delta CP range, reach very high delta CP resolution, and determine neutrino mass hierarchy. And all of this is possible be made possible by ESS Linac, which should start operation in 2 years. And the modifications that we propose could not only be useful for a neutrino program, but additional physics program like muon physics, the decay rest experiments, short neutrino pulses, and our large fire detectors can also be used for the rich astroparticle physics program. So all of this was made possible by the funding of the H2020 ESS USB project, but more importantly, all the people that made quite a lot of programs and did quite a lot of work. So I would like to thank all of my colleagues for making this possible. Thank you.
Perfect. Thank you very much for all of this information. Are there any questions in the room?
It doesn't seem so.
Maybe that's a sign that a lot of us were here in the morning to hear the talk. Are there any questions in Zoom?
So everybody understood everything. That's good.
Yes, and also we're very happy to hear about this. Okay, so since we're running out of time and we're already late in the schedule, I think maybe it's best to go to the break, and maybe you can announce when the parallel session will start.
Yes, thank you, Adi. Thank you for convening the session. I think we will start in 15 minutes at 4:30 p.m. the parallel session. I'll give you a few information here. So working group 1 parallel session will be here and will be also in presence today, tomorrow, and after tomorrow. All the other sessions will be online only, because we were so few that at the beginning we booked some other rooms, but we were, I don't know, 1 or 2 people per room. It was, I mean, not acceptable for our administration to keep 1 room for 2 people. So you will find, I don't know, a room or here. You can sit wherever you want. The hotel is very big, or you can go somewhere else and follow the meetings. Just a few information. So we have 1 person of a local organization per parallel session following the session. So if there is any technical problem, you will have assistance, and this person will give also ownership of a Zoom room to the convener, so that the convener can possibly mute participants who are noisy, something like that. And on top of that, there will be a recording of the parallel session. So in the future, people can look at the parallel session again. Tomorrow, we will have a poster session at 10 o'clock in the morning. It will be fully online using the software tool that we already used in the past, and is very, very appealing to follow. So this is chaired by Francesca Dordei, Helio Damotte, and Matteo Cadeddu. And if you log into this software tool that is well instructed in the conference page, you will be able to present your poster, to ask a question to other people. So you just, you just wander around in this virtual room, and you can join other people, ask, as I said, ask question, ask to present the poster. So this is also very funny and very entertaining. Of course, you can have conversation with people here also. So tomorrow we will also have afterwards, we'll also have parallel session. If you stay in the hotel, you will have the coffee breaks in the afternoon. So that's very nice also. And Thursday, we will have a plenary session in the morning, which is the Nufact Storm workshop, chaired by Andrea Longhino and Francesco Terranova. And then this will be followed by a parallel session. I have to say that the parallel session, maybe I have to repeat again, is a real strength of this conference, that compared to other conferences where we have only plenary talks by, you know, senior scientists, I would say, this conference allows even young people to discuss and present their studies together with more senior people in the parallel session, have detailed discussion. So I would say that in my opinion, the next 2 days are the most important days of the conference. Well, really, we will have the parallel session where people can have a real discussion on the specific topic and not just receive information from the plenary speakers. Okay, then for people who are not interested in the workshop, we will reconvene in this room for the plenary session on Friday. And in the morning, we will have a workshop dedicated to the outreach. This is also becoming, very, very important in our field. And in the afternoon and also in the end of the morning, we will have again plenary sessions. So thank you. And we will reconvene for the parallel session in 10 minutes. Okay.
Can I just ask, are we going to move to the working group 1 Zoom or should we stay in the plenary?
Yes, I forgot to say, I think we will move to the working group 1 Zoom. There is a dedicated Zoom for the working group 1, and so we switch Zoom now. Okay.
Thank you. Yeah, we'll see everybody there.
Good to ask. Good to ask. It's program.